So thanks everyone for coming to the third day of Environment Week. We have a bit of an interesting setup with the room today. I'll leave it to the speakers to decide where they look. Just a few housekeeping things. As you'll see, you now have microphones in front of you. So if you ask a question, we do ask that you press the button at the base of the microphone. It will turn red. Keep it pressed while you speak, and that allows also anyone online to hear the question. We're starting a few minutes late just because we're in a different room and there was a breakfast this morning. And yeah, that's it. So please, Veronica, come on up. Let me just remind you that these are 30-minute presentations, so please let the speaker get through the first few minutes, introductory minutes before asking any questions.
Okay. Yeah, this is weird. I don't know where to look. Hi, everyone. I'm going to be talking about anti-deforestation policies in general equilibrium in Brazil. This is joint work with Gabriel. Okay. So the motivation for this is that, well, as you know, there's lots of reasons why we want to avoid tropical deforestation. It's a really big cause of carbon emissions. And there's the instantaneous effect of the release of carbon when the forest is cut down. That accounts for about 10% of annual global emissions. But then there's a permanent loss of carbon sinks if the land is permanently changed to agricultural use. It's a huge cause of biodiversity loss, increased dryness, heat, soil degradation, and it also destroys the livelihoods of forest dwellers. Now, it is considered one of the major components of all IPCC emission reduction pathways that are compatible with 1.5 or 2 degrees warming. However, even though it's regarded as a necessary, avoiding deforestation is regarded as a necessary tool towards stopping climate change, it's also considered one of the most cost-effective, according to several calculations, ways of mitigating climate change. However, in part due to concerns of leakage, it has been, for example, excluded from the clean development mechanisms, which is one of the main green finance tools for developing countries. And there's this big concern that if we avoid deforestation in one place, we don't want to pay people for avoiding that deforestation because it's just going to go elsewhere. So that's the broad motivation. Leakage is defined as this unexpected loss of anticipated carbon benefits due to the displacement of activities in the project area to areas outside the project, resulting in carbon emissions. So in this map, you can see this is a close-up of kind of the arc of deforestation in Brazil. And that blue shaded line, shaded area, are indigenous territories. Everything that's green is everything that was forest in 2000. Everything that's white was non-forest from 2000 onwards, and the red is what has been deforested between 2000 and today. So you see, there's some inside the blue shaded polygon, but very little, and it mostly seems to go around the borders. So this picture is kind of suggestive of leakage, but you don't really know if having protected that area increased how much was deforested outside, or if it had like a net overall reduction in the amount of deforestation. So this paper is going to try to address that question of how much protected areas avoid leakage, how much avoided deforestation leaks outside protected areas. And then where does that leakage go? And work in progress, I'm not going to show a lot of results on this, but the objective of this project is to also say, how does it depend on different targeting criteria? Does targeting some places lead to more or less leakage? How does it depend on trade frictions and migration frictions and on some features of consumer preferences? So the approach that I'm going to take is entirely model-based. So I'm going to simulate anti-deforestation policies in a spatial general equilibrium model of the Brazilian economy that has trade migration, and I add an endogenous deforestation process that supplies land to the agricultural sector. The main reason for this is that in reduced form, even knowing what are the effects inside the area has the challenge that leakage is a SUDBA violation. And there are some approaches to like look at neighboring areas, but I want to take an approach that is agnostic to where the leakage goes. And in order to have a valid counterfactual, you have to assume some region where there's no leakage. So this is my approach. Now, why Brazil? This probably doesn't need a lot of justification in this audience, but it has a third of the world's rainforest and a really large average forest loss. Since 1985, it's been like the surface of Wales every year. It's gone down by a lot since 2004, but it's still quite large. That cumulative over the whole period is larger than the surface of the country of Ukraine, primary forest loss. And the leading conservation policies are spatially targeted. This image is from the boundary of an indigenous protected area. So this indigenous reserve has a fence that has kilometers and kilometers covered in meat. And this is hung there by the kind of patrols of people that go around looking for cows that are put inside their land by invaders. And then they kill their cows and hang them as kind of a warning for people not to come in. That's how it happens in practice, at least in this protected area. This is where they're placed. So the main point I want to make is protected areas and indigenous territories and blacklisted municipalities, which have been sort of some of the main anti-deforestation policies in Brazil, are spatially targeted. So protected areas, and they have very different targeting criteria. Protected areas and indigenous territories are typically placed in places that at the time of establishment have very high forest cover, between 80 and 90% on average. And they have very low deforestation rates as well at the time of establishment. And then what these policies do is virtually ban deforestation. Blacklisted municipalities, on the other hand, are chosen as, so this is a policy where municipalities with the highest levels of deforestation get sort of punished by the federal government. There's a mix of a carrot and a stick. So there's some fiscal consequences for them, but also, yeah, kind of fiscal punishment, but also some incentives to shift away from deforestation to other activities. And there's mostly just increased monitoring, more fines, and more enforcement of illegal deforestation. Oh, I should add that most deforestation in Brazil is illegal. So you should think of most of this activity happening inside or outside of protected areas is not legal. Even in private property, the forest code says that at least in the Amazon region, about 80% of your property should be kept as forest, and the average is about 30%. So really, this is overall an illegal activity. Okay, so a quick preview of the results. The counterfactual exercise that I'm going to show for today is simulating this blacklisted municipalities policy. So I'm going to take as targeting criteria the regions that have the highest levels of observed deforestation. And what I see is that leakage is actually seems to be relatively small, and it takes time. So it's going to be around 8% after 20 years. I also find that allowing for migration lowers leakage, and that agricultural land towards more labor-intensive activities. So more from pasture to crops, which perhaps paradoxically means that banning deforestation in some places increases the labor share in agriculture. Okay, now I'm gonna go into the model. You can start asking questions whenever you want. So the main features of my model are, it's a multi-region model. I'm gonna use the micro regions of Brazil, which are 557, and have costly internal trade and migration. Now, what differentiates these regions is their productivities in the three sectors that I'm gonna have. Well, a little more than three. So agriculture, which is split between different agricultural commodities. deforestation, which can be thought of as a sector producing the factor of production for agriculture, and non-agriculture. And they also differ in their land endowments. There's an initial land endowment in agricultural land and an initial land endowment in the natural use of land, which is going to be mostly forest. And also different amenities. Now, the technologies are, there's non-agriculture and then there's 3 agricultural sectors. The key reason for doing this is that I want to think about the different land intensity of different sectors. So non-agriculture doesn't use land, and then there's pastures use a lot more land to produce output. Permanent crops use a little, and permanent crops use way less. So things like trees require a lot more labor, a lot less land, and temporary crops are in between. Now, preferences between these goods are non-homothetic between non-agriculture and agriculture, and there's constant elasticity of substitution between agricultural goods. Their production functions are Cobb-Douglas. They use land and labor as inputs, but they have different land shares. Whereas non-agriculture, again, has only labor as input. Now, the key addition to the model is that there's a deforestation sector. And the way to think about it is this deforestation sector is kind of like an investment sector in a capital accumulation model. So every year, some forest that was forest the previous year, some agricultural land that was agricultural the previous year will go back to forest. There will be some natural regeneration, but it's mostly carried over as a stock. And then the amount of deforestation each year gets added to that stock. And it's produced with this function that has the decreasing returns to scale. This is basically so that governed by this parameter, by this parameter delta, this is basically so that the costs of deforestation are convex. So there's how much is deforested every year responds to the prices of land, and we don't want to just deforest everything all at once. There's some more details about how the less forest left there is a little bit more expensive to deforest, but it doesn't massively change the results. Yeah, this is showing in a graph how the dynamics happen. So this is quite important because the short-run supply is going to be a lot more inelastic. In 1 year, if the prices of land go up, there's going to be a certain amount of deforestation, but over time, because each year, sort of each year they just get added, the deforested land gets added to the stock, then the deforestation that happens over a long time has a different elasticity than the deforestation that happens in 1 year. Okay, this is a little diagram that shows how leakage happens in the model. The basic idea is that when deforestation goes down in a place, say a blacklisted municipality, there's going to be a reduced supply of agricultural land, which is going to raise the prices of agricultural land everywhere. So it's all a question of how the transmission of agricultural land prices happens from within the protected areas to outside the protected areas. And this is going to happen in the model through the market for agricultural goods, primarily. So there's less agricultural goods being produced in these unprotected regions. That means either there's going to be some substitution away from agricultural goods, so that will depend on the non-homotheticity of preferences, like on the substitutability between agriculture and non-agricultural goods for consumers, but also on how easy it is to instead provide those goods from another region. So, for example, something this model will predict is if a place is very unproductive, if where deforestation is happening is very unproductive in agriculture, it's not going to have a massive impact in the price of agricultural goods if we stop deforestation there. And if the places outside are way more productive at agriculture, then they're not going to need that much land. So that's some of the intuition for why the leakage that I find is very small. That the places where a lot of deforestation happens is mostly due to low enforcement or to more difficulty of enforcement, and not really because they are very productive in agriculture. Yes.
Okay, hopefully this works. I'm a bit worried about the absence of external trade in your model, because my understanding of a lot of deforestation is that it's driven by people converting forest into pasture for beef and then exporting the beef. So A, is that completely wrong? Or if not, B, how do you think about the absence of external trade and export?
Yeah, no, that's an excellent question. I mean, it's definitely a feature that I want to add to the model eventually, but I don't think it's terribly worrying in terms of leakage. So the way I think about it is, well, beef, about 10% of it gets traded internationally, I believe. So it really is largely about domestic consumption. And the Amazon has a lot of big cities that consume a lot of this beef. But also, I think that would dampen the leakage that I see. Because if there is international, I feel, I need to think more through this. If someone has other ideas why it would increase leakage, please let me know. But in my mind, is the fact that there's only a domestic market for international goods means each place where deforestation, where the supply of land gets changed, affects the price of the agricultural good more. So if there's an internationally set price, like in the extreme case that the prices are just purely set from the international price, then a specific place stopping to the forest is not going to change it. So there will be less leakage.
Yeah, I think it's just kind of like applying the model to reality in the context of like, I know, rising demand for global beef, you know, because then the agricultural commodity price would be rising. And my guess would be like that would increase leakage.
Well, it would increase deforestation, but I'm not sure if it would increase leakage in the sense of the counterfactual to not banning. It's all about the counterfactual between same things happening in the rest of the world, but what if we ban or not ban deforestation in this place? How much bite does that have? But I need to think about it a little more. Because in these models, unexpected things happen.
Hi, just like for just to understand, like the price of land is a function only of non-protected areas, or it's also affected by commodity prices or by the productivity of the land?
It's also affected by all those things.
So it will be endogenous, fully endogenous. Okay, good.
Of how banning deforestation will create an increase of deforestation outside. But the demand for agricultural land in each place is also determined by its population, by its productivity, by a lot of other things. A similar thing happens if we don't think about goods but workers. So there's going to be a decreased demand for agricultural workers in the places where deforestation is banned. And that could lead to shifting away to other agricultural activities in that place, but it could also lead to workers migrating outside, either to work in agriculture or work in non-agriculture. The main data that I use comes from the land use data, comes mostly from biomas. It's really amazing data source that I should use. The agricultural census, population census, and then there's some other data I use to calibrate the model, like micro data from the Consumer Expenditure Survey, international prices to calibrate to estimate the elasticity of deforestation to commodity prices, so to land prices. Yes, and trade flow between states. I'm not going to go through this boring slide on all the parameters. The main thing is there's some parameters that I estimate outside the model and some parameters that I calibrate exactly from data. So that would be the sector region TFPs and the regional amenities come from a model inversion that uses population, the current distribution, so how each region distributes the land between different agricultural land uses, and the share of population working in agriculture those are exactly matched by these parameters. This I'm gonna go through kind of quickly. So this one I was quite pleased with, the calibration, the validation of land rental rates. So this is taking how my model that only uses agricultural revenue in the 2006 census fits land prices reported in the agricultural census. So this is how people report how much their land is worth. And because land markets are quite imperfect, you would be worried that these don't match that well, but they match reasonably well. And they're weighted, the circles are weighted by the amount of land in each Wages are a little bit less good in big cities, but because this is mostly about the agricultural sector, I'm not too worried, although I'm working on improving it. If you just look at agricultural wages, they're a little bit better. Agricultural value added is reasonably well matched. Non-agriculture is working. Migration shares. Okay, so now let's go into a counterfactual. So I'm gonna first let's look at how unevenly distributed deforestation is. If we take these micro regions, the top 20 micro regions account for about 40% of the aggregate deforestation in 2006. And they're very similar to the municipalities that were blacklisted in 2008. Because it's a different administrative unit, they don't fit perfectly, but it's kind of a good approximation. And it's those red ones in the histogram. Now the counterfactual exercise is going to be, I'm going to calibrate the regional fundamentals to fit the data in 2006, solve for the equilibrium, and then pin down a vector of deforestation for each region. So like how much deforestation there will be each year for the next 20 years, updating the land endowment stock. But I'm going to do this for 4 different scenarios. If there's policy or no policy, so if I fully ban deforestation, yes, the key thing is the policy is going to be fully banning deforestation. So setting that deforestation TFP to 0. And I'm also going to compare what happens if I allow for migration or don't allow for migration. So these are the top 20 microregions. And you really see they have a lot more deforestation than the rest of the country. And this is what the paths in the total stock of agricultural land look like for those 4 scenarios. So the dotted lines are without policy, and red is with migration, blue is without migration. So there will be, that's how the land stock, the agricultural land stock would evolve over the next 20 years, according to the model. And it really goes down with the policy. Now let's just look at leakage. So the leakage is going to be the policy line divided by, no, sorry, it's not that. The leakage is going to be how much, it's going to be the increase of deforestation as a result of the policy outside of the protected areas divided by the decrease in deforestation in the protected areas. So it's a percentage, and it's to be interpreted as like 8% of the deforestation that was reduced was increased outside. And it takes time for it to happen. This makes sense because of the dynamics that I described, that this elasticity, supply elasticity of land is a lot more elastic in the long run. So, yes?
Down deforestation at baseline, or is it the model predicts some amount of deforestation and some amount you look at changes?
Yeah.
So what I'm saying, I'm fitting the actual deforestation in the data and the initial period.
Yes. Yeah. I'm fitting it in 2006. That level of deforestation is perfectly matched. And then this is more than to actually fit the trends, because there's a lot of other things changing over time. More than to fit the trends is to see a bit more of a long run effect because of this different elasticity of supply over time. Maybe over 1 year, the supply of agricultural goods is not going to change that much from that little bit deforested. But once we allow for a large chunk to not be deforested, that changes a lot more. Thanks. Yeah, you had a question?
Oh, yeah. No, I was thinking about why only with 1 year.
Yeah.
So,
It is for simplicity to know. I think once you try to calibrate all the different things that are happening, like that the TFPs of agriculture and non-agriculture are changing as well, it becomes a little less clear. Here I'm thinking in kind of as a static exercise, but to allow it to have more bite, I want to allow many years of avoided deforestation to really happen. That makes sense. This is how it looks in space. So you can see it looks, this is just in square kilometers. So the blue is how much, sorry, the numbers are really small in the legend, but The blue is how many thousand square kilometers of deforestation were reduced after 20 years, how much avoided deforestation happened, and the red is how much it increased outside. So you see, it sort of happens in neighboring places, but not really in a clear, in a pattern that it would be easy to predict ex ante in a reduced form strategy. Not like clear rings of where it happens. And some non-neighboring places have big increases in deforestation. Although overall they are quite small if you look at the legend compared to the yes.
And the data determines which places end up red.
What in the data determines that? Well, largely they're deforestation TFP. So the deforestation TFP is to be interpreted as it's what gets calibrated in the data from the data based on. So basically, is a residual of how do we explain the observed levels of deforestation beyond agricultural productivity, more or less. So why do places that have, my model rationalizes high deforestation in places with low agricultural profits as a high deforestation TFP?
I'm wondering whether you can use that, I'm not sure I understand, as a way to run a reduced form strategy. Do you just need to be able to say that these red places are close to the blue places in some space, and that defines space? It's the TFP in deforestation, and then you could run a reduced form.
Yeah, I guess, okay. So to be more precise, there would be two things. There would be this TFP in deforestation, and then something that is dependent on what places are blacklisted. So that's just a fundamental of the place, and then some component, some aggregate, yeah, some aggregation of what place where it got banned. The interaction of those two would be what places are red. But I see your point. I think your point. I think that would be really interesting. Okay, I have 5 minutes. That's great. This is a different way of measuring it. So it's in percentage terms rather than in just square kilometers. So the difference between the policy scenario and the no policy scenario in percentage terms. So the way to interpret this, if we have minus 65, that means there's a 65% reduction in deforestation rate relative to the policy scenario. Yeah, or a 2% increase, whatever. The maximum is a 3.3% increase. Yeah, that's a really good question. So, what is? Sorry. I don't know where that backup slide is, but I take the trade flows intrastate in 1999, and I back out how the trade flows respond to the distance. So I just take Euclidean distance, and then I fit that to the micro regions. I think it would be really interesting to use something a little bit more micro on actual transportation networks. But so far I'm just using Euclidean distance and the elasticity calibrates those flows.
But it's not taking the road distance rather than making the distance.
Yeah, that would be a good improvement and probably significant, significant, especially for those frontier places. But yeah, any other questions? Let's see. I guess I have a little bit of time for those extra outcomes. So I thought this one was interesting. So this is overall GDP in how it changes relative to, this is the percentage change in the policy scenario relative to a no policy scenario. So if we allow for migration, I thought it was interesting that over time, there would actually be a bit of an increase in GDP. And this is mostly explained by people moving to places with higher productivity when deforestation is banned. Yes?
So they live in places with high amenity and low productivity prior to the policy? That's what's driving this red line.
Yeah,
So it's nice living in the Amazon.
well, it has the problems of amenities being measured as a residual. So there's something unexplained that drives people to, something unexplained by incomes, driving people to live in the Amazon. And when we ban deforestation in those places, that stops happening. Whether that's amenities or whether that is coercive structures, we don't know, but yes.
So if you do the equivalent bar with welfare, because presumably welfare can't be fixed by this, if we ignore the externality.
Excellent question.
So these guys, their incomes are going up, but they're moving from a place they like. I guess the interpretation.
Yeah. Yeah. Right. But whereas if we don't allow for migration, GDP decreases. Now, the labor share in agriculture goes up. This mildly surprised me. That banning deforestation, you have less agricultural land. I thought this would be tied to some kind of structural transformation as well. Or we don't deforest there, there's less going towards the agricultural frontier. But in terms of people, the story is a little more complicated because so much of this land is used for pastures that are very land intensive and need very little labor. And once deforestation is banned, in the model at least, the price of land goes up. So then it becomes more profitable to do more land in more labor intensive things. So there's a shift to it, and yeah, this is how there's a shift away from pastures towards crops. So the share, the agricultural share, the share of agricultural area in pasture goes down by 0.15%. Yeah. Yeah, that's all. Any other questions? Yeah, there's next steps, like adding international trade, as you mentioned, teasing out a little bit more what this residual of deforestation does, and mostly trying out different targeting criteria to see how much it depends, like how much this low leakage is. This was a really good way to target, and how much there's just low leakage because of frictions. Thank you.
Well, good morning. So what time is it? Just one. All right. So thank you very much. So first talk was a good introduction, like on what I will be talking about. This joint work with Igor Carreira and João Paulo Pessoa and Francisco. We are currently revising the paper, so like feedback's very welcome. So this is part of this broader agenda of trying to understand the environmental footprint of agriculture in tropical ecosystems. We know that agriculture is important for food security, economic development, and so on. However, agriculture is the main driver of deforestation in tropical regions, right? And it's one of the main source of greenhouse gas emissions in these places. And this is basically because tropical forests hold a lot of biomass in the vegetation that's basically burned in the process of converting forest into agricultural land, right? And today we are going to be focusing on two key forces driving agricultural markets. That's technology and trade, okay? And so first, what we know about how trade and technology affect deforestation, right? So first, trade. Conceptually, the environmental impact of trade depends on a series of factors like changes in production scale, changes in product mix, adoption of more productive and cleaner technology. So it's ambiguous, the effect. Empirically, all the evidence that exists points that trade increased deforestation, right? Through trade liberalization exercise, commodity price, regional trade agreements, and so on. Okay. There is another literature that tries to understand how agricultural technology productivity affects deforestation. And here there are two hypotheses that are ambiguous as well. That's one is that new technology that increase agricultural productivity, they make agriculture more profitable. So this leads to entry and expansion of agricultural frontier into new land, forested land, right? On the other hand, there is a more recent hypothesis that says that maybe higher productivity leads to production intensification, right? So you need less land as a factor of production, and this slow down deforestation. And a key assumption, this type of hypothesis, that there is some type of factor constraint limiting the expansion of agriculture, right? Empirically, evidence is mixed. So the type of evidence that we have, it's that agriculture extension programs seems to have reduced deforestation in a couple of countries. Early electrification in Brazil around the 70s and 80s generated like increased agricultural productivity through the use of machineries and seems to have slowed down deforestation. But there are some evidence that community-driven development programs increase deforestation in some settings. Okay? So as you see so far, like the literature is kind of divided. However, you should think that trade and technology, they are very connected, right? You can think like trade may affect productivity by granting access to cheaper inputs, fostering innovation. Productivity shapes trade, right? Comparative advantage, specialization, so forth. And furthermore, if you think like on the potential effects of new agricultural technology, we should think that the full gains from technology depends on having demand for the product that you're producing, right? What's the use of being very good at producing something that nobody wants to buy? Okay. So I think we should try to think how these two dimensions, they work together or they work differently on impacting deforestation. And that's what we do in this paper, right? So we are going to try to estimate the relative impact of increased agricultural productivity and trade on the expansion of agricultural land over forest. We are going to be focused on Brazil, and we are going to be looking at relative deforestation of local exposure to two shocks, genetically engineered soy seeds and increased demand from China. Okay, so here we are, so this will be a reduced form. We won't be thinking about structurally about leakage or spillovers. We do some exercise, as Veronica said, of looking at spillovers to neighboring municipalities, but we don't find anything there. Okay, so here we are not thinking about the global impact of trade on deforestation. We're looking about the differential exposure to trade and technology on deforestation. And we think that this setting that we are studying is relevant because different from the previous literature, we are looking at the new technology that favors large-scale agriculture. We are looking at a setting where labor and capital constraints were likely loose. So there was migration responding to new production opportunities. The government was pouring money on the agricultural sector in this period. And there is evidence that this technology shock triggered the process of capital accumulation and money flowing around the country, right? On top of that, the China demand shocks not restricted to Brazil. It affected most low-income, middle and low-income countries, right? So just the main result is that it seems, our results seems to show that change in comparative advantage brought by this new technology is the main driver of expansion of agriculture into the forest. Okay, so what I will do, first I'm going to describe the key elements of this work and already telling how we are measuring these things. And then show the empirical specification and we go to the results. Okay.
So you're trying to assess the relative importance?
Yeah.
But you're not thinking that they're interacting?
We are going to look. But relative across regions in Brazil. So we don't have a counterfactor where we have soybean win a war without China. Right. What we are trying to get is kind of regions that are more affected by technology, or they're more affected directly by China. Does that make sense? Cool.
Can I ask a question?
Yeah.
It could also be like biofuel policy, or other types of shock, anything that would affect.
Yes. So biofuel, it could be. We are not disentangling this here. It's not the type of. What I'm trying to think is like if there was some major technological change on sugarcane biofuels in Brazil. I think biofuels is more a matter of international demand for ethanol, but it would be a demand shock.
Yeah, I'm just
Yeah.
thinking of other big things.
Yeah. Yeah. Thank you. It would be another demand. All right. So land use trend, Brazil has a large forest area, and nowadays we're a major exporter of agricultural goods. If we look, and probably between 95 and 2015 or 2017, the share of forest area in the country has been declining steadily. We see this inflection point here, this trend break. Around 2005, 2006, this is when the government started to actually act and impose a series of policies to fight deforestation in the Amazon. But you see, forest cover continues to fall. On this earlier period, what was the main driver of deforestation was pasture expansion, right? Overall, once the government starts to fight deforestation, you see that kind of expansion of pasture stalls, and overall area of pasture in the country starts to fall. And here the scale may give a wrong impression, like still like a fifth of the country is pasture, right? And cropland, we see a steady and steep growth of cropland during the whole period, right? So how we are measuring this, we are using land use change data from Mapiomas, that's also Asuman did. And we are going to aggregate this at municipalities. So our variable of interest in the end will be change in forest cover, pasture, and cropland in the country. So we see that most of the area where we see loss of forest cover is here, on the border here of the Amazon, the arc of deforestation. And this is an area where you have increased pasture and increased cropland. Right? We see a lot of cropland increase here on the southwest as well, and the center of the country. Yes. Right? So the first shock, genetically engineered soy seeds. These are basically more resistant seeds to herbicide, and they require very little soil preparation. So you can basically spread the seeds, put the herbicide and all the chemicals on the floor, and it grows. And important to our setting is that more than just like a productivity gain, this technology made it feasible to produce soybeans on areas that so far, until then, it wasn't feasible. Right, on warmer areas that wasn't profitable, wasn't feasible. This was developed in the US, but it was only approved in Brazil in 2003. And it's common sense that geosoil is central to the explosion of agricultural markets in Brazil over the last decade. Jacopo and co-authors, they've shown that this shock led to structural transformation. It actually led to increase in the area produced with soy, natural process of capture accumulation, so forth. And now Brazil is the largest soybean exporter in the world. Okay. So how we measure differential exposure to soy? Basically, we follow Jacopo and co-authors here. Basically, we use FAO data. They compute potential yields for different crops or in different pixels under different agricultural input combinations. In particular, they have a potential yield using modern inputs that includes seeds, fertilizer, etc. Potential yield using traditional production, that is without using modern inputs. You can think about this using productivity, rain-fed or irrigation, right? And so we measure local exposure to these potential gains from adopting GE soy seeds in each municipality as the difference between the potential yield of using modern technology versus potential yield using traditional technologies, all rain-fed because irrigation is not big in Brazil, okay? Especially on the side. No, promoted in, it was financed later. There was credit lines, subsidized credit, and yes.
And was the subsidy just for seeds or?
No, for agriculture sector.
So it was for irrigation.
For the agriculture sector as a whole. Irrigation is like, it's not here. It's not important. Yeah, but it's for agricultural sector as a whole. So there is like biofuels, like so sugarcane, there is maize second cropping of other maize. There is a lot of subsidy for the agriculture sector, for cattle, in the cattle industry. There is a lot of subsidy flowing into the sector as a whole, not only soy.
But these subsidies include all across Brazil at the same time, or was it decentralized?
It's centralized when it starts to have like after 2006, like with this part of the one of the components of fighting deforestation in the Amazon is conditioning this credit or the subsidy to environmental compliance. But then it's like in one region after 2006.
Here, I mean, anecdotally, some evidence that a lot of this soy was displaced in hospital, actually not a and so the good identification will try to capture that within the boundary. Yeah, we might not find it might be other effects.
Yeah. So this is a very local effect. What we did to look at the displacements, trying to look at effect on neighboring municipalities using different definition of so the other municipalities within the microregion, different threshold of how close the other municipalities are. I'm not going to show the results today, but basically it's on this type of spillover we don't see.
You do not see.
We did not see any. Yeah, it was surprising. Yeah. Yeah. Okay. Right. So Brazil-China trade. So China joined the WTO in 2001. This affected trade everywhere for low and middle income countries. In Brazil in particular, this represented a major shift on the type of trade. That's a commodity for manufactured trade boom, where Brazil starts to export more than just like an increasing the volume of trade with China. The pattern of trade changed a lot. That's so the share of agricultural extracting sectors in export to China grows from under 20% to over 80% and keeps growing on 15 years, right? So, and here, we'd like to build a measure of local exposure to this growth in demand from China. And here we cannot simply look at trade flows because other factors affect trade flows, including, for example, soy, renewables, and other things. So we are going to build a measure of local exposure to trade using a two-step procedure there. First, we try to isolate the China product-specific growth on imports or demand on this period. So we use bilateral trade data, and we run this regression on the growth rate of imports from every country, C, and product J. We are excluding Brazil from the sample. On product fixed effects, and this side, that's a China product fixed effect. So what this China product fixed effect capture is deviations on the growth of imports from that product of China relative to the growth of imports from the rest of the world. Okay. And we are going to use this to build kind of a shift share measure where this is the shift, right? And we allocate the shift across Brazil using a combination of the share of that product grown in the municipality in 95, and we use 95 because the earliest agricultural census that we have available. The share, the value of Brazil exports to China in 2000, right? So we basically distribute this growth on Chinese demand relative to how much Brazil would sell to China and distribute across the country according to the production share of each product across municipalities. So if you think on this new shift share literature, we are trying to exploit here shift exogenate, right? We actually don't have so many sectors to exploit a share exogenate. Okay. Good. So then our main specification is simple. We are trying to get the local impact. We are going to regress long change in land use in municipalities between 2000 and different years on exposure to demand from China, local exposure to technology, and an interaction term between both, and state fixed effects and a series of controls, basically what are used in the literature. We do Conley standard errors. And key here for us is that there is spatial variation on regions that they are being affected, exposed to trade and exposed to technology, right? And yes, there is a correlation, it's 33, that's a 33 correlation, but there is some variation, spatial variation. For example, from the municipalities most affected by either of the shocks, only about a fourth are affected by both. So we have some variation to explore here. And the identifying assumption, here's that conditional controls. This differential exposure to G, soy, and China, they are not correlated with other determinants of land use in the field. So I have what, 10 minutes, right?
Can you say again what
XI is China. Local exposure to China-specific demand.
Have you considered that rather than just interacting the AI with the XI, you could think of another definition of XI which uses the FAO Gaia's like relative productivity across products using modern inputs? Because I'm thinking the way you define XI at the moment takes production in 95, which is like X all these modern inputs, right? It's like X.
Yes.
It doesn't have, yeah, exactly. So I'm thinking that at the same time as China's demand is growing, you have these technological changes going on, and that changes the relative productivity across products of different areas. And so that would be captured if you use the FAO Gaia's data. And it's just like a different way of using the shift share, which might get a more dynamic interaction between the two.
Yeah, right. The points that we only have 3 points of agricultural census, and that's, so it's 95, or it's 2001, 2002. 2001, 2002, it's...
Yeah, but the FAO Gaia's, so that's what I'm suggesting, is that rather than use the agricultural census to define your X-hat, you use the FAO Gaia's data on how suitable different areas
instead
are
of
using
share.
modern inputs. That's a crucial.
Yeah, I would have to think. But thank you, I see. Instead of actual share of productivity, like some comparative advantage. I see. Good. Okay. So I have to think. Yeah. All right. So results. So here we are looking. First, let's look at the long difference 2000, 2017, just to decompose the effects, and then we look at the dynamics of the effect. So here, the first column, if we just run changing forest cover and exposure to demand from China, we see some negative relationship that would mean greater exposure to demand from China means less forest cover over time, right? When we only look at the GE technology, we see it's more significant, and the coefficient's bigger, but more than the coefficient, the magnitude's bigger. We see this negative association stronger. That's kind of greater exposure to suitability to the new soy technology. Means that you have faster deforestation in the period. When you put both together, you see that basically the exposure to China, it's zero, right? And all the effects captured by the exposure to the new suitability. And one thing that I may have been fast, like this growth, this demand growth from China is not only soy, right? We have the concordance that we managed to do. We have 37 products. China is buying out of everything. Several. Brazil used to produce lots of this product, used to export lots of this product. And what we are seeing, like when we put both together, basically everything's about soy. When we add the interaction, and just like to give a sense of the magnitude, if we compare municipality that's in the 75th and the 25th percentiles of exposure to soy, this means that over the period, this municipality lost 1 percentage point more of forest than the one at the 25th percentile. And yeah, with you. But I think it may make sense. Why? So what this interaction is saying is that basically this exposure to this technological shock effect on deforestation is smaller on areas that they were also greatly exposed to trade shock. Who are the areas that are greatly exposed to trade shock? They are areas that they already produce some sort of cash crops, right? So how we think, and here we cannot give the full mechanism, is that what this is capturing is that if you think on the technology shock, on this intensive margins of increasing productivity on places that already produce commodity cash crops, and this extensive side of the technology that's basically opening new areas to cash crops, I think what this interaction is saying is that the effect on deforestation of the technology is larger on these extensive margins on areas that they were not growing cash crops at the beginning of the period. Does it make sense? So causally, no. We can look like what we can look at some. we looked at some descriptive stats from this region to understand like who are these guys, and it's basically this like this. These are areas that they already grew rice. They are more likely like, we have a bigger share of. Our first hypothesis was that maybe these areas that they grew more cash crops, they had less forest anyway, so it's more kind of a decrease in return. It's not just like looking at descriptives, it doesn't seem to be the case. So places that they are being hit by the both shocks, they don't have particularly more or less forest at the baseline than the other places. What it seems to be more different is this. It's kind of, it's the composition of how much cash crops you have.
Clarifying question. How was the outcome defined exactly again?
The outcome is changing forest cover. The share changing in
The percentage change relative to
yeah, it's only percentage. So it's you have the share of forest in the baseline. So we exclude everything that's urban and other use. So out of everything that's not urban and other use, what's the share of forest? What's the share of crops?
Oh, okay, so if they change the percentage of the municipality.
Yeah.
And
here is robust, like if we use some type of inverse hyperbolics, and like if we do transformations on the left-hand side, doesn't.
Yeah, no, just asking because I was having some results. Sometimes are very sensitive to it. And I found anyway, maybe that's more later, but later that if you deforestation as the outcome, that's kind of bound, it's censored at 0, so it can be something later.
Right. Here is censored at -1 and 1.
Yeah.
Okay.
In principle, you could split the sample between those that were doing cash crops in 1995 and see how UG soil differs, right?
Right.
That would be.
Yeah, because I think we have power. We may have power to do that. Good. And just like the others here, like assessing that identifying assumption, like we don't find any relationship on these shocks affecting land use before 2000. So probably I'm running out. Where this expansion of forest is coming from, basically it's expanding crop, reducing pasture. So it's that movement that like basically crop is you're converting pasture to crop and you're converting forest to crop. If anything, like we have in place more exposed to demand from China, we have a conversion from crop to pasture. And the interaction go all in the same direction that we discussed before. We have some robustness. We pull everything together to show the dynamics of how this effect takes place over time, but I think I'm running out of time. So in sum, we are trying to look at the differential local impacts of new agricultural technology and demand from China. And I think our main result seems to be that this is like changing comparative advantage brought by the technology seems to be the main driver of deforestation. So I think it's important to think jointly about productivity and trade when looking at deforestation, right? Thank you very much, and comments are welcome. Thank you.
Thank you. Hi, everyone. Thank you to the organizers for including our paper. My name is Anna Papp. I'm a 5th-year PhD student at Columbia at CIPA, and this is joint work with Florian Grosset, who is also at CIPA and will be on the job market this year, as well as Charles Taylor at Harvard Kennedy School. And so after these two excellent talks on deforestation, I'm now going to shift us towards afforestation and talk about land use policy, climate change, and adaptation. So these large tree planting programs are becoming increasingly popular with policymakers. And perhaps this is not that surprising because trees are sort of like the original carbon capture technology. And so we see a large number of countries in the Paris Agreement, for example, prioritizing some sort of land use or forestry to meet carbon mitigation targets. Perhaps the most famous example is the Sahel's Great Green Wall, which is shown, the logo for which is shown here. But there's many other ones you can see on this timeline. All these programs that are being announced basically every year or even more frequently. A perhaps less well-known one is Pakistan's 10 billion tree tsunami. And this picture here is an image of the tree nursery for that program. In addition to the carbon mitigation, these programs are also popular for their effects in reducing soil erosion as well as local dust storms. And actually, for these reasons, there's been a longstanding interest in these types of afforestation programs that go back decades. This example is from the plan from the USSR, and then this is from China from the 70s. And then the program I'll be talking a lot more about is the US's own afforestation program in the 30s and 40s. However, so these programs are popular for the carbon mitigation and for the local soil erosion effect. What is less talked about and less attention paid to the local and regional climate effects of these programs. And so why might planting trees in a place where there were no trees before, which is what afforestation is, why might that actually change climate locally? That's because trees are changing the energy fluxes between land and the atmosphere, specifically evapotranspiration, which is the transfer of water from land and trees to the atmosphere, as well as albedo, which is the reflectance of land. And so for these reasons, the natural science literature, which mostly relies on modeling studies, shows that there's a potential impact of afforestation on precipitation. And specifically, we expect that to increase in the areas where trees are planted because of this additional moisture, as well as in the neighboring areas as wind transports this increased moisture to nearby areas. Then there's also, from the natural science literature, a potential impact on temperature, although this is actually not, this could be ambiguous where trees are planted due to the interplay between these different physical mechanisms, but we still expect a decrease in the neighboring regions where trees are planted. So then these policy-induced afforestation programs can impact potentially climate, and then the changes in climate can then have socioeconomic consequences, either from the direct impacts of climate change or adaptations to this local climate change. And so this is what we study in this paper. Specifically, we asked the research questions of how these large-scale tree planting programs affect the local and regional climate, and then what are the resulting economic effects of these local changes in climate. The program that we study is in the US, and it's called the Great Plains Shelter Belt Project. This was a large tree planting program that took place in the US Midwest, in these states, in the late 30s or mid 30s and early 40s. I'll talk a bit more about it in a few minutes. And so we implement a difference in differences empirical strategy that also considering spatial spillovers. And to preview our findings, we do find that this tree planting has an effect on local and regional climate. Specifically, we do see this increase in summer precipitation and a decrease in summer temperatures, which together are basically like this more favorable weather for agriculture. And we see these effects both in the directly afforested areas as well as in neighboring regions, downwind regions specifically. And then we also find that this change in local and regional climate has impacts on agriculture, specifically we see an increase in yields. Corn yields is what we focus on. And then we also show some evidence of actual farmer adaptation to these more favorable growing conditions. And so that I'm done with my intro. So yes, question.
How far are these local effects understood or targeted in the program, perhaps not in the historical setting study, but in the set of policies that you moved?
How far are the local effects?
Yeah, I mean, it seems that if there are these potential gains that you mentioned and adaptive benefits? Is this something that, given the amount of science and evidence that we now have, is sort of understood and incorporated in policy design?
I see. I see. I would say in general, from at least the policies that I've seen, the local effects are really talking more about the soil erosion and the wind erosion effects, not necessarily the local climate effects, if that makes sense. This specifically, no. So there was not a lot of forest in this area in the US. No, actually, so this region is mostly plains region. So we have some data from the early 1800s, and there's very little forest then. Of course, that's maybe different from some of these newer programs that are perhaps targeting previously deforested areas in the Amazon or elsewhere. Yes.
Yes. We have 8 different, but will you talk about the timing when they materialize, or will you take this talk at the end of the century?
Yeah, so this is a good question. So an advantage of studying this program is that it was a long time ago. So we have decades of data afterwards. I would say that on the climate effects, at least, because sort of year to year precipitation and temperatures kind of vary a lot, it's a little tricky to nail down exactly when the timing happens. But so mostly in the presentation, I'll be focusing on sort of think about it like the effects in the decades afterwards, after the tree planting. But yes, we'd hope to do a little more on the exact timing. Okay. So I'm not going to go into detail here, but basically we are just adding here to this kind of emerging literature on local and regional climates of climate changes due to land use, as well as providing direct causal evidence on impacts of climate change, as well as adaptation to climate change. Okay, great. So then to give a little bit more background on this particular afforestation project, as I mentioned, this is taking place in the US Midwest, 1935 to 42. So if you're familiar with this region, the years of the program might already suggest to you that this has something to do with the Dust Bowl, which were basically a series of these very destructive dust storms in the region and a lot of soil erosion. And this is in fact the case. So this was in response to these, or partially in response to these destructive storms. And the afforestation here, or the tree planting here, you should imagine not as dense forest, planting dense forested areas, but really sort of these windbreaks or these lines of trees. And so this is zooming in here on Kansas here, and this is modern day satellite imagery, but I don't know if you can see, but the blue lines are showing where these shelter belts were planted. A lot of them are actually still around. If you're driving around in that area, you can see them. And so really it's these windbreaks, not dense forested areas. At the time, this is the largest afforestation program. Over 220 million trees were planted in this region, in this map I showed before, from North Dakota to northern Texas. Awesome. So now moving on to the data. So obviously, we first need data on where these shelter belts were actually planted. And so for this, we digitized some historical maps of the shelter belt areas that are coming from the decades after the program, including the one I just showed before. So, these, the dark shaded regions are basically the areas of this concentrated tree planting. So again, not all of this was forest, but imagine a lot of those lines of trees planted in these areas. And so then we convert everything to a county database. And so the green counties here are the treated areas that have, based on the map here. Yes.
You have this big area.
Yeah.
Within that area.
Yeah, that's a good question. I think I guess there's, so you're asking whether the trees where actually were planted are different.
With the whole region. Rather than
Yeah, so I guess we do a couple of things. So we do also have this shapefile data that was done by a geographer who's digitized USGS quadrangles from the decades afterwards, where it's actually showing where, well, it's based on slightly later data, but it's showing like these lines of trees where they were planted. And so we compare this, and it's very similar to the maps. So in terms of like the accuracy of these maps, that's reassuring. And in terms of like differences, we do address, for example, like we do run an IV where we instrument the planting with either like soil type or distance to this like region that was kind of this like gray shaded area was basically where what they were targeting. So, and we still find similar things. Okay, so then we combine the digitized maps with various other data sources, including data on wind speed and wind direction. And I'll talk a bit more about wind in a few minutes. In terms of outcomes, we use climate or weather outcome data, precipitation and temperature, mostly from station data, because of the timing of the program, but then also verify robustness to other like monthly commonly used data sets. For economic outcomes, yield and land use and things like that come from USDA annual agricultural surveys or 5-year censuses of agriculture. Okay. Yes.
Can I ask if you know how long some information about the kind of trees they plant?
Yes, that's a very good question. So, and I'll come back to that sort of in my conclusion of like the external validity of this tree planting program. There is some data in the decades afterwards. So roughly, like there were surveys seeing how many of the trees survived. Overall, about 61% of the trees survived, although there's some like variation in the types of trees and all that. And actually they used many different kinds of trees, so over 30 different species. And there was a lot of attention paid to the to planting like local and native like native adapted trees for this area, and also like shrubs and other kinds of greenery. Yeah. Okay. So then coming back to wind, which again is important because wind is one of the main mechanisms through which the increased moisture in the air from the planting of the trees can then travel to nearby regions. So to take this into account or to use this for as spillover analyses, what we do is we construct an approximate measure of wind exposure. And so this is so what I mean is that we're trying to get a sense of in the summer for the counties that are not where the trees were actually planted, but nearby, how much wind is coming from like through the shelter belts, potentially carrying this additional moisture. So I'm just going to demonstrate quickly how we construct this measure. So this is zooming in on part of a shelter belt in like Western Kansas, specifically like the 3 green counties. And so we take hourly wind data and including direction and speed, and then we sort of imagine like imaginary particles moving in that wind direction. And then for the neighboring areas, you basically count how many particles would pass through those counties. And so for a county like this L-shaped county, you can sort of intuitively see that a lot of the wind coming from these 3 counties would go through. And so this would have a higher wind exposure metric compared to counties nearby. But then we add this up, of course, this is just illustrating for these 3 counties, but then we do this for every hour in the summer and for every county. And so this is our wind exposure, this approximate wind exposure measure in the end for the neighboring regions. And then so we then use this wind exposure measure to classify counties into various different groups. So I showed you the treated counties before. Then we also have the downwind neighboring counties using the wind exposure measure, counties that are nearby the shelter belt, but higher than the median of this wind exposure metric. And then for the remaining nearby counties, we have this other neighbor county name. So these are again near but below the median wind exposure. And then we'll be comparing all of these different groups to the pure controls, which are this kind of belt around 200 to 300 kilometers from the shelter belt. Great. So then these groups will form the basis of our main empirical strategy, which is a difference in differences model, again, considering spatial spillovers. I always forget to say this, but the time period that we look at is from 1930 to 1965. And so what we identify here, the beta 1 is looking at the local effects of tree planting. So this is in the shelter belt counties where there's afforestation. And also looking at, for the beta 2, is the spillover effects, if you will. These are looking in the downwind neighboring counties. So this is the regional effects of tree planting. And then the other neighboring counties, for at least the climate effects, we don't expect significant effects there. So this is sort of like a placebo check. This is the non-downwind counties. So, yes. Who was managing the trees? So initially, it was so this was during the Depression era. So a lot of the trees were planted, brought in from nurseries, planted by the government, and then the farmers, on farmers' land. And then in terms of afterwards, the trees were not irrigated or anything like that, due to not a lot of water at that time in the region. So I don't think there was necessarily anybody particularly managing the trees year to year, although of course farmers whose land the trees were on could have contributed to that, if that makes sense. Pretty much, yeah. I didn't mention this, but the end of the program, 1942, basically that was because of World War II efforts, the US's World War II efforts, and so after 1942, the program was kind of there was nothing officially done about the trees after. Yes. Yeah, so this is a great question, and the wind data from this time is not amazing, unfortunately. So the way I think about it is that the wind exposure measure that we're trying to get at here are these really big, big patterns of kind of the larger scale wind patterns. It definitely very locally, on the field level, for sure we expect the winds the houses and pasture land to be sheltered, for example, by the shelter belt, as the name suggests. But we've done some checks on these larger patterns of higher up. This is all at the 10-meter level, for example, and the wind, these larger patterns of wind don't seem to have changed due to the shelter belt. But yeah, I think it might yeah, and I wish there's better early wind data to kind of address this more. So I definitely welcome suggestions on that. But yeah, that's sort of thinking the difference of the local wind versus the larger wind patterns. Sort of what we have in mind here. Yes, Matt. Yeah, so that's a good point. Yeah, because in the summer winds are sort of towards the north in this region. But then, so we do also use the wind exposure measure, not as a dummy here, but also a continuous measure, because we do worry that if it's just the western counties, there's differences as we move from east to west in this part of the country, in terms of rainfall and other things.
I heard we just see the rainfall patterns changing that much over time, sort of what's getting interesting. Rainfall each day.
I see.
Can you see this in this specification?
It's relatively small, and actually there are sort of decadal, it is pretty noisy, rainfall in terms of comparing the magnitude of the change we find, it's pretty noisy. So, but yeah, so, sorry, does that sort of answer the question?
Just like.
Yes.
In the sense of, I think this higher levels of currents, like they are mostly driven by pressure difference.
Yeah.
Driven by ocean temperatures, etc. So I think the direction of the wind will be affected by this monster.
Yes, yes, thank you. That's exactly what I was trying to say. But yeah, that's perfect. Yeah, because this is a 10-meter like larger wind patterns. Exactly. Okay, so then we also implement some other alternative specifications in part to address some of the questions that were brought up. So we also do a synthetic diff and diff, long differences, and an IV approach. I'm happy to talk about these more later if there are questions. But if not, I'll go into the results. So I'll start with the results on climate. And so what these coefficient plots are showing are on the left precipitation, on the right temperature for the summer. And the different colors are these different empirical strategies I mentioned. The red one is the main diff and diff that I talked in more detail about. And so first, looking at the shelter belt counties, we see that rainfall in the summer increased. This is about 0.2 centimeters or roughly like 3 to 4% in the summer months. And then temperatures, this is average temperatures, decreased by about 1%. I'll also show you, we also look at like extreme temperatures, like maximum temperatures, and also like 29 degrees Celsius degree days, which are especially harmful for crops. And there we see an even larger decrease of about 6 to 7%. So then moving on to the regional effects. So we also see these effects in pretty similar effects in magnitude for the downwind neighboring counties. And then reassuringly for the other neighboring counties, this is like the non-downwind, we don't see significant or much smaller in magnitude effects for these areas. Okay, here's a table form just in case you want to see it. And here are the degree day results that I mentioned. Okay, then we do a lot of robustness checks. Some things I won't go into these, but I'll just highlight, like we control for things like the dust bowl intensity in the 30s and irrigation, which may be a potential concern in later decades, and repeat for longer time periods, et cetera, et cetera. Okay, so now moving on to the economic or the agricultural effects. This is first looking at corn yields. Again, the same sort of coefficient plot. So for the shelter belt areas, we see about like a 20 or so % increase in yields. And then for the downwind neighboring areas, which are particularly interesting because there's no trees there. So none of the like very local effects of like the dust or soil erosion are relevant here. We see about an 11% increase in yield. And so to put this into context, these are large numbers, but I just want to point out that over this whole time period between the 30s and the 60s, yields in this area actually increased by more than 100%. So this is large, but perhaps not like, you know, unbelievably large. Great question. So thank you. So I'll talk, hold on to that just for 1 minute. So then we do some robustness checks again. And then next we think about, is there evidence of farmer adaptation to these, to these more favorable climate conditions, focusing on the downwind counties where again, the very local effects of the shelter belt are not there. And so we see an increase in corn area, which is evidence that, you know, people are planting more corn also, and then a reallocation from pasture to cropland, as well as from wheat, which is less water intensive, to corn, which is more. Here are that's just, you know, so increase in cropland, decrease in pasture land in the downwind neighboring counties, and then an increase in corn, a decrease in wheat. And so then on your question, Anna, about the decomposition of the yield increase. So we do exactly what you were suggesting. So we take the Schlenker and Roberts model of like just using our coefficients from the first part of the study on the climate effects, and then see how much would have yields increased. And we find that on average, our results, or those the predicted results that way, are about half of what we find. So again, that's roughly that seems roughly consistent. And then also, actually, there's reasons to believe that. So those increases are sort of the physiological or the economical effects of only the climate change. And then there's reasons to believe our results are taking into account also adaptation and other potentially other effects that are not climate effects. And so it makes sense that adaptation and these other effects could account for up to half of the total yield increase. Great. Okay, so with that, I'll just oh yes, question. Yes, that's true. Yeah, we would definitely like to do more on that. If I'll have to go back to, we've been meaning to go back to like the censuses, the 5-year agricultural censuses, to see what sort of data is available there. But I agree that would be very interesting.
These are districts.
Counties.
Is there any evidence in the model that the places that actually have the trees within county effect, that would be advantageous for today.
Yeah.
Otherwise, it's surprising that quite similar down in. You think that'd be much more
Local. Yeah. So I think, so a couple of things on that. So on the climate side, we have actually done a version of the analysis at like this hyper local level, looking at the weather station level, basically how like just what area of trees were planted near a weather station. And so there we do see this, I mean, the coefficient, the magnitudes here are not comparable because this is now an area, but we do see generally the same direction of results. So this is reassuring. Although, of course, if we do see like the large spillover effects, we expect these like very local results to be a bit tempered by that. I do think it would be like I'll have to think about if we can do more on the like the yield and the economic side like, at that very local level, just because of the time period. But that's it. Yeah. Thank you. Yes. Oh, yeah. Yes. Thank you. Yeah. Okay, so just to wrap up, yes, so we investigated the local and regional climate effects of this large tree planting programs. We see impacts on climate as well as yields, and find some evidence of adaptation through land use and crop choice. And so Jen, just something, again, going back to, are these effects realistic? I want to note that this is like looking at the evapotranspiration part of the story, not necessarily the whole parts of all of the water cycle, although we're thinking about how to extend it to that. But Jen, we do some back of the envelope calculations, just kind of multiplying our coefficient by the area of trees planted, and then converting that to like how many gallons of water extra you see in these areas, and then compare that to some science literature on the theoretical transpiration rate of oak trees. And actually this ends up being, well, and then we multiply that by like the number of trees, and then going back to the survival rate, and actually this ends up being remarkably similar. So this is, again, very simple back of the envelope calculation, but reassuring that the effects are not unbelievably large. Okay, and then so I just want to, I know I don't have much time, but then just kind of coming back to this idea of what can we say from this project about this current tree planting mania. I think our project shows that tree planting can be a tool both for climate mitigation, but also and for climate adaptation by reducing the negative impacts of warming on agriculture. But then again, want to return to the fact that there was a very careful design of this afforestation program, and a lot of careful attention and planning was paid to the type of species that were planted, this may not be the case for some of the more monoculture tree planting programs today. But otherwise, the places where a lot of these tree planting programs are taking place today are still highly dependent on agriculture and also have some similarities in terms of like the soils and the economic situations. And so we do think that the takeaways from this project could be applicable to these modern programs. Yes.
Are you able to detect survival of trees by species, whether it was native or foreign, to just kind of emphasize your final point on how it does matter what sort of trees and species are?
Oh, I love that idea. Thank you. Yeah. So there's like this table actually showing something like that, like the survival based on, and yeah, we could definitely go into which of these are more local and less local. Yeah. 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 Thank you. Yeah, that's a great idea. Awesome. That's it. Thank you so much.
Okay, thanks everyone for coming back. So we'll start with our second round of presentations today. I do ask you to please remember these are 15-minute presentations, so no questions allowed unless the speaker explicitly asks for them. And if there's a minute or two at the end, then we'll take questions. So Jonathan.
Thank you very much. Well, thank you for having us on the program, and to the IGC as well, who sponsored this project and gave us some funding, which is greatly appreciated. I'm Jonathan Colmer. I'm an assistant professor at the University of Virginia and director of the Environmental Inequality Lab. And this is joint work with David Lagakos at Boston University and Martin Shu at CUHK in Shenzhen. And so this paper is sort of unapologetically macro in content. It's a sort of the macro development tradition, in which case, you know, everyone is asking this sort of single question: why are some countries rich and some countries poor, right? And we're not going to answer that question today. You're all still in the job. It's okay, you don't have to worry about that. But that's sort of the ultimate goal, right, of the macro development sort of space. Everyone's working on this single project or single big project. And so within this sort of space, you know, there's been an increasing emphasis on trying to understand the extent to which certain sectors may be important in shaping sort of productivity differences across countries. And so we are going to focus on the electricity. And there's good reasons to think that the electricity sector might be quite important in shaping patterns of development. If my micro papers had relationships this strong, I would be very happy. This is GDP per capita on the x-axis with electricity consumption per capita on the y-axis, and there is a very strong and very tight correlation, right? And so sort of two possible interpretations, right? One is that you need access to electricity to be able to engage productively in economic activity, that lack of access to electricity is a fundamental constraint to development. Alternatively, it could simply be the case that as you develop, demand for electricity also increases. And that if we had opera tickets per capita, we might see an equally strong or maybe even stronger relationship here as well. And so this is sort of the starting point that we have. We have this very strong relationship. I'm a big fan of, if you see it in the raw data, then that sort of suggests this might be important. And so we wanted to sort of set out with trying to understand this sort of question. Does electricity, is it an important sector in shaping these patterns? And so specifically, we're going to ask the question, is the electricity sector a weak link in the development process? And weak link is the idea that when productivity increases in the sector, it has a bigger than aggregate effect implied by the sector's share in the economy. And so this has sort of been an idea within growth and development for a long time, dating back to Hirschman and before. You know, Michael Kramer's O-ring theory of development, you may be familiar with, discusses the idea that the electricity sector may be a bottleneck to the process of development. Jones, in his 2011 AER paper, also discusses the role that the electricity sector may play as a bottleneck in the development process. And of course, there's a voluminous literature, pun fully intended, using night lights to think about patterns of economic development as well. And so we can draw on that to think about the potential. And, you know, there's good reason for this. Electricity seems like a prime candidate for a weak link. There's very low substitutability with other inputs, right? And so it's hard to sort of use a machine absent electricity. All modern production techniques require electricity, and it's frequently ranked as a key barrier to growth by firm managers.
And so we're going to set out to try and answer this. And the way that we do this, there's sort of several parts of the paper. I'm going to focus just on the kind of key facts today. We start by constructing a new cross-country database of electricity inputs and outputs, which I'll tell you about. We then document that electricity productivity is actually only slightly lower in poor countries. There's actually substantially more variation in TFP in other sectors like agriculture and manufacturing and even aggregate TFP. And so there's actually, it's the case that the low-income countries, developing countries are actually pretty good at producing electricity. There are more fundamental issues of how much electricity is produced. But in terms of the productivity of electricity, there's actually only slightly lower in poor countries. We then sort of reconcile the facts by building a multi-sector model to sort of think about this weak links question by studying the aggregate effects of improving electricity. And sort of the core features of this model are that, we model it as electricity not being very substitutable with other inputs, as mentioned. And we're going to also think about distortions in poor countries that raise electricity costs. And we're going to use that to sort of then engage with this idea of weak links and test the weak links hypothesis. And sort of the analytical result that we get from this model, which builds on the work by Bakai and Fahy and others, is that the long run gains from improving electricity productivity depend on how productive the electricity sector is to begin with. So if you have a very low productivity in the electricity sector, then in the long run, if you increase productivity, capital can be reallocated to other sectors of the economy, and that can actually allow you to have a lot of growth. But if you're already very productive, then there's not a lot of, there's already a lot of capital in other sectors, and there's not as much scope for reallocation. And then what we do is calibrate the model, with the data that we've produced, and as I said, we show that under sort of the main set of results that electricity is not a weak link. And I'll come back at the end just to sort of discuss where there is scope to think about electricity as a weak link, but it sort of comes out of what we would think of as the standard, that side of what we think of as the standard macro ways of writing these models down. So in terms of measurement, this just sort of to give you a broad sense of the way that we've been thinking about this and the data that we've been collecting. So in terms of thinking about the definition of electricity, the electricity sector, we're going to think about production, transmission and distribution, and self-production as well. We obviously want to account for this left tail of generators and other considerations, which might be especially important in developing countries. And the most broad of production functions, therefore, we're going to say that electricity output is going to be a function of capital, sort of the machines, the generators that you're producing, the workers in the employment in the electricity sector, and then the fuels you use to produce that, so natural gas, etc. And one of the really sort of nice things about measuring electricity, as opposed to, say, other sectors that have been studied, such as manufacturing or agriculture, is that electricity output is this physical quantity. It's a homogeneous quantity. A kilowatt hour in Ghana is a kilowatt hour in the United States. And so we don't have as much of the measurement error concerns that have sort of like the productivity literature in, say, manufacturing or agriculture. And so that's one of the things that we quite like about studying in this context. In terms of output, we obviously want to include all of the electricity that is produced and distributed, as well as I mentioned, any of the self-generated electricity that is produced from generators. And so what we're going to be measuring is sort of this total electricity production in megawatt hours from the IEA. We're going to account for distribution losses as a fraction of total production. And then we're also going to be using sort of imputed own produced electricity from generators. And I'll talk a little bit about how we do that in a moment. So that's going to capture our sort of output side of things. In terms of capital in the electricity sector is going to be this function of both sort of electric power plants and sort of the transmission and distribution network as well. We want to account for that. And here we sort of are going to basically capture in that, there's the amounts that you can sort of produce is going to be restricted in some way by the amount of distribution capital. Yes.
Yeah, you mentioned I think there's an output. I tend to think of it as input. Not in my work. I work on production, but more generally for those. So should we think of the TFP result that you mentioned as are they efficient at producing electricity, or can they use that as
Okay, so yeah, we're going to I'm going to actually hold off on that, and we'll come back to it shortly. But we'll get to the facts first. So in terms of capital, so I say that we have the generation capital and the distribution capital. But sort of to your point, Mar, we're thinking about sort of not just, in the power plant, how much it's being produced, but also we want to make sure about, how much it's being distributed to be used productively. And so we're going to be, capital here is going to be in megawatts. And so we're going to be summing up the universe of large and medium scale electric power plants from the Platts World Electric Power Plant database. And then we're going to come up with our best efforts to try and capture this sort of left tail of electricity generation, which sort of inspired by the work that Casselli and Wilson have done. We're using imports data on generators. So the idea here is that, Ghana probably doesn't have much in terms of production of generators. They're probably importing generators mostly from China and other places. And so we're going to be using detailed import data on values and quantities to try and get sort of an imputed sense of what that left tail is in terms of the amount of capacity from those generators. And then we use that to impute output for those sectors as well. And then we have information on the amount of distribution capital from power lines and distribution.
Measuring in any way the reliability of electricity supply, because I think that's a big concern in developing countries.
Yes.
What is the total number?
So reliability obviously is very, very important. We are thinking about transmission losses, as mentioned on the previous slide. And I'll come back to discussing more the implications of thinking about reliability towards the end. But the idea of thinking about, self-generation as a way of ensuring against reliability issues, but we'll come to that sort of after the model. The weak link here, if we think about sort of the traditional approach, one would tend to think about the role that sectors play in terms of aggregate production, in terms of what their DOMAR weights are, following Holton and Solo and those sort of areas. So this is the idea that your share of sales over GDP is usually a good first order approximation for what your contribution to aggregate production would be. A weak link would be that your DOMAR weight, or your share of GDP, has a bigger than a much larger effect, a multiplier. It's not really. So it's the O-ring is sort of thinking about it in that way. It's not just the O-ring, but like the weak link stuff of Jones and others. It's the way that sort of Bakai and Fahy and others think about weak links formally is that you have a bigger than contribution than your share of the economy. This is capital, and then in terms of other inputs, thank you. We have total electricity employment from industrial censuses. We have fuel information from the IEA. And then this third bullet point, thoughts and prayers go out to the RAs that did this, but they basically scraped detailed company records. We found they went through the annual reports for 69 private producers in 31 countries over these multi-hundred page reports to draw information about the value added and the employments, to try and get factor shares, effectively labor shares within those sectors for 31 countries. And the final database covers about 131 countries. So I'm running slow on time now. So just to sort of give you the cross-country patterns. So the first sort of fact we have is that output per worker is a lot lower in poor countries. And so as a first sort of shot, this sort of suggests that, maybe there's a bit of a puzzle here. Maybe it's the case that, the amount of electricity productivity defined in this sort of standard first approach suggests that poor countries are not particularly good at producing that. There's less variation here than in terms of output per worker in aggregate, but there is a lot of variation still to speak of. Now, when we go to capital, we actually find a very different pattern. So there's actually very little capital output per unit of capital. And what this is really capturing is a utilization approach, right? We have megawatt hours divided by megawatts. And so this is really hours, right? And so what this is saying is that in poor countries or rich countries, utilization of the capital is not really the problem. Right? Similarly, with fuel, we find a similar pattern, very little variation here across. And so the question then becomes, well, we have these sort of low sort of dispersion in capital productivity. We have a reasonable amount of dispersion in labor productivity. Ultimately, it comes down to sort of, well, how important is labor? And as might be your pride, we find that labor is actually relatively not important when it comes to producing electricity. You have your machine, you have someone turn it on, and the electricity comes out. Just to, be reductionist about it. And so this was the result of those of scraping those annual reports. This is sort of the labour share in the electricity sector compared to the labour share in aggregate, and it's much lower here in terms of and constant throughout the income distribution, which will be helpful in terms of our modelling assumptions. So we need to measure TFP, and the way that we do this is sort of we take the generalized production function is going to be output, it's going to be a function of capital, employment, and fuels. We're going to assume that the production function is constant return to scale based on sort of a standard macro replication argument. For the IO economists, please don't freak out about this. We can think about sort of diminishing marginal returns, but the basic idea here is that, you know, if you think of in the US, Arizona has its market, Boston has its market. Arizona isn't producing electricity and sending it to Boston. And so as you replicate, I can get into a sort of constant returns to scale at the aggregate level. But we can sort of relax this assumption. We're going to use constant labour share, or we're going to assume quadrilateral between labour and this sort of nested function between capital and fuels based on this constant labour share. And then, given the low substitutability between capital and fuels, we're going to assume this sort of style production function within between capital. And when we sort of calibrate this, we get, again, very low dispersion in TFP for electricity. Sort of the bottom quartile of the distribution is about 90% as productive as the top quartile. If we look at aggregate TFP, it's actually the case that sort of the bottom quartile is about 60% as productive as the top quartile. So there's much less variation in TFP in the electricity sector than there is in other. So we reconcile these facts through the lens of a model, and I have less than 1 minute left, so I'm not going to tell you about that. But the basic idea in the model is to reconcile these facts. We calibrate the model, it matches data pretty well, including untargeted moments. From this, what we find is that actually, you know, the electricity sector in terms of its contribution is actually far less than would be implied by the Hopkins approximation. We actually find that it's not much of a weak link in sort of standard calibration. Now, what's I think interesting here is that this is basically saying, you know, if you have a country that's really good at making left shoes, and you make it a bit better at making left shoes, that doesn't help if it's not very good at making right shoes. And so relative to other sectors like agriculture and productivity, there are probably more gains to improving productivity in those sectors than electricity. Reliability is obviously something that we're concerned about here. And so the model that you'd have to have in your mind, like the distortions that we have in this model are sort of standard Shane-Plano-esque macro distortions, right? They're competitive distortions, right? So what we're saying here is that there is a price that you can get electricity for. It's just more expensive. And so you should have, like the model we're using in our baseline is a sort of Alcott style model, right? You know, where you get a blackout, but you have a generator, it's 5 times more expensive, but you can get access to electricity at some cost. We can get a weak link result if we assume that there is no price that you can get electricity for. If, you know, firms are basically optimizing, and then every day Lucy moves the football, right? You go to kick it, and 50% of your electricity is not turning up day after day after day. Firms aren't learning. But this is sort of like not a competitive distortion. This is sort of one where some Calvo fairy is tapping you on the shoulder and saying, you're insured, you're not insured. And it's sort of, that's the puzzle. And so that's the sort of, if anything, the sort of street light that we're sort of shining in a macro sense for more micro work. To the extent that you don't believe the results and you think that electricity is a weak link, the puzzle really is, what are the barriers to self-generation? What are the barriers to insurance? And that's where reliability is very important. So thank you very much.
Hi everyone, my name is Mirabelle. I'm at Imperial College, and I'm presenting work that's joined with Felix, Shefali, and Ralph. And I've put nice logos below. This is work that's been funded by two research councils in the UK, EPSRC through the IDOS program and ESRC through PRITS. And the paper I'm presenting is called Waiting for Carbon Reductions, a Smart IV Approach. So this is very much work in progress. That won't click. There. So given I have 15 minutes, I'm just going to give you a summary of what I'm going to tell you. So what we do in this paper and this project is we find a new way to use information from smart meters data, such as to create an instrument for electricity demand. And this allows us to estimate the marginal carbon intensity of an electricity generation system. By doing this estimation, it means we can measure better the benefits from short-term shifting of demand from one half hour in our case to another, but we could use it in other ways. And these are very preliminary results again, and they show that by doing this, we can show potentially larger benefits from shifting demand. So that's in a nutshell what I'm going to be saying. But let me step back a bit and tell you why it's interesting and important to do this. So the UK electricity system, but it's true in other parts of the world, has been very radically transformed in the past 15 years. Mainly driven by coal phase out and phase in of renewables. So what you see on the left-hand side is the carbon intensity of the grid between 2009 and 2022 or 3. And we see it's going down. On the right-hand side, you see that this is driven in the UK by, in pink, the percentage of coal in the generation mix, and in blue, the percentage of renewables in the generation mix. While this is a remarkable transformation, there are still issues with such a pattern of a grid. And one of them is that renewables are intermittent. And this means that the moment when electricity is going to be consumed is actually going to determine how carbon intensive your grid is. If we are thinking of a transition to a zero carbon grid in the next few decades, this change in content throughout the day means that there are potential gains from choosing when and how when to consume electricity. And so with this problem and cost optimization is added the fact that we're looking at electrifying our economies in as much as possible. And therefore that we want to be using both supply side and demand side to make sure that this optimization and that's the load is balanced in a most carbon neutral way possible. So understanding how to do load balancing is important. And as I just said, it's not only that we want to reduce carbon of on the grid, but also reduce the cost of making supply and demand meet. So by doing it on the demand side, it means one, convincing users to change when they consume or automating when they consume energy, and to know how to make these changes in the flexibility of demand. There are several questions that we need to answer. So in another project, which we'll tell you about next year, we're looking at how users respond to different incentives you can give them to be flexible in when they are going to consume electricity. In this project, we are trying to take a more systemic view of how will the electricity system respond to these changes in the time of electricity consumption. So, and we are not at all the first people to be asking this. So not only in engineering research on devices and technologies to allow flexibility and to make the grid absorb such flexibility, but also on the market, a lot of firms, electricity providers, and other new entrants are exploring these potential markets. So, for example, you can have a flexible tariff. So, Octopus is a big player in the UK on that, but you can also have firms that make agreements with their energy providers to be more responsive. You can have, there's a dam there up there, so there are some reserves and batteries firms, etc. So it's going to be a very complex and sophisticated market that we can see emerging, and therefore understanding the actual carbon content at different points in time during the day has value, and we want to explore. What this paper does is to understand how we can measure that. So the very simple way to measure the carbon content is to take an average over time. And this is can be a very naive way, because I'll try to give an example so you understand why, and let's see if I achieve that. So imagine this half hour, 100% of the grid is powered by burning gas. And next half hour, half of it will be renewable because the sun rises. So you could think, great, let's just move my consumption now to the next half hour, and its carbon content will be lower. However, this movement will only have that change if the demand next half hour allows for my extra demand to be moved to the point where the sun is shining. And so to estimate this marginal carbon of my demand, I need to take into account both the supply, so is there sun or not, and demand, how much are other people asking, consuming. And so the state of the art now that has been being used in the literature is to regress the carbon content of the grid as a whole at a certain point in time on quantity, and to measure this marginal emissions. So the problem with doing it that way is in the current state of the grid becoming more difficult for two reasons. So first is that weather is going to be affecting both supply and demand of electricity. So supply, as I just said, if wind and sun is going to affect supply, but at the same time, demand, because my demand for heat or cooling or movement or going out, etc., will be also affected by weather. And so in these estimations, weather is affecting both supply and demand and needs to be taken into account. In addition, there are more and more demand side response products being offered, so that the consumers can be actually already incentivized about when to consume and when they are demanding electricity. And therefore, in our estimation, this also can create problems. So what we do is that we are going to add weather controls in estimating the marginal carbon, but also we are going to use smart meter data from a large sample of households, things, to instrument the quantity consumed at each moment in time. So the data we are using for this comes from various sources. First, we get the grid level emissions data at the half-hourly point, and this is based on power plants output and is available for good period of time. Second, we use weather data. So we use hourly data from 1950 to now for the Era 5 land data set. And then we have access to smart meter data for a specific sample of customers. There's about 1,000 Octopus Energy customers for which we have smart meter data between 2018 and 2020. What's very useful about these customers is that they are not on a flexible tariff. So their demand is not going to be affected by different prices throughout the day. What's also interesting here to see is that the moments in the day where they are demanding electricity is not very uniform throughout the UK. So that's something we allows us to exploit this variation. So the colors you are seeing there show you how the demand is varying compared to the average electricity per half hour. So in detail, the way we specify our estimation is, so we include these period fixed effects that are the key of what is being estimated. We show that we use a nonlinear specification. So it could be that more quantity consumed changes the marginal emissions. We use log terms and we interact weather controls with quantity. As weather controls, we use temperature, wind speed, and solar radiation. And we estimate this for every 2-year window in the data. So that's how we include weather. And then we also instrument quantity consumed by household-specific regressions on these different weather variables, and these moments across households become our instruments for quantity. So once we have all these estimated, we're still actually, this is a good test. We're trying to think on how to best present what we find. So we do an experiment where we take 1 megawatt in a given 30-minute period T, and we measure how much we would be reducing emissions if we delayed the consumption of this by up to 3 hours. And we then look at which percentage the emission reduction potential per half hour in a year. And what this graph shows you is that, say, here in 25% of the hours of the half hours of the year, we could have reduced carbon emissions by 10% by moving our megawatt by 30 minutes. Our 30 minutes to the next 3 hours. Then we use the estimations I showed you, and we find that there's a big difference between the naive case of taking the average and the marginal. And then we add weather controls and smart IVs. And we find that in 50%, so here it looks a bit narrow, but these are the 2 years for which we have our smart meter data. But we find that in 50% of the hours of these years, we could have decreased emissions, the carbon content of our electricity consumption by up to 30% by moving energy demand from 1/2 hour to later. So to conclude, the power in the UK, the grid has been dramatically cleaned up, but this shifts not only the average emissions, but also marginal emissions. And so there are biases that arise in estimating these. So we can improve this estimation. And while it seems a bit nitty-gritty estimation, it has actually big impacts in understanding how investment choices are made into the clean grid and in designing markets for these demand response incentives, etc. So thank you very much.
Okay, hi everyone. I'm Milan Quentel from UPF in Barcelona. This research project is titled Gone with the Wind: Renewable Energy Infrastructure, Welfare and Redistribution. The motivation for this project is that to achieve net zero emissions by 2050, countries are looking at a rapid expansion of renewable energy. This project, I'm studying wind energy in Germany. Wind energy in Germany is already the largest source of electricity, and yet the government has mandated that we have to double the capacity within the next 7 years to be on track with those emission goals. And that would increase that the annual capacity growth that we currently have has to increase by factor 5. Or put in other words, if nothing changes, we miss the new installation target by 80%. And so the key challenge that we have here is that residents dislike wind turbines. Modern wind turbines are approximately 150 meters high. That's higher than London Eye, for example, if you want some comparison. And so there's very little local incentive to build wind turbines for residents, for local policymakers, and in the end, developers struggle to find land. And this is particularly challenging in Germany, but there's anecdotal and systematic evidence that this happens in the US, it happens in the UK and France, and in many other advanced economies. And so what I'm doing here is I'm studying turbine development and its welfare costs for residents. And I'm trying to use that to understand, given a certain capacity goal, where should we build wind turbines to minimize the cost? And can we design a set of transfers that compensates losing regions so that there is larger incentive to build turbines? And what I'm doing here is I have this 3-point strategy. The first thing I'm doing is I'm estimating the reduced form effects of wind turbine development on surrounding neighborhoods. I have very disaggregated spatial data and a novel ID strategy to do that. Then I'm going to embed those reduced form estimates with theory to infer the implicit amenity loss in terms of willingness to pay. How much would you be willing to pay if I don't put the wind turbine there? Then I'm going to embed that amenity loss in a quantitative spatial general equilibrium model with the idea of what happens if we allow residents to adapt by moving away through residential sorting? What are the welfare effects? How should we think about transfers and future wind turbine development? And so what I'm doing is wind turbines with very local effects, right? And so I'm also using very localized data. I'm going to divide Germany into 1 by 1 kilometer neighborhoods. And for each of those 1 by 1 kilometer neighborhoods, I'm going to collect wind turbine development data. I'm going to collect data on house prices. And I'm going to collect data on population, employment, and workplace wages. And on the right, you see a map of Germany, and every little small blue dot is a 1 by 1 kilometer neighborhood in my sample. And the first thing that you can already see from this is that the population density is pretty high. There are not so many regions where there's no population. And when you look at the distribution of wind turbines relative to that, I mean, you would have to zoom in, but you can already see that they're pretty close to the population. In fact, 96% of wind turbines are within 2 kilometers of residential population in this context. Okay, so with this, one could already try to understand the effects of wind turbine development. The problem is that policymakers might choose places where they expect growth in electricity demand, for example, to put wind turbines, or there might be other unobserved trends. From having this IV strategy, where I drew this in paint, but I hope it helps to get the intuition across. Suppose you have two villages, village A and village B. They're separated by a hill. And the wind is flowing from west to east in this example. And just by that terrain pattern, you get the following wind speed pattern across heights. The wind is coming from the west at very strong wind speeds. Then it is blocked by the hill at lower heights. And this leads to a higher vertical increase in wind power density in village B than in village A. And now I'm going to exploit that the size of turbines has increased dramatically over the last 20 years. So in 2000, the average wind turbine was 70 meters high. 2017, the average wind turbine was 127 meters. And so that over time, there is a larger incentive to put wind turbines in village B relative to village A. And then this is the estimation strategy. So I'm going to focus on the long run effects of turbine construction. Why? Well, it takes time to adapt. People move away only after a certain number of years. And so I'm taking the long run effect between 2017, the end of my sample period, and 2000, the start of my sample period. This is in changes so that all of the time invariant characteristics are already taken out. And I'm also going to control for a number of geographic characteristics that may affect wind speeds and so on, and for some socioeconomic characteristics at baseline, and for district fixed effects. So that in the end, the identifying variation is really village A versus village B within the same district, relatively close to each other, holding constant their geography and socioeconomic characteristics. And the so geography, I should say that's altitude, terrain, ruggedness, land use, slope. Socioeconomic characteristics are population density, per capita income, the share of high-skilled residents. And so these are the results that I'm getting. This is a large table. Let me walk you through it systematically. There are two panels. Panel A shows the intention to treat estimates. Panel B shows the IV estimates, okay? And each column is showing a different dependent variable. Column 1 is first of all showing the first stage. So the instruments that I'm using here is this wind power density change that I told you about due to the technology. And I'm also going to interact that with the share of land that is available for wind turbines within 3 kilometers. The intuition for that is you can see wind power density matters for turbine placement, but of course only in the neighborhoods where you can actually build wind turbines. Whenever there's a conservation area and you're not allowed to build wind turbines, there's no effect. And we see, sorry, say again? That's the baseline measure. Yeah. And so we see that for wind turbines in the first stage, and we also see the same pattern across the whole reduced form. And that's an indication that this strategy is working as proposed. It's working through the channel of where can we build wind turbines. And the results that I find, first of all, now I'm going to focus on the IV because these are the things that we can interpret in magnitudes, is for each additional wind turbine, house prices decrease by 2.1%. Right? This is something that is known in the literature. But we also find that residents move away. And in particular, I should say high-skilled residents move away, while low-skilled residents stay. It's something that is theoretically expected. Whenever a neighborhood gets less nice, there's residential sorting, right? But then this also spills over to the labor market. So this is employment measured at that place. And here I find that high-skilled employment decreases, and to a smaller degree, also low-skilled employment decreases, which points to positive, either complementarity between the two types or positive externalities from high-skilled onto low-skilled workers. And this is consistent with a negative labor supply shock story, because in the end, what I find on wages is that those wages are increasing. Yes.
So is it what actually work, or is it the residents of those workers or the place of work?
Yeah, so the resident columns are really where people live, and the employment columns are really where people work. How many people are registered to work in this building?
The difference in number of observations due to the fact that there's not that many people who work in places which are like that.
Exactly. So yes, and employment is much more concentrated across faith than population. Yes.
Why the number of observations changed so much?
Yeah. So first of all, there are many more unskilled people than high-skilled people. This is why this drops here. Okay. Between residents and workplaces, it drops because workplace employment is much more concentrated spatially than residents. Yeah, a lot of them. 80% of people, 70%. Okay, I have to speed up a little bit. So from these results, we can already see that wind turbine development has negative side effects on surrounding communities. But if we want to evaluate that, we need some welfare measure. We need to understand how much the utility of a resident there is affected. So what I'm doing here is I'm using this revealed preference argument that is embedded in the Rosen-Roback framework, and that is more recently used by a lot of quantitative spatial models, such as the Alfred et al. Berlin wallpaper. And the intuition there is, in a place where you see many residents, but also high house prices and low wages, it means that there must be high implicit amenities, right? So I live in Barcelona, for example. Housing prices are ever increasing, wages are super low, still people live like the place where maybe the beach is good for something. That's the idea. And this gives me a model consistent mapping from the reduced form estimates that I showed to you onto amenities. And there are some things that I have to parameterize, which is kappa, which are migration costs, and alpha, which is the share spent on housing, which I parameterize from the data and from the literature. And when I do that, I find that for each wind turbine, amenities decrease by 3.5% for high skilled and 1.0% for low skilled. And then the idea is to take those two numbers and embed them in a quantitative spatial general equilibrium model. Okay, this model is a bit bigger, but this will be the shortest summary you've ever seen in 2 bullet points. Essentially, the key trade-off is we've seen in the data that people move away. Moving away means adaptation. How much people can adapt and want to adapt is first of all driven by how much do they dislike wind turbines. And then on the other hand, how large are the moving costs, how congested are housing markets, and how downward sloping is labor demand. This is why I need the model. I estimate that model for those 130,000 locations in Germany. And then the main counterfactual is going to be comparing the equilibrium with wind turbines to the equilibrium without wind turbines and see what changes. Okay, so this is the first application of the model. This is showing you how much the average quality of life changes in percent across Germany. And the first thing that you can see is it's all over the place, right? So this is not that one region is particularly harshly hit. And this is also a reason why we need that fine data. There are some neighborhoods that are hit and others that are not hit. And so when I show you the distribution of wind turbines, that maps to the distribution of red points here. These are the regions that lose. In a situation of high skilled, the quintile of strongest losers loses more than 4% of quality of life. In terms of the low skilled, it's a little bit lower. And so that's the first thing. This is interesting because from this, I can calculate the transfers that would make those regions, that would compensate those regions and incentivize wind turbine development in them. The other application that I can do with this, both of this is still work in progress. The other application is I can look at any allocation of wind turbines and try to understand what are the aggregate welfare costs from that. Okay, so here on the left, I'm showing you a scenario that is consistent with what the German government is planning currently. Government is not allocating the wind turbine itself, but it's setting targets for where to build them. And this is very, very balanced across space. And here's an alternative scenario that I provided that focuses much more on the wind energy regions in the north that are also lowly populated. And you can see that this right scenario, for example, has welfare losses that are 4 times lower than a spatially balanced scenario. Okay, instead of a conclusion, 2 broad contributions. Yesterday, we've talked about how we can make climate policies more incentive compatible, because we know that we need this popular vote to make climate policy happen. This paper takes one particular policy, discusses the redistributive effect, and looks at policy implications. And the other thing that's interesting, I think, here is that I'm looking at environmental disamenities through the lens of a quantitative model. So we've talked about water quality, air quality. It's great that residents can adapt, but we need these GE effects to see how sorting is affected. And that can have all sorts of repercussions for coming to the nuisance versus environmental discrimination. What are the segregation effects across a whole bunch of disamenities? Okay, that's it. Thank you.
Right, this work is joint with Shefali, who's here in the back today. We're thinking about phasing out coal from the electricity sector. Okay, so when it comes to mitigating climate change, economists have long called for carbon pricing as the first best policy. We've seen a really slow rollout of carbon pricing, and where we do see it, it has limited stringency. So the plot here from the World Bank shows that those regions and countries that do have carbon prices are generally lower than about $60 per ton of CO2. This is about a third of recent estimates of the actual current social cost of CO2. So the stringency we have with current carbon pricing is way too low to meet our carbon goals. If you include all policies, not just carbon pricing, but also the slew of second best policies and estimates of what might happen in the future, according to the IPCC, you might expect that those implemented through 2020 will lead to a 3-degree increase in warming by 2100. So we are not on track with the whole pot of all policies. Given this situation, we've become really interested in a particular form of second best policies, coal phase-out programs. So these are government-mandated scheduled retirements of coal-fired power plants from the electricity sector. They may be tied to the entry of new assets, such as nuclear, natural gas, or renewables. And they're often coupled with compensation for plant owners, coal miners, or other impacted communities. We've seen some of these programs already be completed in a few Canadian provinces. There's one that just started in Germany, and here I have plotted the schedule for Germany, just to give you an example of how this works. So Germany has a schedule in which it's laid out, okay, from now until 2038, we're going to have this maximum capacity of coal in our electricity sector, and we're going to follow that schedule to slowly phase it out. And there are discussions about similar programs being crafted for South Africa and Indonesia to help them meet their electricity sector decarbonization goals. So why are we so interested in this particular policy? Well, one, it has revealed political support. We've seen policymakers just do this when it's not clear that any academic has ever recommended this. We also see large potential for coal phase-out programs to not just reduce climate damages, but also damages from local air pollution. So we've known for a long time that coal-fired electricity is just really bad. Estimates from over 10 years ago in the US suggest that it has greater gross external damages than value added. And if you just look at the ratio of external damages to value added, considering only local air pollution damages, that ratio is 2. If you weave in climate damages, that ratio increases to 3. So arguably, if we have been, or if we had been pricing externalities properly in this sector, coal-fired power just wouldn't exist anyways. And finally, decarbonizing the electricity sector could be particularly important to accelerate climate mitigation, because it can help decarbonize all the other sectors that we have plans to electrify, such as transportation and buildings. So the big challenge with this type of program is that it's weird. One is essentially using an asset retirement program to address an externality problem, which is very far from first best. And there's no theory or guidance to policymakers on how they might want to go about this to do it well. However, we see really large potential for doing it well, because if you think about an optimal coal phase-out program compared to a naive one, the naive one might not take into consideration the dirtiness of plants, their closeness to population centers, and all those damages that we might care about. And if we think about, phasing out the dirty ones and those close to people earlier, we could potentially improve welfare compared to not doing that. There's a lot of associated academic work that kind of has been working in similar veins, looking at similar policies. Most closely related, there's a camp of empirical papers that estimate the value of eliminating coal globally, barriers to exit in the US market for coal-fired power plants, and estimated labor costs to the German CPO. But there's nothing that really kind of tackles the theory on the head and provides guidance to policymakers on how to do this well. So with this paper, we're asking, conditional on choosing to use an asset retirement program such as a CPO to address externalities, how does a policymaker craft an efficient program? And what we do to answer this is we create an analytical framework for designing an asset retirement program to maximize net benefits. Then we demonstrate how to use it by applying it to the state of New York in the US to explore gains. So here's our framework. We say in this setting, the regulator's problem is that they need to choose from a set of assets in a subset to retire in each period T before a deadline big T. And if they care about maximizing net benefits of this program, they will have the following objective function. They will choose a retirement schedule such that the sum of the individual net benefits of retiring each unit in each year is maximized, subject to any constraints that are important, such as a maximum retirement amount you could have in each period, which is particularly important for the electricity sector. And then also this deadline needs to be binding. This type of optimization problem is part of a class called generalized assignment problems. So thank you to the operations researchers who have identified this type of problem for us. The generic problem here is that you want to assign units to bins to maximize some value conditional on bin constraints. So think about, Amazon assigning stuff to boxes to ship in a least cost manner subject to box sizes or something like that. So this is the type of problem that we have at hand. Unfortunately, there's no general analytical solutions in large samples, so you need to use a solution method or algorithm to optimize these types of problems, which we do. We further define the net benefit of retiring a particular asset in a particular time period as the difference between the retirement benefits and retirement costs of doing so. Retirement costs are the foregone profit that the asset owner experiences from retiring it early compared to retiring it at that deadline year, minus any sell-off value that they would receive from being able to sell it off at that time. Retirement benefits are foregone externalities that are not placed on society as a burden because the asset was retired early. Okay, and so how do we apply this to New York? We first calculate the net benefits of retiring each coal unit in New York for each year from the period 2008 to 2017. Here I'm talking about a unit as a sub-plant unit that is separately retirable from an entire coal plant. And we use this time period because of the institutional particular facts in this setting. It allows us to kind of leave the baseline retirement alone because it was reasonably cost effective and done in a way that was efficient. We calculate retirement benefits from observed climate damages. We're really looking forward to including local damages, but we don't quite have that included yet. And we calculate retirement costs from foregone profit that is set aside from actual coal operations. So we use observed data on production and costs, as well as system wholesale prices, and say, all right, if this unit had retired early, this is how much it would not receive in profit it had done so. We then use a GAP algorithm to construct a retirement schedule that maximizes net benefits, subject to a reliability constraint. Then we look at production spillovers. So we model electricity production and wholesale price adjustments from coal retirement using a least cost dispatch model. That allows us to compute final outcomes that we care about, such as climate damages and complete producer surplus between the CPO and a baseline prediction from our production model. Okay. We use a variety of publicly available data sources for this from the US. Most importantly, our production model is estimated at the hourly level, so we have hourly data feeding into it. When we calculate these net benefits, we get results that look like this. So if you retire a coal unit in New York during this time period, the net benefits from that can be up to $50 million, 2010 USD. And those net benefits decline over time. So that says that, okay, it's more valuable to retire early than before that deadline period because it's basically a multiplier. There's some positive net benefit of retiring at the end, but the sooner you do it, you just have another year of value from that. All net benefits are positive. So this says that doing this is socially beneficial, and then we can take this and optimize to do it in the most beneficial way possible. When we construct an optimal retirement schedule from this, we find that over half of the sample is retired 5 years or more, like before its actual retirement date. So this does significantly advance retirement for coal units in New York. And total net benefits from this retirement scheme are on the order of $140 million. So when we then run our production model and say, okay, how does this retirement schedule impact the rest of the market so we can look at final outcomes? We see a 2.5% reduction in climate emissions, which has a value of $193 million. And that's just thinking about the case in which there's no entry. So the rest of the units in New York take over the production for retired coal units. We're also trying to think very hard about potential complementary policy that's needed to guide entry with this exit policy. So in that direction, we've also crafted a scenario in which we say, okay, there's a new natural gas combined cycle unit that is just magically immediately there and available to run instead of the coal unit that was just retired. If we say that, you know, there's basically natural gas that's entered immediately, we see a larger reduction in climate damages. So that says that, you know, new assets are cleaner than existing assets. So we can expect to see even more reductions from that. But we're currently working on crafting a scenario that uses some sort of limitation on the entry of natural gas, because I think in an ideal world, we don't want natural gas to just come in and replace our coal, right? So we're thinking about, you know, what's a closer to a zero carbon type entry scenario that would make sense for New York for this time to see the most gains possible we can from this program. So we also look at distributional impacts on the production side. So here I've plotted the change in coal unit producer surplus between the CPO and our baseline prediction for each year in the program. What we see is that in the early years, there are some positive values. So that says that if you own a coal plant and there's a coal phase out program going on and you aren't the first to retire, but you're the one that's going to retire a few years later, you receive some initial benefits because you take over production for the retired coal units. But then later everyone loses out, of course, because you're just forced to retire. Here's the same plot for owners of natural gas plants. And we see that they just simply gain from this program because they take over production for those retired coal units. And also they receive the benefit of higher wholesale prices. So when you force coal out of your supply curve, you then need to rely on higher cost assets. And that's what we see here. So those triangles indicate higher wholesale prices in each year of the program compared to baseline predictions in those dots. And this has implications for consumers as well, right? So electricity is just going to be more expensive if you just force out coal, rely on what you have left, and you don't have other lower cost assets coming online. Sure. No, these are just absolute values. I mean, I think we could ballpark a percentage from each year, right? So some of those look like 10%, some look more like 20–30% maybe. Yeah. Okay, so in conclusion, we develop a framework for using an asset retirement program to address externalities in a way that maximizes net benefits. We then apply this to crafting a coal phase-out program for the state of New York. We find that a CPO implemented from the years 2008 to 2017 would have accelerated retirement for over half of the units in New York for 5 or more years. Climate damages are reduced from this almost by definition, but they're reduced even more if we have new natural gas assets coming online to replace coal. But entry rules could still improve this even more if we start to think about things that would incentivize or zero carbon coming online, or maybe restrict natural gas. While coal owners lose out, those that take over production win, and wholesale prices of electricity increase, which has implications for both producers and consumers. And coming up, we are looking forward to incorporating local damage estimates into both our program design and in the outcomes that we estimate. Thank you. Oh, great question. I don't really have that off the top of my head, but I'm going to guess 5 to 10 years. So that gets down to some nitty gritty, like permitting stuff, I think, in the US setting. Yeah, I mean, so how I thought about this so far is that a coal phase out program probably would have a decent time of policymaking development. And in that time, entry would, other firms would be thinking about entry. And so there wouldn't be a huge lag, but at the same time, arguably there could be a lag for sure. I don't know how much time I have left for a question or two. Yeah.
So I suppose option value is a salient part of this problem because the planner made a decision to retire a plant as irreversible. The planner might worry that they might need the plant based on it, for example, or geopolitical flaw or something like that. Can you talk a little bit about how your optimization approach deals with option value in that?
That's a great question. So we've included a reliability constraint in our optimization. Ideally, that reliability constraint would allow for that type of shock by making sure there's enough of a capacity cushion that you could deal with whatever shock came at hand, which is the idea behind reliability standards in the first place.
If you maximize over expectations at time zero, then the plan is set for the rest of the period.
Yes, yes, we have talked about a shorter period perhaps and revising it midway, but we haven't done that version yet. Yeah.
Is the current government policy phasing out, is it just based on how old the coal plant is? Are there other considerations in deciding which gets phased out?
So New York doesn't have or didn't have a coal phase out program. We created a fictional one, and pre-existing retirement is based on market conditions. It reminded me of your question. So is
it in other phase out plans? Is it just the older plants get phased out first?
Not necessarily. It seems to be driven by a mix of concerns about reliability and then also just pure politics, like discussions with plant owners and how that kind of shakes out. There's weird stuff in the German program where there's like an auction that's being used to schedule retirement for half the fleet that we suspect creates some distortions that might actually lead to newer plants being retired first. So it's really just taking on a different form in each setting. Yeah. We've talked to those who are involved in the Ontario and Alberta systems. Haven't yet talked to anyone involved in the German system. Some interesting, thoughts that came out of that is that policymakers really wanted something that they could show had results at the end of the day. So like the carbon tax felt too mushy, but if they could say that they actually got rid of these coal plants, it would have a political advantage for them. And local air pollution benefits were a driver for some settings. They were just concerned about how kids were being affected by asthma, and so they said we're going to tackle coal. And so, yeah, given that type of stuff, we're thinking that, you know, other policymakers might have similar motivations to construct some of these programs. Okay.
Okay, so it's lunch now. There should be food outside, and we have about an hour 20, and we'll be back in this room at 1:30 for the master lecture. Thanks, everyone.
How are you?
So we're going to start this master lecture and policy session on renewables and climate change. And I wanted to begin by sort of mapping out what we want to focus on, which is basically this major problem of how you integrate renewables into energy generation and distribution, which is a global problem. And so I'm going to begin by introducing the policymakers down here. So we have Eric Asuman, who is the Acting Director General of the Ghana Meteorological Society. Raise his hand. And Sam Mugume next to him, who's the Assistant Commissioner for Statistics in the Ministry of Finance, Planning and Economic Development in Uganda, which, by the way, is my birthplace. But I think that the way we're going to do this, learning from the session yesterday that Oriana innovated on, is we're going to have the two other speakers. So there's Reguant, who I guess is Northwestern and UPF, or UPF and Northwestern. Yeah. And Steve Cicala, who's up here, is going to go first from Tufts University. So what's going to happen is Mar and Steve will talk for just around an hour, a little bit less, 50 minutes. And then we'll all sit down at the front. And what will then happen is that Eric and Sam will kind of reflect on the lecture, and then we'll open it up to the room to get a bunch of questions, because obviously the problem we're talking about is really everywhere, whether in the US, Europe, or whatever. And then at the end, I'll give time for Eric and Sam to kind of again reflect, and to Mar and Steve as well, and then we'll sort of wrap it up that way. Because I thought that worked well yesterday in terms of getting lots of questions into the room, and you guys are going to sleep and feeling you have to be on your toes to ask questions. I also asked Mar and Steve whether you would take questions during the lecture, and I'm happy to take questions if there's like some burning thing you want to ask. So without further ado, over to you, Steve.
All right, thank you very much for having me. As Robin said, the problem of integrating renewable sources of generation into the grid has a set of problems that are universal. Everyone is facing them around the world. But of course, everyone's grid is particular. Everyone's government and institutions and regulatory issues, all of these things can be particular, but there are some common themes that I'll try to highlight. My work has mostly focused on the United States. So I hope you'll bear with me the number of maps of the United States that we'll look at. Those are for illustration purposes, but for the content, hopefully we'll be talking about things that are not just US specific issues. And if you have questions about that, please ask. So my plan for today is mostly just to introduce MAR. So I'm going to give some background on the sector. There's a lot of history built into the problems that we're facing today. And so I'm going to give some background, some overview, some more general issues, and then hopefully set things up for more. That's going to start with how we got to the situation we're in. What exactly is the situation we're in? Where we need to go and why we can't get there. Okay, so starting with how it started and how it's going. I mean, it's really striking to think that I think for many people in the room, when their grandparents were born, or maybe their great-grandparents were born, they were born into a world that did not have electricity. And all of these things that we're dealing with now are within a couple of lifetimes. And many of the things that we're going to look at were built once and have been sitting there ever since. Right? So in 1918, they started just having relatively high voltage lines that could be transmitted across distances that were larger than 1 to 3 miles. In 1933, as the New Deal is really kicking in and electrification is a major priority of the Roosevelt government, you see that we have this sort of growth from the coasts, which is where people lived. Right? So you start with there being economies of scale of serving more dense populations. The grid starts there and starts to grow in towards the middle of the country. So that in 1936, finally, a UK map at least is up here in the top. You see how this grid growing from the coast is creating different synchronous grids. So we use an alternating current grid, which means that all of the machines, the generating machines on the East Coast, are pounding to the same beat at the same exact time. They're synchronous, and that beat is different from the beat, even though the frequency is the same as the West Coast. They don't talk to one another. Right now, if any of you have spent time in the United States, you know that Texas is a bit different. And so there are actually 3 grids in the United States. There's an Eastern grid, a Western grid, and a Texas grid, which is a strategy literally to keep the federal government out. That they said our grid doesn't cross state borders, therefore the federal government doesn't have jurisdiction. And so when you read about all of the problems with the Texas grid, why don't they have power? Why are they having these blackouts? All of these things, it's because they don't have transmission capacity from surrounding states. Okay. This is sort of a more recent characterization of the grid, where the garish colors are meant to not just make you recoil artistically, but also just as economists thinking about wanting to trade power across space, how fundamentally balkanized the grid is. Right? We have these local monopolists, so they're local utilities that historically have been vertically integrated. They've owned the generation, the transmission, and the distribution system. They have a captive set of customers, and their job is to serve their customers. The black line denotes the different grids that I was describing before. So those are the asynchronous grids. The red lines are sort of reliability regions that have some greater level of coordination. And then like all of these ridiculous shapes are utilities, right? These are utilities that are doing the exact same thing that their neighbor is doing, but for their own customers, right? And they would trade power across them the way that you would lend a neighbor a cup of sugar, right? You would level up at the end of the month. Their operations themselves are not really coordinated. So that really through the 2000s, 90% of the electricity generated in the United States was being consumed with both generated and consumed within the same borders, right? Very limited trade across these areas. Now, what I was just describing for these vertically integrated utilities, this is something that has changed starting in the late 1990s, so that we do now have wholesale electricity markets. The EU and UK also have these wholesale electricity markets, and the way they implement them is a little bit different with the exact pricing mechanisms, but the general idea is the same, which is that they predict what load is going to be. So some of the highest paid meteorologists in the world, their job is to predict what electricity consumption is going to be. And then given that predicted amount of electricity, they run an auction and power plants bid in and are called on to operate depending on whether their bids are economical or not. Now, some places have those markets. Many places are still doing the same thing that they were doing in 1936. right? They're operated, regulated the same way, nothing has changed at all. Okay, so in terms of where we are, these sort of different dynamics that I've described here, if you think about like, where is the energy coming from and where is the energy going to? We have largely a fossil-based electricity grid, but fossil resources are not evenly distributed, right? This is going to be true in the United States and anywhere else. And the way that the whole, not just the grid itself, but the energy delivery system is to take energy out of the ground, put it on a rail car to the population center, and then burn the fuel at a power plant close to the population center, at a power plant owned by the local utility that serves that population center. So essentially all of the energy transportation is occurring through rail lines and pipelines, right? About half of the coal in the United States comes from one county in Wyoming, right? 10 or 15 years ago, half of all rail traffic was just moving coal from mines to population centers. And the fact that we have this sort of regulated utility model meant that it's not that it was economical, but the utility companies could survive building a coal-fired power plant in Georgia, even though it's 1,000 miles from the closest mine, because they had captive customers who were, guaranteed to be buying from them at a price determined by the regulator, when it would have been much more economical to build massive generation resources close to the resources themselves and transmit it by wire. Right? So you can now move, and this is what China is largely doing, move, well, their latest is 12 gigawatts of power. So 12 nuclear power plants worth of energy. You can move that 2,000 kilometers with a 2% loss. It is amazing how efficient ultra high voltage direct current transmission is. Putting that same coal fuel on a rail car and moving it across the country is incredibly expensive. You more than double the price of coal going from Wyoming to Texas, for example. Right? And so it's just a very different way of organizing the energy transportation system. Okay, so in brief, the situation we have is that we're going to predict load and then determine which power plants we're going to turn on and off over the course of the day. There are enormous problems of misallocation here, both in where the power plants are built, because they're built far from the resources themselves, but also the utilities' incentives to build power plants, because the way the utilities are paid is based on passing through variable costs and then earning a rate of return on their capital stock. And so if you're a utility, you have the option to either buy power from your neighbor from a plant you don't own, and you will just pass that cost through one for one. Or if you own the power plant, you will make 10% per year on the value of that plant. So would you rather make 10% per year on a $100 million plant, or would you rather make 10% per year on a $1 billion power plant? Right. So this goes by a number of names: gold plating, padding the rate base, in general called the Avers-Johnson effect, that utilities tend to have this strong incentive to dump as much as the regulator will allow into their capital stock, because that is how they make money. Ishan, you had a question.
Oh, yeah, quick question. What is the
It's actually a different time scale. So they will do a day ahead prediction. For many of these markets, they'll run the market a day ahead. That becomes a financial obligation that you're either going to be long or short on. And then you sort of over time refine that so that it varies from market to market. Some will just have a day ahead and then a real time physical market. Yeah, and Mara has a number of things on that. Yeah.
This is only for vertically integrated.
So it's not. It's certainly true for generation for the vertically integrated utilities. The things that I've described for, in these places where they have wholesale electricity markets, some still remain vertically integrated. But even if they don't, and generation is competitive, privatized, distribution and transmission systems are universally rate regulated everywhere. Because you can imagine there are, economies of scale of having just a single distribution system. Okay. Other items to emphasize here are that what we're describing is, as people get up in the morning, electricity consumption increases. If it's hot, it increases even more. It decreases in the evening. And so demand is constantly fluctuating. And the system operator's job is to keep supply and demand in perfect balance so the frequency of the system is fixed. What that means is that you're going to be calling on different plants to operate over the course of the day. And you're going to have relatively high marginal cost plants called peaking plants that you use relatively rarely, right? So on a very hot day, there will be plants that you use 10 hours per day. And your installed capacity is going to generally, for reasons of regulation, you're going to have 10 or 20% more installed capacity than you're predicted to use in the course of a year. So you have vast amounts of capital sitting idle. It's sort of like as you walk in the streets and see all of these cars that no one is driving in because they're parked. Similarly, in the electricity system, we have just a lot of power plants that just aren't being used. That if there were better coordination across space, because you have these location-specific idiosyncratic shocks to demand, you could improve capacity usage. The other thing is this vast mispricing problem. Because you have demand constantly shifting and you're using different plants with different marginal costs, on the consumer side, you really only see, that the price of electricity is 12 cents a kilowatt hour, and that's fixed over time. It tends not to fluctuate over the course of the day. We call this real-time electricity pricing is very rarely implemented, right? And then last part was I was mentioning the transmission and distribution systems are rate regulated. These are also large fixed costs. Like if you look at the total cost of the electricity sector, very large share of that is a fixed cost. It's even more so as we transition to a renewable grid with essentially zero marginal cost and all of the investment is upfront. We overwhelmingly recover the revenues required for those investments with a volumetric rate. That means that the marginal cost of electricity may be 2 cents or 3 cents a kilowatt hour, but consumers are seeing prices of 12 cents, 25 cents a kilowatt hour in order to recover revenue to pay for the fixed costs, right? So that is a very large wedge between marginal cost and price. Okay, now how am I on time here? 10 minutes? Okay. In terms of misallocation, misallocation here is going to be coordinating the generation and consumption of power across space. So this is like a classic trade figure where the x-axis is the sum of production and consumption of a local region and a foreign region. The local region has a relatively high marginal cost curve, and they are consuming to here. Where if each of these regions produce in autarky, there's going to be this large gap between the marginal costs of generation between these two regions. It would be much more economical for the foreign region to expand their generation, the local region to reduce it, and ideally have this point of a single marginal cost and the law of one price prevailing here, right? You would have large allocated efficiency gains from coordinating across these areas. And you remember before what I was describing, this sort of balkanized region where everyone is doing their own thing. Well, aside from lack of coordination, the transmission system that we have has been endogenous to this regulatory structure and the way that we've organized this sector so that we generally, even if we wanted to, do not have the capacity to move power across space. And so you see these large gaps in marginal cost opening up even between areas that are near one another because of the capacity of transmission from point A to point B. Okay. So here, the price in Springfield is in the several hundreds. And on the other side of this bottleneck where there's wind power, the price is negative, right? Which means that the power plants there are being fined for generating. It's the system operator's way of saying, hold on, there's too much power in this place. We need someone to scale back. And the way we're going to do that is fine you for your production, right? We'll get to how common that is in a second. In terms of the mispricing part, if you think of the average retail price of electricity being about 12 cents a kilowatt hour in the United States, at least, you'll have the extent of volumetric mispricing being on the order of the average cost in general. And ironically, you'll have it in the places that care the most about doing something about climate change. I mean, California is an enormous outlier here. For the amount of fixed charges, environmental charges, but also the transmission system, that they recover the costs of by increasing the price of electricity. And this is going to get to the part of where we're going of the price of electricity is central for the extent of electrification that we're going to have. People are going to be deciding between having a gas boiler for heat and hot water at home. They're going to decide between an internal combustion engine and an electric vehicle at home. And when they're making that decision, they are comparing the cost of, filling up the battery with electric or heating their house with electric and the cost for oil and gas. And if you are recovering all of these fixed costs with variable pricing, you are distorting people's decisions away from electrification. So that's why I sort of put up at the first order problems of misallocation. Mispricing is also an important problem because that is going to help determine the extent to which we're going to electrify the economy. Okay, now this was sort of what I was alluding to before in terms of where we need to go. This is sort of all energy consumption put together, transportation, residential, industrial, commercial, all of these things, where we consume a lot of oil. This is almost entirely transportation and some industrial uses as well. Natural gas for home heating and industrial purposes. You've seen this large wedge growing as natural gas is displacing coal in the generation sector. You've seen how quickly this transformation can have. We've been making progress with renewables, but like in terms of scale here, we sort of need to go from here to the sum of these put together, right? That's what real decarbonization means. It means getting these fuels out of transportation and home heating as well, right? So we need to decarbonize the grid. And we also need to massively expand the grid into these areas where we're typically not using electricity. All right, now that map that I had before of coal resources, similarly concentrated for gas or oil resources, is quite different for solar and for wind. Some places get a lot more sun than others. Don't think that needs to be emphasized in London. But you can see how this is inconsistent with the model that I was describing before of a local monopolist who wants to own the generation resources in their territory. You would much rather run a bunch of wires to the southwest, to North Africa. So the UK is currently, I'm not sure of the state of the negotiations, of a high voltage line to Morocco, which is fantastic. In terms of like economically, where you want to be getting your resources from. It is similarly for wind. There are places where there are excellent wind resources off the coast, and that is not necessarily where people live. And so like one of the main challenges that we're going to be facing is this incredible reallocation of where resources are located and how we get them from the places they're located to where people actually live, because it's not going to be a pipeline or a rail car anymore. It's going to be a transmission line, right? So now we're moving to a renewables grid, where instead of predicting load and dispatching generation, we're trying to predict where the sun is going to shine and where the wind is going to blow. We're predicting generation, and we need to figure out a way to dispatch load, to send signals to consumers that now is a time where you should be running your hot water heater in order to have hot water for later. You should be charging your car battery in order to charge your car for later. These are coordination mechanisms that need to become prevalent that basically don't exist for all intents and purposes in any widespread sense, right? So a very big change both in how we're generating power and coordinating the generation of power, but also for how we're going to coordinate the consumption of power. As I described before, I mean, it's kind of funny to see the way that special interests have been entrenched in this discussion, because they're sort of fighting over the territory that they know. Whereas if you step out for a second and think of the scale in which the electricity sector needs to grow to decarbonize the economy, there is going to be a lot of money for a lot of people to be made in expanding the grid and expanding electrification to these other sectors. And so it's kind of frustrating to see these sort of small ball current issues be fought over so fiercely. Okay, so in terms of what's keeping us from getting there, one thing that we have been doing is subsidizing the generation of renewables. Right. This is, again, something that is common across many places, that the way we've been solving this problem to increase renewables is to subsidize generation, whether it is a feed-in tariff or a renewable production tax credit in the United States. We have made incredible progress in reducing the marginal cost of, well, it's not necessarily, it's generally marginal cost of production, the levelized cost of electricity, how much it costs to build a megawatt of capacity, the capacity factors, how often those are getting used. We have made incredible gains in generation. We have now taken that much more productive generation sector and plugged it into a 20th century grid. Right? The grid that was meant for reliability and not for the mass transit of electrons. And so we have these incredible wind resources through the middle of the country where no one lives and no extension cords to get them to the population centers. And so if you pay someone $23 per megawatt hour to generate from a renewable resource, they will wait until the price of electricity is a minus $23 fine before they turn the blades on their windmill, right? Because they're still happy to take a fine and make a $1 return when marginal costs are zero. And so we see this increasing prevalence of negative marginal prices in the electricity sector. That was 2019. That is 2022. We are massively expanding, as we need to, the generation of renewable resources. And we have this supply problem. You imagine your toilet is stuck. And what we're going to do by increasing the subsidies for renewables is just fix it by giving it another flush. All right. We are just really increasing the amount of renewables that we're pushing into the system, and it has nowhere to go. So we need to build more transmission. Now, why aren't we doing that? There is a long list of problems for all of the issues of building transmission. It usually starts with NIMBY, second is NIMBY, and third is that people hate power lines, right? But the fact of the matter is we already have a lot of power lines. There's a lot of upgrading on existing corridors that we could currently do. And in the United States, like the few examples of success that we have are in settings where they either replaced an existing transmission corridor with a higher voltage corridor. They ran it along the bottom of the Hudson River so that there's no one to complain about the sight lines. But we have a vast interstate transmission system. You could run it along highways. There are many existing corridors that we can run transmission lines. And so like a lot of we're still sort of figuring out exactly how we're going to make this grid the way we need it to. But I think an underappreciated aspect of the opposition to building out the grid, when we all see, or what the politicians see are NIMBYism, is just market power. There are incumbents who live on the other side of that transmission bottleneck. They are the generators in the population centers where that price is high. We're depressing the price where the renewables exist, and we have really high prices in the population centers. So if you want to, say, run a transmission line from Hydro-Quebec to Boston, the generators in Boston are not thrilled with this prospect and are pouring money into the grassroots organizations that are very concerned with their view sheds, right? And so for sure, there are going to be people who don't like the sight of power lines and that kind of thing, but ultimately, like, there are big bucks involved in running these opposition campaigns, these very loud opposition campaigns, takes a lot of money, and you will often see that it's really just incumbent interest behind it. And so you see a lot of really skittish policymakers that, you know, seeing through the ghost of NIMBY for what it actually is, I think can be very illuminating. I must have gone over time, so let me stop there.
Wonderful. So I'll continue talking about the grid and how the grid can enable renewable power to succeed. Here you can see my actual affiliation. It's ICREA, EI, and Northwestern. It's from September 1st. It's basically a research institute in Barcelona and Northwestern. So what I will do is continue talking about the grid, the challenges that grid expansion can entail, but I'll kind of bring in some feel-good kind of thing, because I'll talk about Chile, where we have a successful grid expansion. Not always true, often not true, almost always not true, I would say. But I'll talk about the Chile case, and I'll mention a little bit why in Chile it was doable, what are things that might be more portable to other settings, what are things that are more idiosyncratic to Chile that are good in Chile and nowhere else. But first, before getting to the case study from Chile, I'll follow up a little bit more on the introduction. This I don't need to do, because Steve already said that we need to decarbonize all these different things, and a big part is through electrification. Lots of homework, but that's where we need to go. And Steve already mentioned that all of this has become cheaper and cheaper. This is 2018. If you run it further, it's even cheaper. There's no question, especially in places like Europe, many developing countries that are not fossil fuel rich. There is no question the cheapest source of power now is solar, and even the big fossil fuel guys will not even try to contest it, because it's a very big truth. So that's good news. It's not true for those who are sitting on top of coal that you don't even have to mine. So there are challenges in the decarbonization process, but for many countries, solar is cheaper. And I would add it's way more reliable than fossil fuel. So oftentimes we talk about reliability and solar. There's no sun at night and whatever. Well, there might be no natural gas because there's a crisis. Geopolitical crisis, and that's really zero power, whereas with solar you know what you're getting into. And for many countries who are living in the Ecuador, that's way more reliable than being the last guy in the supply chain of natural gas. Good luck to you when things get ugly. So I do think there's a lot of good news in solar. Wind as well, although wind is much more complex to deploy, and the supply chain can get a bit more saturated. It's very concentrated, and it's way harder to place. So with wind power, you have the two NIMBY problems. Like, I don't want the wind farms, and I don't want the transmission lines that go to the wind farms. So I don't even want the wind farms far away from me. So wind farms, it's much harder, but for solar power, it's really a no-brainer in many places. The challenge, however, being that oftentimes these solar sites where you can easily deploy without much backlash might be far away. And in the case of the US or Chile, for example, Europe as well, the demand centers might not be close to the solar sites. In the case of
The US, yes, to some demand centers, but not all of them. In the case of Europe, Spain has a lot of empty land, but there are the Pyrenees in the middle, so it makes it a bit harder to reach to the rest of Europe, even though it's clearly a way more productive use of solar panels than London. So there we go. We are trying to think how can we connect this and what are successful examples. There are successful examples. Steve already mentioned China and the massive amount of ultra high voltage lines that they are building to bring wind, a lot of wind from the west to the east. Texas, for what's worth it, I would say has one of the most successful, maybe with the exception of California and Nevada, which were already talking to each other nicely. But I think Texas is probably the most successful expansion, or one of the most successful expansions to bring wind also from the west to the east. And then the one that I will mention in Chile, which basically is harvesting a lot of solar power from the Atacama Desert into Santiago, as well as the mining region in the north. So transmission can deliver many gains from trade. Even ceteris paribus, Steve already showed us that if you have a cheap place and an expensive place, you allow them to trade. Econ 101, that's better. It can also help mitigate market power. I think Steve was hinting a little bit at that with a Scooby-Doo kind of picture. But if you are sitting on top of some captive consumers, transmission is not good news for you. And then there are plenty of environmental and climate benefits, so local and global pollution will, no question, improve. There are many studies here. I'm just listing partially some of them that will quantify this benefit. So there have been several innovations in the transmission grid. One is direct current cables. That's the one that goes under the Hudson. Much easier for not in my backyard things. For geographical accidents like the Pyrenees, much easier to go around it. So it's not just the not in my backyard, it's also the fact that sometimes it's just easier. And they have very little losses, so you can go many lines. This is also true for the very high voltage lines that might be DC, but could also be alternate current. Another thing that I'm very excited about is the grid was built to be next to the demand centers and have the power plants next to the demand centers. And the grid itself is also a very complex network. Some of you might work with network economics. Well, the grid is kind of a network where you cannot choose the flows in each of its segments. You choose what you put in there, and then the segments do whatever they want by following the path of least resistance. So this means that whatever your network is, you throw a drop into the bucket, and that drop goes in whatever ways the laws of physics are determining for you. Well, that used to be true, but now they are coming up with basically damaged goods that will increase. You cannot decrease resistance of lines. That would be great, but you already build them to have the least resistance possible. But you can actually make them worse by adding resistance to the lines, and you can prevent bottlenecks by not allowing power to flow through places where it used to make sense that power would go there, but now it doesn't make sense depending on the hour of the day, depending on the day of the year. Now we can have a grid that changes from day to day, and it was not feasible. It's still not at scale, I would say, but it's coming, and it will make, you know, the grid a bit less dinosaur-y and a bit more like 21st century. At the lower level, smart meters can help quite a bit controlling voltage at the distribution network level. Here, maybe an interesting political economy, Scooby-Doo kind of a story is that the smart meters can really decrease losses, but utilities are paid for their losses. So if I'm a utility and I lose 6% of my output, just like, oh, here, 6% of my output, I'll get paid for that 6%. So if I now have a technology that makes it 3%, I'll be like, oh, where is my other 3%? So there are actually incentive programs that encourage utilities to cut their business by becoming better, because they otherwise would have no incentive to become better. But these are kind of nice things that are happening at the grid and the distribution level. So we already were mentioning that in the absence of transmission, we have challenges. because we have all that wind stuck in there. It can even deter investment altogether. So nowadays, there's a lot of wind increasing in that picture that the Steve showed us on how often do we have negative prices, because those wind farms are incentivized. But if you were not paying money to them, they would have no incentive in building a wind farm in a place where prices are negative. Oh, wait a minute, I'm gonna spend money to build a farm and then I will have to pay to produce with that farm. That doesn't sound like a good business model. So the lack of transmission can both deter an efficient outcome, and it can also deter further expansion of renewables. So this is a little bit why making progress in this transmission bottleneck is very, very important. One question that I added here, all of this is emphasizing that we can make a huge grid. Actually, some people were entertaining the possibility of having, you know, like the internet line that goes through the Atlantic and the Pacific, having a solar line that basically there's always sun somewhere in the earth, right? Like some side of the earth, so that we could just have this global electricity grid. It's a bit, you know, futuristic, but that would be like bigger is better. Here, I think for the discussion later, I was very interested in your perspectives on is bigger always better? And there are quite a few studies that mention, well, these transmission lines also cost a lot of money. So deploying just for the sake of it, because bigger is better, might not be necessarily the best strategy. Now, I showed you solar panels are becoming cheaper by the minute, but so are batteries. And with good batteries, we can basically create reliable grids that are at a much smaller scale. Typically, it would be a terrible idea to be Texas on my own. But with huge batteries, then Texas on my own, you know, it gives me some freedom. And I get people in Texas, I appreciate that. More importantly, in a small, not necessarily small countries, but countries that have a very small grid, going bigger is better, like could be a burden, economic burden, and you can build these grids that are not tiny, but that are a kind of a, so I think it will be interesting to see whether there is some leapfrogging into bigger is better versus small and a bit more resilient, especially in the face of a lot of climate Armageddon. So I think for later I wanted to know. So how do we do a cost benefit of the renewables on the grid? Here I'll get a little bit on the methodologies that we will see for the other paper. So my aim was to give the grad students also tools and methodologies to be curious about. So that was my agreed role in the session. So when we think of renewable deployment and transmission lines, a lot of it comes with opposition, especially in countries that already have quite good electricity supply. So then people feel more kind of entitled to be complaining about everything because they kind of have good electricity. So it's important to basically justify the cost and benefit and try to come up with a consensus, at least try. So it's no question that renewables are a no-brainer. And I think everyone agrees, even the fossil fuel guys agree because they have no choice. But when it comes to transmission lines, as I was mentioning, yes, bigger is better, but these projects can be really expensive. We'll be talking about thousands of millions of dollars. So which in the US, maybe it's not as much, but for a country like Chile or Spain, or, you know, like these are very large monetary investments. So it's kind of good to think about the benefits and costs in a clear way. So we can do a lot in cost benefits. Cost of the panels, it's very easy to quantify. There's a lot of data available. It could be a bit kind of engineering driven, report driven, but everyone knows what solar panels cost, kind of. Cost to incumbents, intermittency. Here I refused to put not in my backyard costs, but you can add not in my backyard costs. Benefits, price reductions from solar. By the way, I put costs to incumbent in the costs. I don't necessarily see this as a very big deal, but it does prevent progress. So that's why I put them in there. Benefits, again, are very large. And I do think in terms of resilience, some people think it's a cost to renewables, but I do think it's a clear benefit to resilience. In the project that I will present later, we also look at the transmission investment and the investment spillovers from transmission. So this idea that not only we're getting the static benefits from the solar panels, if we put a transmission line, yes, we spend a lot of money, but we completely change the picture in the market. So how do we do this type of analysis? For the ones that are in kind of black, it's relatively straightforward to do. Well, maybe resilience is a bit hard, but the others, it's relatively straightforward to do with a regression approach, where we can see what are the benefits of adding more wind and solar. I guess Mirabelle will see with the right instruments, but yes, we can kind of do that. For transmission and investment, we might require a more structural approach, a model approach to basically try to decide, okay, where should we put the transmission line? What will be the investment effect? What is it? Decentralization. So I do think the nice thing of renewables is that I don't think we are there, but that if there were some big shock, you can decouple some parts of the grid more easily. Yes. People are using it individually in Texas. So the very rich households have solar panels at home and a battery. And when the Texas grid fails, they have power. I do think we need to look for more public, socially optimal solutions that every single household. And I do wonder to which extent it will come in the form of a smaller, basically parts of the grid that can function on their own in the phase of, but I'm not sure we are there. But as of now, I see there are resilience benefits, but as of now, they are very privatized to the very rich individuals, which is not a very glamorous outcome, I would say. I mean, definitely socially unacceptable. So yes. So it's, I do think they can provide benefits. I'm not sure if I mentioned it somewhere here. Maybe, so people are building climate shelters with solar panels, batteries. Those would be tiny grids. I do wonder if there is a middle scale, a middle ground scale, but those have a more public purpose of providing electricity to everyone in the face of Star City. So the paper that I will present in Chile will basically emphasize the dynamic benefits from this transmission expansion. So not only we will do the regression analysis to get at the benefits, we will also build a model to show the investment benefits of the grid. And we will find that these benefits are very large and can be an order of magnitude larger than the static benefits, depending on the setting. I think accounting for these dynamic effects and making it transparent to people can help with the narrative of why do we need a transmission line, to make it very clear who are the winners, who are the losers. If we put this transmission line, this much solar will come in, but you want to kind of quantitatively be able to justify that. And I do think it can be important. The dynamic effects make it very hard to also deploy transmission projects because oftentimes there is an allocation problem of cost, where it's like, okay, if I put the line and I come in, who pays for the line? Is the solar panel that's coming in? Is the household that want the solar panel? So oftentimes what works best is that consumers pay for the transmission line, because otherwise there's a lot of chicken and egg problems of, oh, I'll pay for the line, but then other people will come in, and how can I make sure this line is for me? With the exception of very localized projects like a wind farm, that's very clear that's the line of the wind farm, then typically the wind farm will pay for it. But in practice, because the cost allocation process is difficult, it tends to work best when we subsidize the renewables implicitly via transmission. In many countries, renewables are no longer subsidized. They don't need to be subsidized, but I do think there is room for subsidizing. So making it as easy as possible to connect to the grid, even if that means putting some dynamic investments in there, some big transmission lines that will pay off with a longer time period. So I wanted to mention briefly also for discussion later, it will not be part of the case study that I will present, but how we think about dynamics in terms of demand. So I come from Spain, as I mentioned, and obviously we would be eager to put a lot of solar panels in Spain so that we can send it to France and Germany and send them cheap power. But many people in Spain are also eager to see if our cheap power will bring jobs to Spain. And that's an alternative to moving electricity with transmission lines. It's bringing the demand to where solar power is. I think for existing businesses, it might be hard to be like, okay, let's move this entire factory to Spain. But for some other goods, it might be a good kind of complementary way of transmitting power, so changing where it's demanded. So that I think we need more work, and it might be interesting for the PhD students to think about how to look at manufacturing effects. But I will not have it in the case study. I do think, by the way, it's important for Chile, but in our case, you would need a longer time series because it just happened, and these manufacturing effects tend to be a bit slower. So the case study from Chile, I'll go fast because do I have 5 minutes or maybe 10? Okay. So the case study that we'll be looking at, we'll see how a transmission project in Chile performed. And by doing so, I'll kind of show you the tools that we use to quantify the benefits from this transmission project. It was bringing solar power from the Atacama Desert to Santiago. By the way, with this picture, yes, they do need to get cleaned. So it's not zero marginal cost, we need to clean them. But badly, it's zero marginal cost in the Atacama Desert. Steve had that picture on solar radiation. Atacama Desert is the best radiation point in the entire world. And this is why there are many astronomy centers there. There's literally no one there, so there's no light contamination for the astronomers. But on top of that, there are no clouds. So you get absolutely very precise solar power. Yes, it gets hot, but even taking that into account, you get great solar output from there. So Chile, for those of you who know the country, tended to be an extremely energy poor country, and it was very dependent on imports of fossil fuels, even diesel. For electricity production, this is kind of island level, kind of precarious kind of generation. 1 year, Argentina shut down the natural gas to Chile. I don't know if that sounds familiar to anyone here, but this can be extremely disruptive. So Chile used to be extremely energy poor, and it had gone from being ridiculously energy poor to having an energy boom. And it's thanks to these solar panels in the Chile desert. So Chile expanded its transmission to bring vast amount of power from the Atacama Desert to Santiago and the mining regions in the north. And the projects were approved with not a lot of political economy resistance. So I wanted to stop a second here. This is the part that is not extrapolable to other places. There are many reasons why this was easy. One is that the Atacama Desert is unpopulated. So you're bringing cheap power, but you're not taking it away from anyone. So there was no one directly benefiting from that cheap power that could oppose to this. It's also vastly unpopulated, so agreeing to put a line in there was not the biggest of the deals. And finally, and this is the funniest one, is that when it was approved, these things take a long time in most countries except China. So the line was maybe discussed in 2010, 2009. Solar was not cheap, but the model suggested that a coal power plant in the north could benefit from this line. It did not benefit from the line, but even the coal power plant was eager about this. Now that coal power plant might well have shut down, so they did not benefit from this, but at the moment they were supportive for it. Even the incumbents, the Scooby-Doo incumbents that Steve was talking about. So it's kind of a case study where everyone benefited, and the ones who did not, they thought they would. So that's kind of a good news scenario. So here you can see just visually the event study. There's no line between the yellow area and the blue area. You put a line between them and they become green and less dark blue. And then you put yet another line going to Santiago and everything becomes cheaper and more similar. So in the data, the benefits of the line are very visible. The point of the paper is to quantify them and kind of trade them against what it costs to build a line. The line costs $1.8 billion, so not a small amount, and not a small amount for a country the size of Chile. So what we do in the paper is an event study to look at the static effects, but then on top of that, we look at these dynamic effects. So how much solar could be added to the system thanks to the line. So Steve showed you the static benefits of trade. So if you imagine two regions, here there would be one very cheap region, the region with solar power that has a very low price, PA, and an expensive region that's the one demanding the most, which has a high price, PV. As you let them trade, the price should go down in the B region, but it will go up in the Atacama Desert. This is the typical gains from trade. What we quantify in the paper is that on top of the price going down, thanks to the Atacama Desert solar, you add a lot more solar to the Atacama Desert. So the benefits are not this other area, but they are as much bigger triangle of benefits thanks to this added investment. So we first do the event study. I'll go quickly, but we look at whether costs go down thanks to the line. It's a very straightforward setting. The event study is very clean because there is one day that they go like click, and now there's a line that's working. And an hour before it was not working. So it's like a high frequency event study, no question. So we have the two lines, we call them the interconnection, connecting the north and the south, and the reinforcement, which made the line better. And basically we quantify the benefits. Here we'll be regressing the costs on these two events. And then we will be controlling for the costs that you would expect in an ideal world. This is something that we will from Steve himself. And the idea is that these costs will help us control for many confounders that are happening at the hourly level, at the seasonal level. So you can see here, by the way, we were not too worried about the sign of these regressions. We were expecting it to be negative. It's a mechanical gain from trade that we should be expecting here. What we see is that cost went down by about $3 per megawatt hour. This is about a 10%, 5 to 10% reduction in costs, depending on the hour of the day. This is 5 to 10% reduction of all costs in the system. So it's a relatively large effect. So in the paper, we go into more detail, but is this event study giving us the right picture? Well, it's definitely giving us the correct immediate effect of the line, but it might be missing some of these investment effects. In particular, what happened in Chile is that once they announced the line, many of the solar panels were already being built in expectation of the line coming in. So by the time the line came in, all of the solar panels were already in there. So if we do an event study here, it will look like solar was already there and we were just using it better. But in practice, you would expect that a lot of these solar panels would not have come in unless they had expected that there would be somewhere to put that solar power. So what we do with the structural model is try to say, okay, how much of this solar power would not have happened without the line, so that we can do a better cost-benefit analysis. Because otherwise, we're missing a lot of the benefits from the line by thinking that this solar power would have magically been there, no matter what. So that's what we do. And to do that, we basically build a structural model. Here is where I'll share very quickly in 1 minute some links so that you can look into it better if you are excited about this. We built something I think similar to what Megan was describing, a model of the grid, where you on top of that have transmission, and then we try to see what happens if you put more transmission and less transmission, and how solar investment would change. So to do that, we are exploiting the fact that Chile is very long and thin. I joke sometimes that my next paper will be about Mozambique. So from a network point of view, it's a line. So the network is not as complicated as I described it before. It's just one line. So we can build a model that's very accurate with only 11 zones. Depending on the market, it's much more complicated. we build this model and then we try to see, okay, what happens when you have more connections here? What happens when you have less connections? I don't have time to go into the details, but basically we compute how much solar will come in depending on that. And then we do the before and after analysis, taking into account this solar. So again, I will not have time to go into the details, although I'll put some links there. I hope we can make this slide available. When we do the cost benefit, we compare the $1.8 billion to the benefits. And again, the key is to take into account the benefit in investment. If we assume that there are no investment effects, we find that yes, the internal rate of return is not bad, it's 6 to 7%. But if we take into account the investment effects, we basically find this is a no-brainer and you pay off the line very, very good. So that's, I think, one way to highlight that depending on how we frame the benefits of the transmission grid, we might have more or less resistance from the affected communities. And in this case, the numbers are both still quite positive because in Chile, solar power is amazing, but the numbers are even much more positive when we have these investment effects that are. So I talked about the political economy that makes the Chile case very easy. In our setting, we don't worry too much about winners and losers because basically everyone was a winner except for the coal power plant that we don't care about personally. I'm happy they didn't put it on hold. That's as much as I can say. In most other settings, I do think we need to worry about that. So in most other settings, you don't want to worry about not just the aggregate effect of the transmission line, but who are the winners, who are the losers, how can we compensate? So I'll leave it there, but for the slide, there will be these backup slides of modeling tools where I put coding examples. If you are interested in seeing a coding example, not for Chile, but for the Western interconnection, California, Nevada, and stuff like that, but it will be in the slides.
Okay, thank you. So I think
now I see here. My son is called, so I love your name. Now every time I see the Sam, my
you are such a Okay, so I think we'll start with Eric and Sam sort of reflecting a little bit on what Steve and Mara said, and then I'll open it up to the floor. I'll try to stay sort of centrally located so I can see hands on. Remind everyone if you want to ask a question or make comments, please remember to press the microphone. Each one's, I guess, not. Right? Yeah, those ones are automatically on. Okay, so maybe I'm not close enough. So the main thing is after you offer some reflections, we'll open it up to some questions and then we'll begin a discussion. But at any point in the next hour, you should feel free to raise your hand, add to the discussion here. So either one of you would like to begin? Sure.
Thank you so much. And this is very interesting. I'm honored to be here. And to go, the lectures were very good, very, very insightful. I'll tell you about, based on the lectures, about experience in Uganda, and I'll move a little bit Africa. We do have, we still are energy deficient in Uganda. We want more energy for industry development and for household use. Still the same thing in Africa. I know 60% of Africa is energy deficient. We use fossil fuel. We don't use coal much in Uganda, but the rest of Africa, like Nigeria, I know they still use. In Uganda, there's no coal, but we use a lot of oil and also hydropower that we generate. I was very, when I had the presentation from Steve, in China, you can transmit power 2,000 kilometers, and it was only 2%. We are not yet there, I'll tell you that. Probably also we need to do more research in Africa and Uganda. Maybe next year we shall have a presentation on Africa and Uganda. But we are not yet there. When it comes to using railway and pipelines for energy transmission, we are not yet there, slightly there. And what does this mean? We're using trucks to move oil from Mombasa to the center. It increases the price. And you know what it happens now to production and to growth and to GDP for the country. So these are some of the difficulties that we're facing and which are related really to making power easily reach the final user, industry or household. We have hydropower, like I've told you, but again, the transmission lines are not enough. So we still deficit in that way. We have power generated from there are two big dams that were constructed, but we cannot transmit power to the industry. So it's still, we don't have 28% of the population, the households in Uganda are on the grid. And really, if you can extrapolate it to Africa, it's mostly the most developing countries are like that. So with this deficiency, what next? What has happened? We've invested a lot in mini hydroelectric power generation points on small rivers. And these ones have managed to put power on the mid grid, which is still limited, like I told you, and I put it on, but we need more. But what do we depend on mostly than the rest of the country when it comes to power? It's biomass. Fuel wood is highly used. Most of the households for cooking, and mostly for cooking. Some point, industries, even tea industries use a lot of wood to heat, so they sell that. Then we've also gone to other renewables. Solar is something that we've gone in a lot. Luckily, like you put it, the price for solar generation equipment is going down. So households have managed to buy small panels with a battery for lighting, sometimes to put on a TV. But we've not been able to have it that much for power generation to run industries and the rest. We still, wind, still some cases used, but in some parts, it's not enough really to generate that big power. And now when going back to, we have biogas, also on-farm small generation points for family use, cooking and lighting. We've tried, because of the high dependence on wood fuel, we are cutting a lot of forest. And what we've gone to is now to make sure that we subsidize the use of energy saving stoves, rate awareness, and also be able to make sure we use it. So these are things that we're still using at the low level. We've not yet managed to put on the grid all this power. The potential is high if well tapped. And there's a lot of area to take on research and to advise us as government on what to do and where to go. But I thank you for the presentation, and those are my insights, looking at the different aspects that we have and what we presented and our challenges. We would be happy. I like to the thing is big better. Honestly, big would be better. But big comes with its problems also, because I'm going to depend on someone. Suppose this someone decides one day to say no. What will happen? Those are things that we need to go in very well and see. But big would be better because then the cost of generation probably would go through down, and then the transmission but it may also increase monopoly. Like we do now when we come back to the hydropower generation in Uganda in particular, we have what we call Uganda Electricity Distribution Company. And it has a monopoly because of the patent rights that we gave. We were energy deficient, then we called them to come in. So those are things that we may want to avoid as we increasingly invest in the small hydro in the household generation points. I want to stop here.
Thank you very much. That
Thank
was
you.
brilliant.
Yeah. Thank you. Brilliant presentations. Appear to relate more to Reguant presentation. I would have loved Steve to do his research in Ghana and see how it will pans out, because the question that was going through my head when I was listening to him, who owns the power? And I think the ownership of the power brings about the challenges that you spoke about. We don't have that in Ghana. I was going to ask you that question, who owns the ownership of the power in Chile? But I think at the tail end of your presentation, you addressed it, where we're talking about win-win, and you didn't care about the cool people, you know. Ghana, we generate a lot of our power from, it used to be hydro. We have a Kosombo Dam, which give us close to about 40% of the power generation in Ghana. And recently the government came out with renewable energy master plan, encouraging usage of solar. And I see that it's a question that was asked, decentralization, what that's going to be, you know, the way to go. In Ghana, the government is encouraging a lot more people to have their own solar in their households. Initially, when they started, the conversation was around, you get your own panel, use, and when there's excess, then the trade-off, the government takes it through the grid. What hasn't been done is how to connect the households of individual power, solar power, to the national grid. Not succeeded in doing that yet. I was talking about Steve's presentation when I was talking about the ownership of the power, because in Ghana, it's state-owned. And so the NIMBYism issues doesn't arise. And looking at the renewable energy master plan, an area that we're going to have a problem, especially when it comes to the solar panel, farming, it's land. The issue we have is a land tenure system, which individuals own lands. And so for you to build such a farm, you need to be using people's land, and it's going to be a challenge. But the master plan addresses that and says that that will be taken into, the plan will take spatial planning into consideration in acquiring land for such activities. Again, if you look at government policies and plans in addressing this energy renewable issues, started way back where government banned, in Africa and especially in Ghana, we use vehicles or cars that are slightly used from the West and the US and things like that. And no very old cars will be emitting more emissions and creating more problems. And so they banned the use of used cars coming into the country. That has gone beyond 10 years. You can't import vehicles 10 years and above into the country. That was the first step they took. And then they also trying to encourage the use of energy efficient bulbs. And so government through policy brought in a lot of energy efficient bulbs. And for electronic gadgets, they are rated. And so they banned the use of used refrigerators to be imported into the country. And so a lot of policies are going around ensuring that, we get a good environment. There's a policy of planting for, tree planting exercise, which annually millions of trees are planted. And so these things are going on to ensure that we become energy efficient. In fact, the challenge for the climate is energy. And the key to solve this problem is energy. And so with this energy master plan and this encouragement of individuals building using, a solar system, and then government policy of getting small grids, building small, mini grids. So the policy says that every 1,000 kilometers away from the national grid should be encouraged to use solar, because we have challenge of transmission. And transmission losses alone is between 28 to 35%, which is huge. Yes, and so trying to get this mini grid built is a way of also resolving that. You will not, as I said, will not have a challenge in people saying that don't bring this at my backyard because it's a state-controlled system. And power, especially electricity, is critical when it comes to political economy, because people want it, and the citizens can tell you that without giving us power, we will not vote for you. And so there's a lot of demand for it, and states, the government is prepared to extend electricity to virtually everywhere in the country. In Ghana, have about 90% penetration of access to electricity. So I think I will pause here and then through the discussion.
Yeah, so I think, it's interesting that the discussion that you were giving is sort of contrasting this big versus small, because the really, really big is you're moving energy across oceans, or at least across countries, and in Africa, whereas the other direction is because you're getting no money. For example, the government is getting no money from from people paying for electricity, that people then they want them just off grid, like getting rid of the loss making. I guess, why don't we open it up? I will try to remain in a central position so I can see hands on both sides. Anybody who wants to ask a question, just raise your hand. Okay, let's start here. It has to turn on green. I guess just shout.
Okay, for those on Zoom, I'm asking about Namibia, because in 2016, it had less than 1% of solar, and by 2018, it had 25%, and today it has 30%, making it kind of the outlier in the African subcontinent. So I just wanted to ask the panel, some reflections, if you do know about the Namibian experience. And I think the point that I find super interesting about that particular country is that the state-owned utility NamPower, they just held competitive auctions and got private investment. And that's sort of just been a struggle in so many other African countries where credit ratings are low and it's so hard to attract investment. So I'm just curious, what can we learn from that case? Or do you have any other information that would be interesting?
Right, so maybe we'll just get a couple more questions. You have to press the button. There you go. Maybe
Okay. Yep. The question goes into the same direction, maybe particularly to Eric and Sam. Sort of, what are the major barriers you think that prevent the spread of renewables, and what role sort of state ownership versus privatization plays? Yeah.
Yeah, great.
Go to Eric.
You have to hold the button down for someone.
Thank you for giving us a catalogue of efforts the government have been making in terms of renewable energy. But sitting where you sit as the Director General for the Ghana Meteo, has there been changes in the weather patterns, for instance, as a result of any of these interventions that have been made at all?
Let's ask one more here and then.
Yes, what I wanted to ask is, what's your view on renewable policy as such? You know, when you look at solarization, in South Asia, for example, it is happening at every scale, from the macro to household enterprises. So you can solarize your entire house for $10,000. If you are doing it premium, you can do it at $3,000. So there is a lot of informal renewable sector, which is sort of, cropping up. And we have no clarity on either the business model or a renewable policy like you have on the fossil fuel end. And, people are actually groping for a solution, while the evidence is clear that, this is a good thing, but we don't have anything on the policy front.
Good. I think we'll probably let you guys.
Yeah. So, hindrance to the penetration of renewables, maybe the rates that would have loved to have it. I think the challenge is the initial cost. I mean, the initial costs for getting the renewable appear to be high, even though it will pay over time and it will be cheaper. And so a country with high, poverty level, and the fact that government is encouraging individuals to, participate in this space, it becomes a bit challenging to get initial cost to start with. Secondly, I think the sensitization of the populace to buying to these government policies is another challenge. I mean, when you talk about solar, the ordinary person will tell you that, I understand the batteries are not correct, it gives you a lot of trouble. Some misinformation, misconception has been already put into the population. And so it makes it difficult for people to get people buying to easily accept the policy and run with it. And then for any political decision, the politician will want to calculate the political cost. And so if have a community where they rely on their charcoal and the bush, the trees and the wood in cooking, and now you want them to use gas as a means of cooking, and he would have gone to his or her farm to get the firewood for free, but now he has to pay to get a gas for cooking. I mean, you need to do a lot of sensitization to get such a person to buy. So these are some of the things that I think constitute a hindrance. Dr. Sowa spoke about as a meteorological institution, what do I think the weather patterns affects? In fact, as I said, climate change, the heart of it is energy, and the solution to it is the same energy. Weather patterns are changing. Just today, looking at my phone, a forecast, and the way it is raining in Accra, someone put it there that what is happening, the rainfall pattern has changed. In fact, ideally, in the southern part of Ghana, in August, we are not expecting major rains. It's a transition from major rainy season to the minor rainy season. Major rainy season ends around July, middle of July, and the minor rainy season will start in September. But this year, it rained heavily in August, which is supposed to be a transition period where we're not expecting a lot of rains. Again, the onset of the rain, which when we were growing up some years back, 80s, a rural man, a farmer, will start preparing his farms in February, very confident that in March you have the rain. Start planting even though he hasn't seen the rain. But now, onset of rain is somewhere around April, and sometimes getting to the end of April. And then the inundation, call it Costa flooding. With this global warming as a result of climate change, melting of the glaciers, sea rise, causing a lot of coastal erosion, causing a lot of resources to build sea defense. And you can build sea defense all along the coast and have an office in one of the coastal towns. The office has been virtually consumed by the erosion, and we have to abandon that office. And so there's a lot of challenges that we are facing with this climate change and its concomitant effects on the population.
Before we just take some more questions, do you, just on the last round, do you want to just comment on the last round, and then we're going to go through some more questions?
The last, I want to make a comment here. Thank you. And what I wanted to make is really in reference to Namibia's question. I will not talk about Namibia, but I'll talk about Uganda's experience. Because really in the last 10, 15 years also, I can't give you the numbers, but we've seen a rise in like solar panel use among the rural households and households in particular. And this has come out because of the deliberate action by government to raise awareness, that's number one, but also to avail the panels and the batteries at tax-free, and also encourage people to use them. We've done there are some exemptions for people in terms of tax for those who are bringing in the equipment for like biogas and the rest. So it's been a deliberate effort from that angle, but also there's been increase in urbanization for us in our case. You find there are many town centers that have come up and a little bit change in housing facilities and also what they do. So they demand more of household generated power for lighting and cooking. I think this could explain a little bit from our case and could take care of the Namibian case.
Great. So I think what we'll do, again, there was a question back here, and then there was one here, and then I'll take the lady. I'll take the lady too. So we got 4 questions, quick, concise questions, please. So starting with Richard, I guess. Let me go back here. Thanks.
Right, and then, sorry.
Thank you so much. So many great examples. Real quick, I want to give an example of North Macedonia, a country that has transformed its electricity sector in just 2-3 years just by regulatory policy. We've changed net metering to net billing. That was one of the things that we did, and we changed feed-in tariffs to auctions. And the auctions have proven effective because it has spurred solar energy investment into the country by 4 or 5-fold. And now we are a leader in the Western Balkans in terms of solar energy investment and also for self-consumption than any other Western Balkan country. In 2 years, we've lowered our net import of electricity was 30% of total electricity consumption. And in 2 years, we have lowered that to only 16%. And we are projected in the next year or two to actually be at zero imports of electricity. Now, I wanted to throw the example in as a case study because of the Chile example. And maybe the use of solar communities could be the best way forward in order to ensure a localized electricity sector, as you mentioned, because that is the next step to our energy transformation that we have currently in Macedonia.
Thank you. There was 2 questions in the back. I think the lady on the left there, yeah.
Yeah, thank you. So my question on scaling of the renewable energy. So speaking from the Rwandan context, but also from the Malawian context, so use of solar is something that is not new, but most solar units are confined to like home-based systems, so very small systems that are going to be used for lighting and not really much else. I was wondering if you have any sense on what needs to be done to scale these initiatives so that, you know, they're bigger and households can use this type of energy for more than just lighting. And as well as thinking about what are the potential trade-offs that are coming with that, that policymakers have to think about. Thank you.
Okay, thank you. This is just a broad question. So typically there is, I would say there is a strong disconnect between academic research and public policy. But part of what makes this conference very exciting is that a lot of the work that's done is, I would say, quite policy relevant. So I guess my question to you is, how can we bridge this gap, and what types of policy questions or priorities are there that academics and universities in general can help tackle, and what are the type of what are the most important and most urgent policy questions that you're currently grappling with that we can help bridge that gap? Thank you.
So I'm going to just try to distill a little bit and then pass around to the panel. So I think there's kind of 2 things going on. One is, which has been mentioned in different ways. One is sort of, are we going to go for just like more off-grid, plug and play Chinese panels? You know, it's become affordable, penetrating the population, as happening maybe less quickly in some countries. Or are we going to go for grids with huge amounts of renewables? It sounds like with ideally with better transmission lines. So that's, I'd like you to kind of all comment on where do you think we should go, because that's relevant to the public policy question. But the second thing I wanted to throw into the mix, a bit more controversial, is this drive to renewables really being driven by the interests of the countries themselves, because they want to have clean energy, they want to have less pollution or whatever, or is it being driven by the donors who are saying we want to have, you know, less greenhouse gases, and you guys are going to maybe not consuming lots of energy right now, but you will be, and so you guys have got to do renewables. So just throwing that into the mix. I mean, I guess because you do feel that that sometimes is a bit of a tension in sort of at least international donor circles. So maybe start with, just go around, starting with Mar on those two things.
Yeah, so to me, the what seems very inefficient is to go for the tiny solar panels that to you individually are a huge effort, but they don't provide much. But in many of the rural communities that are far away, it seems to me a transmission line would be too expensive. There's some research on how that is difficult. But let's say, so I'm doing work, not myself, but I'm in connection with a team that's doing work on climate shelters. And that's for California, where everyone has electricity all day. So it doesn't quite apply, but they are building these centers that have solar panels and batteries and can actually provide electricity for appliances or things that could be not just light. So I can imagine, and you will tell me whether it's relevant or not, but a model where you have these communities that can provide shelter, maybe can even be conditions temperature-wise for extreme temperature events. That would be the town kind of center where you might have some appliances that are kind of much higher power. Because in these tiny solar cells, you cannot connect anything that's more like, let's say, 100 beds, and 100 beds will get you this far, but it's really not something that can transform the way you live. So that seems to me like cheap, but it's harder to deploy because you have to have a bit of a blueprint of what that will look like. But it's not throwing it into individual households, in which I could see how for an individual household, if they still use it kind of at a subsistence level, it's not that big of an improvement for what it costs to them. So I don't know. I don't know too much, but to me it seems an in-between that seems like a good opportunity, but I don't know of any successful stories, and maybe you have some, but I would love to hear if there are success stories in that paradigm. For the very high voltage things, it's pretty fancy. So, and it's huge investment. It takes a long time to get the necessary materials to do the lines. So I can see room for the north of Africa getting connected to Europe, but it would be more like Europe expecting solar power rather than within Africa. That might be like a very high investment cost. And even in Europe or the US, they are done periodically in places where they seem to have a really high value, like Manhattan. So yeah, but you will tell me. But it's fancy, yes. They do it periodically, even here.
Yeah, thank you. I'll go straight to who is pushing this renewable energy in our country. And yeah, there's all this talk about renewable energy, about running out from fossils and the rest. Good enough. Also, it's coming at the right time. But if you see the use of renewable energy, solar and biogas in particular, and energy saving stoves, I will talk about those three in our country, more of access to energy.
Yeah.
It's people accessing energy easily to light their houses in rural areas where the grids couldn't go, even if there was no campaign for, stop the fuel. So that's one of the great, and it has really worked. And then the government has come in to put subsidies and reduce the prices. So that's it. That's a big driving force. When it comes to grids, yes, because when you look at us, like maybe countries, developing countries, Uganda in particular, and coming to government now at macro level, It's no longer accessing power in your house that's important, but it's much more important for us to be able to get energy to run industries, agro-industrialization in different parts of the country. Is it possible to generate enough power locally to run these industries? If yes, then we can do it. But we think, and I think the grid is could be much cheaper and more available to bring enough power to run industries, to spur development, and having, if we can do it with clean energy, green, renewable, the better. But we need that power in our countries. Thank you.
Okay, can we have 1 second?
Yeah.
So you mentioned whether they should do it because it's green. For me, it seems the cheapest option for many countries. Like not solar in the households for energy access, but like solar at a scale. Industry-wise, because Africa is well located in the Ecuador, you get sun more or less. I mean, yes, you don't get sun all day, but you get plenty of hours of sun. So you can time industrial production to the hours with sun. Everyone might be happier. I don't know. You don't need to, you can time to the solar hours and then sleep at night. So it seems to me a very cheap, potentially very cheap source of power. So in your governments, is it still seen as more expensive to pools? And if that's the case, why is it seen as more expensive? I can totally see households burning wood is cheaper. So that I can totally see, but at a scale for industrial processes, for example, in Spain, there is a lot of demand from industries that want to come to Spain because they see it as the cheapest way to do industrial production. Okay, it's not still melting, but if it's intermediate ranges of electricity consumption, they want to come to Spain, and we have not in my backyard problems where they want to come and they are like, okay, where are we going to put the factory and the solar panels? But to industries, to many, they see it as the best source of power. So
let me respond briefly. And thank you for that question. It's I think about the question of technology. We have the right technology to generate enough power to run the industries that we want. If it's cheaper, we know renewable energy is cheaper in the long run. The investment, the short term, it's expensive, but over time it gets cheaper and cheaper, and it's cheaper to use. We did some models, and we're looking at investment in renewable energy in our country. All that came out clearly. The question is, do we have that technology at the moment? And if we get it, can we be able to put this power on the grid? Is what I'm saying. Okay. How it's generated, but is it possible for it to go on the grid so that it can be able to supply different industries in different sports? My thinking, other than having it, on sport, and probably not enough in terms of to run the industries. But if it comes, better.
Yeah, so I believe the mixed approach. So for industries, the grid will be the best way to power the big plants. Fortunately for us in Ghana, we have hydro. And so the hydro is also green. So we can rely on the hydro and a bit of the solar. We have the sun to deal with the grid issue, and then encourage the households, as the policy appears to be, for individuals to have the solar system in their homes for lighting, for watching television, for household appliances. And I believe if we continue encouraging that, we'll be able to go to the point that the net will be given to the national grid. The issue of whether is being brought down or we have seen the need. Last week, I happened to be at Nairobi, where African Climate Summit, and I listened to the leaders, and I'm convinced that they appreciate that there's a need for us to go green. and that we have the resources as Africa to go green. And so it might have started from external source, but we've come to that realization that we need it ourselves. And I spoke about, as a head of meteorological institution, I see the effects of climate change. We measure the weather parameters, we give the forecast, and we can realize, we can see that really the climate is changing. And as a result of this global warming and fossil fuel that's affecting our climate, something needs to be done about it. Again, there was a question out there about the research issue. I think what needs to be done is to look at the policies and the measures that are being put in place and how it's actually addressing the issue. So to evaluate the policies that the countries are, implementing and see how it's actually addressing the issue. Because talk about climate change, talk about these effects, it's not stopping. And we are pushing in resources, policies, ideas to address them. How far are we going with the measures that we are putting in place? I think should be something that the researchers should take it on board.
I add one thing.
Yeah.
On the research, the measures, how best they're helping us to address the climate change question, important. But I would like for us, really, it's also interesting to look at it the other way. Are the measures we are putting in place going to improve the living standards of people? Can they lead to economic growth? Those could be good research questions also, complement the other side and this side.
Okay, we've covered a lot of ground, and I have some thoughts. I'll try not to ramble. I wanted to pick up from Eric's mention of hydropower, because we, in our discussions, didn't talk about it too much. I think that is worth highlighting, because many developing countries that have incredible hydro resources now have a resource that is even more valuable because they are the world's leading batteries. And so when we're looking at these maps and seeing wind and solar resources, we should also be looking at storage resources that these countries, whether their current assets are run-of-the-river hydro and additional investment from countries that are looking to buy renewables, would be very interested in building reservoirs in order to sort of complement the transmission and size issues that we've talked about before with pumped hydro. On the sort of grid versus off-grid questions, I think this is a really interesting one that I'm sort of a mix of optimistic and worried about, because on one hand, we have these technologies that can increase energy access to places where it's uneconomical to bring the grid, and that sounds great. On the other, we're thinking about putting these in places where perhaps the grid doesn't work so well, and if you're a family of means, it's now technologically feasible to defect. And so then I start worrying about a bifurcation of whether we are talking about education or health or transportation or anything else, where you have a two-track system where if there's a technology for the very wealthy to do their own thing, they're not so interested in contributing to something that would be a piece of public infrastructure that works well for everyone. And so do we have a grid that works well for everyone if households can guarantee that they have 24/7 power at home with their own rooftop solar and storage at home? I do worry about that bifurcation. And then I also wanted to mention, we've sort of gotten into it a bit in terms of the size of the grid that we're going to start running into. It was mentioned a bit with the East Africa power pool, the growing importance of international organizations here, because when you look at those maps, we're talking about going from autarky to relying on neighboring countries for a working grid. And there are, we're now a setting where we're used to sovereign governments being responsible for delivering power within their borders. And that is not going to be an economical way, potentially a feasible way, but not in like the economical way to deliver power. Two last things. One is, I think, a very interesting dynamic that happens when you convert to renewables that have effectively zero marginal cost. If you look at the Indian example, where in India there's plenty of generating capacity, the problem is that they're losing money on every megawatt hour that they produce because they're not collecting enough revenue. We're going to be changing that situation because the marginal cost of generation is zero. And so the rationing is going to happen on the capacity front. Because once you put in the capacity, you can keep it running and people can use as much as they want. And you're going to sort of be moving the question of how do you collect revenue to how much capacity can you build, instead of how much power are you going to be generating because you need to buy. So there's going to be some interesting dynamics that change there when you're thinking about so drastically changing the marginal cost of generating electricity. Last thing was on this issue of academics engaging with policymakers. It's sort of good news and bad news, which is that, 20 years ago, the question was kind of boring. It was that renewables are not economical. We have a technological problem. And how do you solve that? Well, you subsidize the technology and you subsidize innovation. And as Mara has mentioned, we've really done that. And so we have incredibly economical renewable resources. And now we have institutional questions. We have regulatory questions. We have questions that economists can really get involved in and be helpful with. And so there, I think, are a lot of really interesting topics for academics to be working on. And it's a setting where our policymakers are going to be making decisions, and it's either going to be a good one or a bad one. So might as well help it be a good one.
Brilliant. So I think we only have 4 minutes. And I thought I might give, just since we're at the IGC where it's all about research and policy, maybe ask Eric and Sam just to say what, there's a lot of researchers in the room, there's a lot of policymakers. What are the 3 things that you would like us to work on? You on the spot a bit.
Okay, so quick one. I spoke about the fact that for policymaker to be able to get his policy out there fully implemented and get its objective achieved is to get a buy-in of the man at the last line.
Mm-hmm.
And therefore, in even coming up with the policy, how inclusive the policy to get a buy-in of the end user for you to be successful. I think researchers should start doing analysis of how even policies are developed and how to get the citizens, support in its implementation. I believe it's critical because, as I said, every decision has a political cost to pay. Mm-hmm. And if you don't analyze that one very well, policymaker has a short term and the politician a short term to live. You will run away with the right decisions and then flow with what the people want, which may not be the right thing for the society.
Brilliant.
Thank you. We're on the spot really, but we'll discuss more about these things. There is a wide range, but just off head. One is, can we look at the different energy mixtures in different countries that can support economic growth? 2, for countries that have fossil fuel oil, they're going to produce oil, how best can they use it and what they should do? And also, how best can government be able to increase accessibility to energy in the entire, a range of things that we can talk about, but those 1, 2, 3, like you said. Thank you.
Mara and Steve, any final words? Great. Well, thank you, everyone. I think one thing that the gentleman from Macedonia sort of put into my mind and sort of came through with Chile and so on is that the variation in the penetration of these things is so immensely huge. And it sounds like a lot of fairly micro policy, as well as the political economy, is going to, it may be a good thing to kind of begin to think about what are the measures which at least seem to correlate with success in getting more renewables in, and try to sort of create almost, I mean, it's an old-fashioned word, case studies of success, just as a starting point for research.
And the nice thing about solar, I'm sorry, I'm emphasizing this so much, but even where the costs are and the security of supply that you gain, it really, you said it, it's success.
Yeah.
So we're talking more about untapped success rather than potential for failure, which is the common thing in most projects. You can fail, you can succeed, but here it seems like it's a lot of upside that's untapped. And I'm generally not that a person, but in the case of solar, I do think it's untapped potential. So what's preventing that untapped potential? Because we'll come up with other stories.
Yeah.
But there will not be like this huge, someone asked me, what can you say for certain? And I can say for certain, you can push solar in a way that's not just individualistic, that's not just targeting to whoever can afford this. And what I can say is maybe it will not be the most amazing policy ever, but it will not be a mistake. And that's a lot for public policy to say, I can guarantee it will not be a mistake, might not be the best test, but I would be shocked if we found this terrible example.
Yeah.
So it's to keep in mind. Opportunity, untapped opportunity, I see there.
Yeah. Fantastic. On that note, thank you everyone for being here.
And first off, we have Stephie. Again, these are the 30-minute sessions, so please wait until the end of the introductory slides before asking questions. Great.
So thanks very much for having my paper on the program. The usual disclaimer that the views in this paper are not necessarily the views of the event. Okay, so we might expect the effects of climate change to differ across households. And broadly, we can think about there being two reasons for this. First is that households differ in space, and so they have different exposures to climate risk. And second is that households differ in income, and so this gives them different abilities to adapt. And to put this in context, the previous macro climate economy style models have either abstracted from all of these differences and focused on modeling a global representative agent, so think about something like the DICE model, or there's been this recent, I think, very exciting push in the literature, very carefully about the spatial differences, and develop these models with many, many tiny regions and have people be able to move between the regions. What I want to do in this paper is just focus on the other dimension of that heterogeneity and think about income heterogeneity within a region. So to do this, I'm sorry, given the international nature of the audience, but I'm just going to focus on the US and then going to only think about one type of climate damage, which is going to be the direct effects of it getting hotter or higher temperatures. So think of this paper as the distributional consequences across income groups of higher temperatures in the US. The framework that I'm going to build upon will be a heterogeneous agent style macro model. What I'll add to this model is that the full distribution of temperature over the course of a year will affect household utility, and households will be able to adapt to those temperatures by purchasing energy and capital to use for heating and cooling. What I'll find is that the welfare consequences of climate change, where climate change is just the direct effects of kind of a rightward shift in that temperature distribution, will vary considerably with income, but they're not going to be purely regressive or purely progressive. So we'll talk a lot, obviously, about what those patterns look like and why. So I'm very much not the first person to think about the distributional effects of climate change. I'm building on a lot of other work here, but I'm going to skip these details in the interest of time and just go straight to the model. So I want to start with a simple model that I can solve it analytically. And my goal here is to look at how the welfare consequences of a change in temperature vary with income. So we'll make a lot of simplifying assumptions to keep things tractable and reduce the number of parameters floating around. And then later we'll relax most of those, probably not all of them, and build up a much richer quantitative model to use for a numerical. So in the simple model, everything's going to be static. And so there's a household, it gets utility from consumption, C, and from housing, H. And the utility the household gets from its house is going to depend on the temperature of the house. So that's T. So the idea is that if the household's house is a comfortable temperature, then it gets full utility from the house. D of T, which you can think of as a damage function, equals 1. But as your house gets a little bit too hot or a little bit too cold, then you're getting less than full utility from the house. Two other pieces of this utility function. First, the function out in front, G of zeta. Zeta is the outdoor temperature. And G of zeta you can think of as the amenity value of, say, a nice day. Take this formulation directly from some of Esteban Rosican's work. Then the other piece of utility function is that provided the indoor temperature, so T, the temperature of your house, is not extremely hot or extremely cold, so you can think of it as within the bounds necessary for life, then you get the top line on the utility function. If you're outside of those bounds, then you die and you get the line, the bottom value of the utility. So the indoor temperature of the house is something the household can control. It's going to equal the outdoor temperature, which is zeta, plus any energy the household purchases for heating, minus any energy the household purchases for cooking. So the household's optimization problem then is to choose consumption and housing and indoor temperature to maximize utility, subject to the budget constraint that just says its income, Y, has to equal its total expenditures. So what I want to do is solve this model for the household's optimal choices of consumption, housing, and temperature. And I'm going to focus on the case of a cold day. So think about the outdoor temperature, zeta, being something less than the bliss point zeta star. Everything is symmetric if you were to instead do a hot day. So this is what you get. The first line here is showing you the optimal choices of consumption, housing, and temperature. This implies the optimal choices of energy. Our heating or cooling energy is just 0 because we're thinking about a cold day, so you're using heating. What we can see from these expressions is that the outdoor temperature, the zeta, acts as a transfer from nature to households. So if we think about, take an example, let's suppose the outdoor temperature is 10 degrees, then all households are given 10 degrees of heating for free, which augments their income by the value of that heating. So we'll have a more complicated functional form later. This is just to keep things simple. Thank you. Produce the degree of 1 unit of energy produces 1 degree of heating. So what this says then is everyone's getting these 10 degrees of heating for free, but the 10 degrees are more valuable to lower income households because they constitute a larger portion of your budgets. The exact same intuition for say why lump sum transfers are progressive from the public fund. So what we can do then is thinking about the outdoor temperature as these transfers from nature gives us some insights on the distributional consequences of changes in temperature. So let's suppose instead of it being 10 degrees outside, it's 5 degrees outside. That corresponds to a reduction in these transfers from nature. And that reduction is more costly for lower income households because they value those transfers more to begin with. And so what this suggests then is extreme temperatures, which correspond to these reductions in transfers from nature relative to, say, a moderate day, are going to be more costly for lower income households and hence regressive. So if we think about this then in the context of climate change, this particular channel would imply that climate change will be regressive if it leads to more extreme temperatures, which would be true in the southern portions of the US, and progressive if it leads to fewer extreme temperatures, which would be true in the northern portions. That's a simple model. What I want to do now is So I didn't say it was a blessing necessarily, but what we see from just taking the county level climate projections and shifting that distribution to the right, just from what I'll show you the ones I use. There you see just a mechanically on average, at least you're getting fewer of those.
So one thing that we suffer from is not only having lower budget, but also having more people. So we're very comfortable that they have the function, manpower, and keeping on the income, but heavy value that you mentioned as well. First of all, I have one but I'm about that. My family.
So the answer to your question is really kind of sort of. So let me come back to that point when we get to the content, which is a little more rigorous, but it's not quite going to satisfy your. So I want to turn now to the quantitative model. The goal here is to kind of build off this intuition of these transfers from nature, but add, I think, some other pieces that are going to be important for as we think about quantitative. So first I'll add heating and cooling capital. So to produce degrees of heating or cooling, it's not just going to be energy, you're also going to need capital. Second, we'll bring in the full distribution of temperature over the course of a year will affect household utility. This is because a lot of the actions happening at the extremes, so we want to include those directly. And then third, we're going to embed this in a fully dynamic heterogeneous agent model, which will let us look at the interactions between climate risk and labor income risk, but we're not going to talk about that today. Then I'm going to subtract the amenity, take away two pieces too. First is this amenity value and mortality. And one reason for doing this is it can show in the analytic model that neither of these two features are critical for thinking about the relative welfare impacts of changes in temperatures across income groups. This comes with the important caveat here that I'm focused explicitly here on the informed, rational, and importantly, housed population. If you were to extend this to think also about the unhoused population, then this mortality channel becomes a lot more. So, but not in a completely satisfactory way. So I'm going to divide it. I want to give you an overview of the model, and then I'll show you some of the pieces, but not all of them. So I'm going to divide the U.S. economy up into 5 different regions based on temperature. So think, cold, cool, hot, and so on. And within each region, there'll be a continuum of heterogeneous households. Each period, these households will draw an idiosyncratic labor productivity shock that over time will generate endogenous distributions of income and wealth. And then the households are solving a dynamic optimization problem in which they're choosing consumption, savings, housing, heating, capital, and energy, all to maximize expected lifetime. On the firm side, there's nothing interesting going on. I'm not going to talk about them at all. They're just producing the goods we need for the economy. Then there's also a government. The role of the government in this context is to provide energy assistance to low-income households in line with federal, state, and local policies that we have in the US, and it's going to finance this assistance with taxes. So what I want to do is basically build up the household utility function and their optimization problems. Let's start with thinking about the temperature distribution. So what I'm going to do is I'm going to think about there being 100 possible values of outdoor temperature, ranging from -40 degrees Celsius to 59 degrees Celsius. And so to do that, I'll break the model time period up, which will be a year, into 100 different subperiods, one for each value of the outdoor temperature. So this is just showing you a piece of that year where we have a subperiod where it's 10 degrees, a subperiod where it's 11 degrees, 12 degrees, 13 degrees. And the temperature distribution corresponds to the fraction of the year that you are in each one of these subperiods. So think of this as the number of days that it's 10 degrees, the number of days that it's 11 degrees, 12 degrees Celsius. This is big. And importantly, your households know that temperature can range between -40 and 59, but they have uncertainty over the distribution. And that is, they don't know, how many days it's going to be 10 degrees each year, how many days it'll be 11, and so on. So they have uncertainty over whether, this year will be a hot year. But then this temperature distribution will feed into the utility function. This is the utility for a household I in region N. It's going to depend on consumption and on housing, just like we saw in the simple model. The Q's here are those distribution weights that we had from the previous slides. It's the fraction of the period that you have outdoor, particular value of the outdoor temperature. So your utility over the course of the whole year is the sum of your utility in each of these different subperiods weighted by the amount of time that you're in the subperiod. And then we have a damage function. just like in the simple model, but with a slightly more general functional form. And then it's going to depend on the difference between your indoor temperature and a bliss point, which is Vegas. And so now we get to the indoor temperature where we can partially address Mars questions. Just to say, indoor temperature is in household I in a particular subperiod J in region N. Well, just like in the simple model, equal the outdoor temperature plus the amount of heating you produce minus the amount of cooling you produce. But now we have a bit more general functions here for the production of heating and cooling. So you're going to produce heating and cooling from heating and cooling capital. So those are the X's. So think like your air conditioner or your furnace, and from heating and cooling energy that you feed that air conditioner or furnace. There's also going to be a fixed cost of heating and cooling. So think of this as an installation cost for the air conditioner or for the furnace. The reason for this fixed cost is we want to capture the fact that not all households in the US have heaters or have air conditioners. Now talk a little bit about the calibration because we won't go through the whole thing in detail. So important parameters here are these theta parameters. I'm going to estimate those directly from product level data on air conditioner prices, outputs, and efficiency, and same with heaters. We'll calibrate the phi parameters, the kind of productivity terms here, jointly with several other parameters in the model, but the main moments pinning those down are going to be average heating and cooling energy budget shares from the US data. Now this H in front is your housing services. And what this is saying is that your production of the amount of energy of say heat or cooling you need to produce to change the temperature of your house by 1 degree is decreasing in your level of housing services. And the intuition for this is that if higher values of housing services correspond to bigger houses, and if I have a bigger house, it requires more energy to heat and cool that house. But that relationship is not 1 for 1. It's not 1 for 1 for 2 reasons. First is that even if I hire larger H, means I double the size of my house, I don't necessarily double the amount of energy I need to heat and cool that house because a major source of, say, heat loss is from air near the perimeter of your house. And if you double that area of the house, you typically don't double the perimeter. The other reason is kind of my half answer to Mar's concern, and that if I spend more on housing, I also tend to buy a more efficient house with better insulation and so on. And so doubling H is not just doubling, say, the size of the house necessarily, but also increasing the efficiency of the house. It's kind of a reduced form way to get at your. You should think about that gamma parameter as being something less than 1. In practice, what we'll do to calibrate that parameter is choose it to match variation in total energy expenditures on heating and cooling across income groups. So this is similar to the picture Kate was showing us yesterday, but the data here is not quite as, it's not as cool, and it's for you. Yeah. Yeah, so the fees are going to capture that trend. Okay. Their productivity, they're doing kind of both at once. Okay. Yeah. Two effects. So why no mortality? One is because, well, three factors. One is because if you look at, so about 1,000 people each year die from exposure to extreme temperatures in the US. This is likely an underestimate because we don't like to have a box when you go to the emergency room that says, you know, you died because you were too hot or too cold. But majority of those are among the unhoused population. This model has nothing to say about the unhoused population. Everyone here is housed. Second is that a larger portion of those deaths are coming from people making irrational decisions. Now, you live in Phoenix. In the middle of the day in the summer, some people would go hiking on Camelback Mountain. This didn't always turn out so well. In the model, everyone's fully informed about the dangers of heat, and so no one is going to behave that way. All those caveats aside, there are inevitably some people in the US who die because their house is an unhealthy temperature and they're fully rational and they can't get to a cooling center or a heating center or something like that. And to that extent, you should view the distributional effects as a lower bound. I think it's very reasonable to assume that's more of a problem at the bottom, and so view it as a lower bound at the bottom. The point here is that those numbers are very, very. Okay, so the household optimization problem, the period starts, the households learn their labor productivity, and then they choose their housing, their heating, and their cooling capital. And these are going to be fixed for the entire period. This is important. This means that just because it's, you know, a really cold day, I can't go out and buy a heater, use it just for this day and return it tomorrow when it's warmer out. So you have these things that are fixed and constant the whole period. After you make those decisions, you learn the temperature distribution for the year. So you learn, is it going to be a hot year or a cold year and so on. And then you march through each of these different sub-periods, choosing consumption, heating and cooling energy, temperature, and so on. Yeah. No, please. Yeah. No, I think so. I haven't thought at all, actually, but this is a good point about the interactions between your temperature at home and your productivity at work. What I have thought a little bit about is just the effects of heat on labor productivity in general, and talking to some construction firms on how do they think about effects of temperature on productivity when they're making these cost bids. And if you have these rules of thumb that I don't know how scientific they are, probably not very, but like we reduce productivity by X% for amount above or below a certain temperature. And when you take those rules of thumb and you feed in the change in the temperature distribution over the whole year, so accounting for the fewer cold days as well as the more hot days, you get changes of order of magnitude plus or minus 2%. And so which is small, but what I want to do is kind of a robustness around that, see how much it matters, is essentially put that shock in for just hitting the lowest income. But I haven't done that yet, but the interaction forms. Okay, this is the optimization problem in math. This is just to show you that the math exists, but we'll go straight to the experiments. So I'm skipping here the calibration. I hate skipping the calibration because we spend so much time on it. But the general thing here is the set of moments that we're matching are variation in energy expenditures and variation in heating and cooling budget shares across the income distribution. We also have a couple kind of external validation exercises to see how is the model performing against moments that we don't. Okay, so the experiment that I want to think about today is considering the distributional effects of climate change. So to do that, I'm going to compare two different stationary equilibria in the model. One I'll call the no climate change, or you can think the no additional climate change equilibrium, which is going to be, let's feed in the model the current distribution of temperatures that we have in years. And the second will be a climate change equilibrium where we feed in new temperature distribution. And this will be based on the projections for under RCP 8.5 in 2100. So we're going to think about these two different equilibria. So just to give you a sense of what the temperature distributions look like. So this is showing you, I divided the US up into 5 regions. So cold, cool, mild, warm, hot. This is showing you the coldest region on the left and the hottest region on the right, the temperature distributions. And the baseline is the solid line, and the climate change equilibrium is the dashed line. And what you can see here is climate change is essentially shifting these distributions to the right. And one more mechanical thing, to measure the welfare effects of climate change, I'm going to use what I'll call a consumption housing equivalent variation, which is going to be the percent increase in both consumption and housing that a household would need in every period in the no climate change equilibrium. So think today. So that an expectation, they're indifferent between living in the no climate change equilibrium and in the climate change equilibrium. So the takeaway here is negative numbers mean that climate change makes you worse off. Positive numbers would mean climate change makes you better off. Okay, so this is what we get. So let's walk through this slowly. So on the x-axis, we have the household's income decile, so ranging from poorest all the way to richest. On the y-axis, we have the welfare measure, where positive numbers mean you're better off, negative numbers mean you're worse off. And then each of these different lines correspond to the different regions of the US. So the way to interpret this is saying conditional on being in the first income decile, say in the hot region, the welfare cost of climate change would be about -0.5. So this graph looks messy. So the first thing I want to do is just clean it up by getting rid of the left half. And now we have something that's a little bit easier to interpret. So let's think about what's going on for this region, and then we'll bring back the lower income guys.
No. If you're thinking about contribution equivalent in cash value, like if you're very poor, then you still go to your cash is very high. So in some sense of categories, and what the income distribution, I mean, I'll give you a tiny amount of assumption to feel better about whatever is happening in your life. So it's a percentage. So this percentage. Okay.
Okay, so what do we see when we look at these middle and high income folks? So we have following patterns. We see in the colder regions of the US, we see climate change generating welfare benefits. Again, this is just direct effects of higher temperatures. And those benefits are generally larger for the lower income households, so making climate change progressive. In the hotter regions of the US, we see climate change creating welfare costs, and those costs are generally larger for lower income households, making climate change regressive. So let's think about why. To understand why we see these patterns, we can go back to that intuition that we developed from the simple model and calculate how climate change affects the transfers from nature going to these households. And so what this graph is showing you is plotting the change in transfer from nature relative to income. And so what we see is that in the cold region, climate change is increasing these transfers from nature, and relative to income, they're rising by more for lower income households than for higher income households, creating these benefits, and those benefits being progressive. In the hotter regions, climate change is reducing the transfers from nature, creating those welfare costs, and those welfare costs are larger for lower income households, giving us those regressive effects that we saw before. So that helps us understand what's going on for these medium and high income households. Now what I want to do is bring back the other guys and try to see what's happening here at the bottom of our distribution. And so for that, we need a second channel, which I'm going to call changes in kind of the favorability, if you will, of the temperature distribution to specialization. So the idea here is that to produce heat, I need a heater, and to produce air conditioning, I need an air conditioner. Pretend there are no heat pumps. You can add in a heat pump. It doesn't change anything. So what happens then is that we can think about all else equal. I would be better off if I had a temperature distribution where I just needed one of those types of capital. So say where there are only summer days, so I only need air conditioners, or there are only winter days, so I only need heaters. So what this graph is showing you is, in some sense, this specialization index, or how favorable is the temperature distribution to being able to specialize in, say, only air conditioning or only heating. If this equals 1, it's very favorable to that specialization. You only have summer days or you only have winter days. If it equals 0, it's not at all favorable to specialization. You have exactly half summer days and half winter days. So what we can see here is in the baseline, these cold and cooler regions are more favorable to specialization than, say, the warm and the hotter regions. That pattern switches when we bring in climate change. That shift in the temperature distribution, say, to the right, is making these cold and cool regions less favorable to specialization, and the warm and hotter regions kind of more favorable. So the decrease in specialization favorability in the cold regions is going to create welfare costs across the income distribution, whereas the increase in the ability to specialize in the hotter regions will create benefits across the distribution. But these effects are going to be particularly acute at the bottom of the distribution, where they're basically affecting whether households are moving in and out of corner solutions. As in, do I choose to buy an air conditioner or not, or do I choose to buy a heater or not?
So I think this is fine insofar as it jumps temperature. I wouldn't include
No, so I tried to be very clear. I'm sorry that I wasn't. No, this is just thinking about one aspect of climate change, which is the direct effects of higher temperatures. There's nothing to say about storms or sea level rise or anything. You conditional on living in the hot region, and that's how you know the law. Okay. Yeah.
Does this include installation? Because I understand that installation is somehow power conversion. And related to that is, I understand today that heat pumps are allowed, but in the future, if you think about there will be only heat pumps left.
So I think these are both great points. So the insulation gets back to Mars' original budget. It's there to sort of reduce convection. That implicitly, if you spend more on housing services, you're getting a more insulated house. You could add a separate choice variable of what is the insulation capital. I haven't done that. I don't know how to do that. But the heat pumps, I can bring this up. So I haven't done it for this calibration, which is why it's not here yet. We don't see big effects at the moment, like you said. But I think it's very interesting to do if you like change the world, subsidize heat pumps a lot, and see what happens. Okay, so we have this change in specialization. This can help us understand what's going on here at the very bottom of the distribution. So let's first just focus on the cold region. The cold region, we see this increase in transfers from nature, and that's causing, creating these welfare benefits. But at the very bottom, we don't have those benefits. In fact, we have these costs. Why? It's coming down to this moving in and out of corner solution. This is showing you in the baseline in blue, in the climate change equilibrium in orange, the fraction of households that don't have AC in the cold region. And what you can see is at the bottom of the distribution in the baseline, almost no households have air conditioning. They're all choosing that corner solution. But as the temperature distribution has moved to the right, that corner solution is no longer optimal. And that lack of ability to kind of choose the corner is creating those welfare costs that are dominating the benefits from having a more moderate temperature distribution overall. We see the exact opposite story if we think about the hot region. In the hot region, we have a reduction in transfers from nature, but we see welfare benefits at the bottom of the distribution because these households now are moving to a temperature distribution where they can specialize and choose only to have air conditioners and not have heaters because that temperature distribution moves farther. Okay, so just to conclude, we wanted to think about the distributional effects of climate change, or again, climate change is just one aspect of that. The kind of rightward shift in the temperature distribution. We developed this idea of kind of climate change affecting transfers from nature, which would suggest it's regressive in the hotter regions of the US and progressive in the colder regions. This change in kind of ability to specialize undoes those impacts for the lower. There's lots more that I'm working on exploring here, so I view this kind of as a first step, some of which are things you've already suggested. Thank you very much.
Okay, thank you very much. I'm very glad to be presenting here. It's been a great conference. So this is joint work with Fiona Berlig and Amir Jinnah, both at the University of Chicago. It's also work in progress. So if there are bits you don't like, you should tell me what we should do instead, so that you do like it. So the point of departure of this paper is really the idea that we should all be very invested and concerned about improving health outcomes in developing countries. You can arrive as economists at that conclusion in two ways. There's a growing sort of micro literature that suggests that health is an important input into economic growth, or you could believe it is a moral imperative, as the philosopher Michael Sandel suggests. Either way, I'm going to take as given that we care about improving health. Now, if we do, then in developing countries in particular, of course, this is true everywhere where there's a limited number of resources, prevention is much cheaper and much better than cure, right? And so we're interested in particular about, yeah. Reduces. Yeah. So clean water is an especially important preventive input into staying healthy, right? And there's lots of evidence for this. Diarrhea is the second leading cause of childhood mortality. The WHO has linked a whole range of not very nice things to contaminated water. And what's especially concerning is even today, there's very large sections of the population that do not have access to pure water, right? So it's only 30% of people in sub-Saharan Africa, for instance, have reliable access to clean water. And that was on diseases. Now you'd expect that if water is so important, then purifying water must be very helpful. This is a figure from a recent meta-analysis by Michael Kremer and several co-authors, which is basically putting together a bunch of studies that have looked at point of use treatment, so mostly chlorine, and collected data from all of these studies, which tend to be underpowered in themselves to identify infant mortality outcomes because there aren't that many children in any given sample. But when you put it all together, you see all of these studies on the left of that line, all of them reducing infant mortality. Which gets us to the problem that this literature, I think, has. The demand for point of use treatment is extraordinarily low. Now, this is a figure, I don't know where, I think the source got cut off. This is Ted Miguel and Pascaline Dupas, a 2017 review. This is a bunch of different preventive health interventions that people have studied. You have people who are highly elastic across all of them. So that's a problem. But look at the one on the extreme left, which sort of falls off a cliff. That's your point of use treatment of water. That's chlorine tablets, right? And so this is the problem. Water is really important. Clean water is really important, but chlorine tablets seem highly unpopular. And what's interesting here is, so chlorine is incredibly cheap, which means even though chlorine tablets are highly unpopular, they sail through cost-benefit analyses because infant mortality is a terrifying outcome, and chlorine is dirt cheap. And you would not see a benefit by cost ratio as being the mechanism to decide what is an optimal intervention in a paper in the American Economic Review. But it is the mechanism that a lot of funding agencies are using to decide what to fund, right? And so what we see, if you look at this literature, is the point of use treatment is about as popular with researchers as it is unpopular with people. So in that meta-analysis, 14 out of 15 studies are point of use treatment, 12 of them chlorine, the other two sort of derivatives of that. The one exception is the famous spring cleaning paper, which is point of collection. And that's demand curve showed you the picture. If you want to look at some numbers, you have a 60% demand for chlorine at zero price. This is people showing up to your house and saying, I will give you chlorine, and households saying, thank you very much, but no. You add any sort of cost to that, and it falls even further. This includes inconvenience costs, right? And then, the depressing part is that people who do take the chlorine are not necessarily using it to put in their drinking water. They might be using it to clean their home. So even that 60% is probably. So, what are the explanations for this? So there's several explanations have been proposed. Poor people don't care about health. This one, I think most people agree, doesn't make much sense because they spend a lot on curative expenses. So then we come to the second one, which is poor people don't know any better. There's an information failure, right? And this is mixed. So there's some work that shows information interventions increasing the demand for treatment. There's other work that suggests that it doesn't. And so there's a bunch of papers, I haven't cited them all, and it's kind of go in different places. Then there's poor people aren't thinking straight. So when poor people don't do what we think they ought to do, this is explanation that tends to come up. And so there's a lot of evidence that you can rationalize a lot of the evidence on how people invest in preventive expenditures, or rather don't, by saying they're suffering from present bias and limited attention. This is again a contested thing, but that's one explanation. Then there's the one that might come most straightforwardly, that poor people do have high willingness to pay, but they don't have high ability to pay, perhaps because there are liquidity constraints or other things stopping them from paying. And then there's the last one, which I think deserves more attention in the literature, and in some sense is sort of the motivation for this paper, which is chlorine's incredible cheapness may hide a large number, a very high non-monetary costs. Now, I could not actually find this in most, no actually analysis of what these costs are in economics papers. But if you go outside, there is a massive literature on when people can detect the taste of chlorine, in that's chloramines, and what they think about it. And so this is a bunch of papers from the United States, from South Africa, Sub-Saharan Africa, Bangladesh, India. Two things come out uniformly. You can detect chlorine well below purification threshold. So it's not that, people who hate the taste of chlorine are putting in too much. And everybody dislikes the taste. Right? And so this is where we come in. Yeah. They buy bottled water or they get it from taps, right? So it's, there's the, hot tea with a dash of milk and a drop of bleach is not popular. But so, that's sort of where this study comes in. So our idea is another route to delivering clean water, and maybe thinking about how people react to it, is to actually deliver clean water. So this is an RCT. We're going to deliver, the intervention is home delivery of tasteless, odorless bottled water to rural households. We're going to use 3 different mechanisms of delivering this water. I'll describe it in a bit more detail. 2 of them are very standard. One is varying prices. The other is a ration, a fixed entitlement. And the third is something we call an exchangeable ration, which is you have an entitlement. If you don't use a bottle of water, you are automatically paid a certain sum of money, right? And so the varying prices and exchangeable rations are designed such as exactly the same marginal cost, except instead of paying, you are foregoing, right? This is done in collaboration with a startup that operates in the Indian state of Odisha. They've been operating for about 10 years in 230 villages. I'll tell you a little bit about the model. The reason I'm bringing that up is we did not just use the University of Chicago's abundant funds to buy Perrier and distribute it to these households. So I'm going to try and argue this is very sustainable. Think about is it. There's a bunch of things we'll do with it. I'll talk about it. Well, these are the conclusions. So that we're going to come to the following conclusions. The first is that households place a very high value on clean water, but that they do have a constrained ability to pay. So you can look at these conclusions in light of those different explanations. The second is take up under regimes other than prices reaches up to 90%. So this is way higher than point of use treatment. The third is that we see lumpy demand. Most households buy either zero or they buy enough to cover their drinking water needs. Now, this is a sophisticated model of health because it's probably what we do. If you want to stay healthy, you drink only purified water. So that suggests information. The fourth is that households do report large health benefits. It's important that they report them because that means they perceive them. Otherwise, it's not. And the fifth is that we're going to argue that rations are the most are the best of those 3 mechanisms, that rations are both effective and economically efficient. Okay, so I'm, just to move on quickly, the study sites are in the state of Odisha in India. It's a bunch of villages, about 150 villages, and that's where Odisha is. Households in these villages at baseline use various sources of untreated water. Most of them can be clubbed into two types. There's groundwater from different sorts of wells. And then there's piped water, which is actually sort of groundwater because this is the government collects groundwater, puts it in a tank, and then runs a pipe to a house. So it's a convenience measure, but it doesn't make the water clean. Spring Health, which is the company that's our partner, essentially has, the model is the following. So you have it's a franchise model. You have a bunch of decentralized treatment plants. And then you have a village entrepreneur responsible for operating the treatment plant and providing the input water, which is groundwater. And then you have a bunch of executives who go around distributing that water to people, collecting money and paying a share of that to the entrepreneur, right? So they've been able to run this for 10 years. That's kind of what it looks like. There's a small treatment plant there, and then there are these bottles that get distributed to houses. Yeah, the original source is groundwater. So there's plenty of groundwater. Orissa is a water-rich state. So the experiment design is the following. It's a cluster randomized trial. So we randomize villages into these 3 allocation mechanisms. So that's prices, the exchangeable entitlement, and the fixed ration. And then within those villages, under the pricing regime, we have varying prices. Under the exchangeable entitlement regime, we have varying entitlements exactly equal to those prices. And the ration is just a ration. Now, we generate those varying prices by starting with the price that Spring Health is selling its water and then implementing a discount coupon off of that. Right? So we basically went around the entire village handing out scratch cards. You scratch your card, you see what treatment you do. Okay, I'm going to skip over this. So, we have some of our data. We don't have all of it. So that's why I said it's work in progress. Yeah. No, so you basically, at the time, the listing exercises I go around with these scratch cards. You scratch it in front of me, and then I note down your name, your phone number, and which treatment you're in. So now you can choose not to take the water, but you're the treated house. Okay, so let me start with my first conclusion, that households value clean water, but the WTP exceeds ability to pay. There's a bunch of numbers here. I really want you to look at the first 2 columns. So the first 2 columns are a comparison of how many households ever bought water. This is the compliance measure in point of use treatment under the discount regime and under this exchangeable entitlement. And you'll see these look completely different from each other. Again, the marginal costs are exactly the same by construction in these 2. This is not an endowment effect. You are not returning your water. Every day you have to make a decision on whether to place a order for water or get your money instead. And so what we see here is this exchangeable ration, even though you could get money for returning the water, has of the order of close to 90% of households taking the water rather than the money. We'll talk about how they do and how much. Even in the discount regime, it's an average of about 45%, and when you make prices cheaper, it's up to 90%. What's interesting is this is a histogram of demand, right? So I just found this really interesting. So this on the left is the prices, and on the right is this exchangeable entitlement. And you can read them one for one. So these are equivalent margin costs. So the first thing you see is no one is ordering small amounts of water. So a demand curve that would continuous would be a very bad description of demand, right? So the way to rationalize this, you have to rationalize this with a model where households believe they have to replace their drinking water. What's interesting is even for that highest price, the 10% discount, where there's very little demand, the average level of consumption conditional on consuming, so these are histograms for people who took any water, is roughly the same as it is for the 90%. That is, if you're going to buy it, you're going to buy all of it, right? So, this suggests to us informed households who know what the water is for and know why they are buying it. This is another way of looking at this. This is just if you fit a log demand function. This first column is, an IHS, so it includes the zeros. The second column is conditioning on people who bought water. All of the elasticity is on the extensive margin, moving from 0 to purchase. Not all of it, but the vast majority. Now, this is not a population that is weird. We didn't go and find some group of people who love clean water. This is a population that has access to chlorine. It's sold in this powder form in village shops. It's also distributed by the government. It is dirt cheap, 50 cents for 500 grams. You can, purify any amount of water for 500 grams. And about 2 or 3% of this population actually uses chlorine to purify their water. That's very similar to those demand curves we saw. So, if you pause there, our first order conclusion is if you want people to drink clean water, we should perhaps consider giving them clean water. And this might seem really obvious, but we have not been able to find a single other study which has actually used that intervention, right? This is survey results from a set of rolling surveys we did. We haven't got our end line analyzed yet. But what you see here is sort of there's these different measures. They're noisy, almost across the board and negative. To the question of did anyone have to miss work in the last week, they're significant and negative for all of these treatments. And so, they put together, these also intend to treat effects. So they become a bit stronger if you do a late because there's not. So put together, we'd say that these allocation regimes do seem to produce self-reported health benefits, which we think are important to rationalize the value of water.
How do you
Yeah, between the ration and the exchangeable ration, there's very little, there's no heterogeneity, very little. I haven't yet shown you the ration because I was going to discuss it later. The discount group does have lower take-up. And yeah, I mean, you could argue that for health expenses, it's a significantly lower regime. For diarrhea also. It is very similar for sickness and missed work. And one of the things we wanted to explore is whether it's the case that households who are willing to pay for water are also more careful about other things, such as how you store it and so on. So we're going to try and dig into that a little bit in the end line, because prices do potentially generate screening, right? And so in the exchangeable ration, we see pretty much everybody take up the water. So there's not much screening going on there. But under the varying prices, there might be screening. So that's one explanation. I don't know if that's the explanation.
I think the screening in the sense that in the free ration, you get the people that you screen in on discount, plus a whole bunch of other people. And this is like an average effect, not a effect. That would explain why you saw big effects in the supply. Anyway, I just think that
yeah. So it is something we have to dig into. But I think right now the only message I'm trying to take is that all of these people getting this water, these are all ITTs that are negative. So that's on the next slide, right? So now this is, I think, the really interesting part. So why are we saying rationing is a superior allocation method to prices? So first, that exchangeable ration regime, which we are using largely to identify whether there are market failures by looking at the demand curve under those two, that's not really a feasible, scalable policy instrument, right? So that's an experiment thing. So really the question is whether you prefer rations or whether water should be priced and distributed, right? So the first thing is that, the presence of this wedge between the willingness to pay and ability to pay, which we get from the comparison of the exchangeable entitlement and the prices, suggests there are market failures going on, right? So that's one argument against pricing. It's not economically efficient because of those market failures. Likely liquidity. The reason I say likely liquidity is when we look at those elasticities interacted with household income, we do see some evidence that the richer you are, the less elastic you are. And again, to just kind of hammer home how much people value this, because they're using either zero water or a lot of water, households who are in the entitlement regime choosing to take the water are leaving a lot of money on the table. So, if you take that 300 liters per month that they use and you multiply it by the highest price, that's about 430 rupees. That's about 10% of the income they earn and about 5% of the income if you include certain government transfers that these people get, which effectively are doubling. But the second interesting thing, which gets to Robin's point, is that rationing does not incur large deadweight losses. Now, what I've plotted here is two regimes. The first on the left is the entitlement with no exchanges. That's just the ration. And the second on the right is this exchangeable entitlement. The black line is the value of that entitlement. So the black line is the maximum you could take under the ration. It was intentionally set to be above what we thought households would need. And what's super interesting is you do not see people hitting that ration. They're not consuming as much as they could. And this dotted line here, which you can barely see, is something I calculated by taking 2 liters per day, which all the doctors tell us we should have, and multiplying it by average household size. So this has nothing to do with the sales data. And it basically sits right on top of these average demand numbers. So what this tells me is this is a population of households that knows how much it needs to drink, that is taking the water it needs to drink. There is not much value realistically to taking more for 2 reasons. The first is we don't find much evidence of trade in the water. And it's perhaps not that surprising because the whole point is it's supposed to be clean water. So when it comes to you in a sealed bottle, you know that, but your neighbor is very unlikely to take water from your house and think it's clean. And the other is that you have a whole bunch of other end users, and these households are not short of water per se. They're only short of clean water. So, if you need to bathe and so on, you're not going to be using this drinking water to bathe. It will not save you a trip to the well. So we don't think this is crazy, but anyway, this is the fact. We can come up with different stories, right? Yeah.
I think actually that quality of this question, yeah, we have this water for you, it can also money somehow creates an endowment that has the effect that, okay, actually this is the portion that I reserve, and now do I want to sell it back or?
No, absolutely. I just meant it's not the extreme version of the endowment effect where there's water sitting in your house and you need to return. The framing might well lead people to be nudged a little bit. It's just that it needs to be, how strong is that nudge? Well, it has to be 450 rupees a month strong for this population. That's quite a lot. But I'm totally willing to buy that there's a little bit of that going. You could think of the treatment plant as being your village level RO system, right? And then I'm transporting the water. So there are some transport costs. These households don't have those inbuilt RO systems for various reasons. 1, they're expensive. 2, you need electricity. And 3, their piped water is, as I said, it's a tank that was filled by the government occasionally. So it's not like you have 24/7 water. So that's why we don't see anyone with RO systems in this population. One thing we do see, which I didn't put up as a figure, is that when households report what they do to treat their water, I think I put up this thing. Yeah, actually, it is here. So it's very interesting. So this is a question, which is, what do you do to treat this water? Asked of every household for each source of water. So households are not necessarily just using one source of water. There's plenty of households who use piped water plus groundwater, and the bottled water is us. And what's interesting is you see households doing much more treatment of the bottled water and the piped water than they do of the groundwater, which again to us speaks of, first of all, households knowing when they should treat and why they are treating, but also a potential danger with government piped water if it's not actually clean. So we're running a bunch of tests to kind of more rigorously document that. But if that water isn't clean, which it's not, then it's perhaps a little misleading and is driving people to underinvest in what they do. The other thing I should point out here is that people do a lot more boiling than they do chlorine. I mean, I'm sorry for hammering away at chlorine. But as I said, it's dominated this literature, right? So boiling is a lot more expensive than chlorine. You need fuel and it takes more time, and you have to first heat up the water, then you have to wait for it to cool down. So, you know, those non-monetary costs with chlorine are not clearly not small.
Like, I think it's interesting that you get about enough water that everyone in the house, it turns on for the household and everyone gets clean water, which can suggest that you're not distributing it to sick children or the elderly.
Well, it's enough water for everybody's drinking needs if you take that 2 liters and multiply it by household size. We don't know yet who's, you know, well, the miswork is clearly people who work, so that's not children. But the falling ill, I think in our end line, we're hoping to say a bit more about who's falling ill. Anyway, this is my last slide because I'm also out of time. So how does all of this compare to point of use treatment, right? Now, this company barely stays afloat. So you might want to think of its costs as being about as low as you could get. And those costs are about 6 times as much per liter of water as chlorine is to treat it. Then you have to set that against the fact that 90% of our households are redeeming that water and 37% of households redeem free coupons in a couple of recent studies, right? So you get a huge number more of households. If you look at the cost per disability adjusted life year, chlorine will beat bottled water simply because chlorine is so cheap. And so even though we're hitting sort of 2.5 times as many households, you know, you're 6 times more expensive. But I think this is where I want to close with, this benefit cost maximization is just crazy, right? Because it's not the welfare benefits. There is no reason for us to be picking the cheapest thing we can find. We need to be maximizing welfare. And I think the point of this paper is that if you give people the sort of water that we drink, they behave in sophisticated, sensible ways. There are clearly market failures that prevent them from buying this water. But this is not, in our view, a world of uninformed households behaving irrationally or not valuing health or any of those other things which could explain point of use treatment, but cannot explain this behavior. So that's all. Yeah. I mean, the piped water tends to be huge. I mean, this is a good way of kind of, if you look at these last two who are basically using their whole thing, this is sort of, these are numbers in health expenses that are comparable to, or you couldn't reject that they're equal to the cost of the water that they, well, these people are not paying, but the foregone money for the water. So it's rational that way. I think with piped water, the problem is that in these developing countries, even cities have not managed to get clean piped water. So everybody's using those RO systems. So the purification is sort of a given. And the question is then just what's the best way of doing that? And I think it's entirely possible that once you get better piped water and a richer household, then they will use RO systems, and you will not have people wandering around with these things.
Just very quickly, it's clear that the technical aspects are working out immensely. In terms of limiting the corruption in the social enterprise aspect and the business aspect, in terms of the market efficiencies, how are you doing that? And what kind of informational campaign are you running? I've encountered a similar social entrepreneurship through wastewater treatment plants in rural areas in Bangladesh. I tried implementing such a project 6 years ago in Macedonia. Unfortunately, the villages have very few residents, and I was unable to implement it because of the cost benefit did not work out. But I was wondering, in your circumstances, what is the informational campaign that you're running, and how are you limiting corruption to ensure self-sustainability of the plants?
Yeah, so we're working in villages where this company is serving people, right? So they're serving people by charging them some price. And so the control does have some people buying water, not very many, because as you saw, they're highly elastic. So therefore, to the point on information treatment, we're not running a separate information treatment. And that doesn't mean these households have heard nothing about clean water, because the government tells them about clean water, and this company has also, gone around trying to get consumers and has told them about clean water. In terms of corruption, I think, when it's a private company trying to make money, which is what these guys are doing, then you have all of those usual private incentives to reduce corruption and increase efficiency. If you were to say, take us seriously and say the government should implement a ration using the same technology, then of course you run into the sets of problems that all governments run into when they're giving out a good for free. There might be some corruption in that setting, which we can't speak to. Yeah, I mean, so this is all great questions. I think their scalability, I think, so it can be scaled technologically. As a private market, I don't think there's any hope because there's very limited demand and they're, as I said, barely above water, right? But technologically, they've been around for 10 years and 230 villages is a lot, so you can certainly run this. Government crowding out is interesting, and I think the piped water comes in there. And in fact, Michael Kremer is running a study in Orissa, which is basically about putting chlorine into the piped water where it's stored. The idea being that households have this water and they're using it, and so maybe purify with that source. And so that's definitely another model. But I mean, I don't know. All of us should drink chlorine in water once before, getting excited about that. Yes, but so chlorine tablets are chloramines, right? So yeah, should be.
Great. Well, thank you so much to the organizers for including this paper on the program. This is investment, emissions, and reliability in electricity markets. So this paper is motivated by two different policy concerns. The first is that of climate change, which in this room I really don't have to motivate. But let me just note that electricity accounts for approximately a quarter of total global greenhouse gas emissions, more than any other industry. So that's policy concern number one. Policy concern number two is that of blackouts. So in electricity markets, it's possible for the demand for electricity in a given moment to exceed the available capacity for producing electricity in that moment, the maximum amount that we can produce. When this happens, we have to ration people via extremely costly blackouts. So I'm showing you these two separate policy concerns because these issues are connected. We have a solution to the first problem. We have renewables like solar and wind. They're emissions free, but they're also intermittent. The sun doesn't always shine, the wind doesn't always blow. What this means is that if renewables largely replace fossil fuels, this may result in more variability in that available capacity. Potentially, that could lead to an increase in blackouts. Let me give you a particular example of kind of what I'm talking about. Let's look at Texas. In July of last year, it was a very hot day. So this graph right here, we're looking over the course of the day. We've got demand, that's that blue line, and the available capacity, that's that purple line. Values to the left of that vertical line are realized values. Values to the right are projections from that point in time. So you may have to squint to see it, but as you maybe can see, the demand for electricity was predicted to exceed this available capacity. A blackout would have resulted. Now, they managed to avoid this mostly by sending out text messages to people begging them to turn off their lights. But I think it's still an instructive example to look. So what was happening during this time? Well, if we look at dispatchable capacity, about 85% of that capacity was available. And most strikingly, only 8% of wind capacity was available. It wasn't a particularly windy day. And the grid operator cites this in discussing this issue, saying that there was record high electricity demand due to the heat, while at the same time, there was very little wind. What I'm asking in this paper is, what are the policies that we should adopt if we want to develop an electricity industry that is both clean as well as reliable? Now, how a policy is going to impact these things, emissions and blackouts, is going to depend on how firms, investments, and retirements of generators of a variety of different technologies are going to respond to those policies. And as with that, generators changes in the market, that's going to change the equilibrium production decisions and the equilibrium prices. So to fully quantify the impact that a policy has, we need an equilibrium model that's going to link production and investment. So that's what I developed in this paper. It's a structural dynamic oligopoly model that's going to endogenize a few different things. The investment and production decisions for different energy sources, the distribution of wholesale electricity prices, the level of blackouts, and that of emissions. And then I'm going to use production and investment data from Western Australia in order to estimate the model's parameters and use those estimates to quantify the impact that counterfactual policy tools would have on emissions, blackouts, product market welfare. Specifically, I'm going to be looking at environmental policies like carbon taxes. I'll have a little bit also to say on renewable subsidies. And I'll also be looking at what I'll call reliability policies. So I'm going to specifically look at capacity payments. These are widely used in electricity markets, and you can think of these as basically subsidies to capacity. We're going to pay firms for having capacity, regardless of whether or not they're actually using that capacity. Okay, so let me give you a quick preview of the results, and then we'll dig into the meat of the paper. So we look at just a carbon tax by itself, equal to $20 per ton, would reduce emissions by 25%, quite a bit, given that it's not a huge tax on carbon, but it would increase the level of blackouts by 23%. Yeah.
But how do you define a blackout? Because blackouts are really
yeah. Yeah, so 23%, basically this increase in blackouts is going to be the equivalent of experiencing like between an hour and 2 hours additional amount of blackouts in here. Yeah. Okay, so then the other policy tool, subsidy to capacity, of the size that's currently used in Western Australia, virtually eliminates blackouts, but it increases emissions, and it does so by 11%. Now, when we use both of these tools, we're going to be able to reduce both emissions as well as blackouts. And the intuition behind why we can do both of these things simultaneously is that these two things depend on different margins. Blackouts are going to depend on an extensive margin. They depend on how much reliable capacity exists in the market, while emissions depend on an intensive margin, which generators are actually used to produce electricity. So if we subsidize reliable capacity, we make sure we've got, a large amount of reliable capacity, while at the same time making it expensive to use emissions-intensive technologies, we can achieve a reduction in both of these things. I also look at renewable subsidies. So those results were for carbon taxes. I'm going to find that they're less effective at reducing emissions, in particular renewable investment subsidies. And I also look at the impact of waiting to implement a carbon tax. So many environmental policies are announced, but don't actually go into effect until some point in the future. It gives firms some time to adjust to that policy. I find that we can reduce the cost of that policy a bit by waiting to implement a tax. But for most values of the social cost of carbon, the optimal delay would be just 1 year. Yeah. Yeah, I mean, when I'm calling it reliable capacity, like, of course, all technologies have like some possibility of, not being available. I'm calling it reliable because, the difference between the two is quite stark, but yeah, I mean dispatchable. When I'm saying reliable capacity here, I'm referring to dispatchable. Yes. Yep. I'm gonna give you the cost of these later on. Yeah.
Is there a way of
So I think there may be, I'm not looking at that paper, so answer your question, am I going to have anything to say about that? No. I think there's it's potentially interesting. I think maybe like implementability might be a little tricky there. I'm trying to, I guess if we're putting the penalty on the retailers rather than the generators, that's maybe a little more clear. You should pay the penalty, but yeah, but I'm not going to have anything to say about it. Yep. So here I'm giving you percentages, just as I think fairly easily interpretable, but like later on, what I'm going to give you are like numbers where I'm going to say, this is the cost of a blackout, this is the cost of emissions. And I'm going to like, provide those that like should account for that. I actually think blackouts are quite costly. And like, it's not going to be totally trivial, the impact of blackouts here. I mean, how much would you pay to like not have at some random point no longer any access to electricity? Like probably not a trivial amount, but yeah, I mean, I mean, I'm not saying that this is optimal. Anyway, but I mean, it's just later on, like there are going to be numbers associated with both of these things that should reflect the world. Yeah.
That's also like the policy.
For the
like that 23%.
Bullet point 4. Oh, I see. So I'm not going to give you the number in these slides. They are in the paper though. And so the renewable subsidies depends on whether we're looking at the production and investment subsidies. The production subsidies result in more blackouts. Investment subsidies a little bit less. I've got like the exact exercise. It's not orders of magnitude, but like that is the relationship compared to the carbon class. Okay, in the interest of time, I'm going to skip this slide, but I'll just note there's of course a very wide literature studying electricity markets. A more recent literature that's been looking at investment in these markets, and that's kind of where the main contribution of this paper lies. All right, so let me give you a little bit of background. It's nice to go at the end of the day because people talk about electricity a lot today. So I probably don't have to talk too much about like electricity market in general. Let me just tell you about Western Australia. So here's Australia. Here's Australia's transmission network. We're looking at the southwestern corner right here. That's from the city of Perth. Okay, so at the utility scale, almost all electricity is generated from 3 energy sources: coal, natural gas, and wind, with the majority coming from coal. So why look at Western Australia? Well, you look at it, it's basically an island, right? It's unconnected with the rest of the country. It's also fairly small. Both of those things are going to be nice for studying this. It's going to make it a kind of a tractable setting for modeling these issues because it's unconnected. We don't have to worry about trade with other markets because it's geographically quite concentrated. We're not so worried about transmission constraints. Moreover, in this market, they've used capacity payments. The size of these payments has varied significantly over time. that provides me with some nice variation for estimating some of the parameters. I'm not going to talk too much about that today, though. Okay, so how does the market work? So at a half-hourly level, we're going to be equating supply and demand. So what does this look like? We have some realization of demand. It's virtually unresponsive to whatever the wholesale spot market price of electricity is. Firms are submitting bids, and the grid operator is running auctions that are going to determine the price that equates supply and demand. That's happening every single half hour. Each year is when these capacity payments occur. Okay, so the grid operator chooses a capacity price, some number of dollars per megawatt. Firms choose what fraction of their capacity they're going to commit. What does a commitment mean? Well, it means that they're going to receive the payment, capacity price times the capacity they committed. And if they're unavailable for whatever reason, they're going to have to pay a penalty for that based on whatever the capacity is that they committed. That's happening every year. Over the long run, they're making an investment. They're making their investment and retirement decisions. I've got data from 2007 through 2020. This is detailed data on these half-hourly wholesale markets, prices, quantities produced by each generator, their availabilities, stuff on capacity payments, and characteristics of each of these generators. So since this is a paper about the long run, let me tell you about some of the long run trends here. So there's been a decline in coal, from 54% down to about 45% toward the end of the sample, a rise in wind, natural gas has stayed pretty constant. There's also been a decline in concentration. When we started off, one firm had produced about 80% of electricity. It's now producing 40%. You've seen the entry of some new firms and the rise of some smaller ones. We've also seen prices decline over time. Early on in the sample, we have some new investment in fossil fuels, but after those first few years, we've basically exclusively seen retirement of fossil fuels, particularly coal, and we've seen some new investment in wind, especially at the very end of the sample. Yeah. So Western Australia is a sunny place. If you remembered from Mars graph, if you happened to look at the southwestern corner of Australia, it is a sunny place. And there's a lot of rooftop solar. In fact, it's like one of the highest has some of the highest adoption in the world. But we see almost no utility scale solar. It's like less than 1%. Yeah, exactly. So, that's going to affect what the demand is, the net demand when we net out rooftop solar. But I think that's why we're not seeing that here. Okay, great. So let me dig into the model. So electricity is going to be produced by generators. What do generators look like? Well, they've got some capacity. They've got some technology. They're going to be a coal plant, gas plant, or a wind farm. And there's going to be a firm that owns the generator. Could be one of a number of strategic firms. It's going to end up corresponding to those 3 large firms I showed you a few slides ago, or part of a competitive fringe. And then we've got two components of the model here. We've got the short run, that's generator production. It's going to correspond to the half-hourly interval, where the set of generators is fixed. We have some realization of demand. Firms compete, they get profits in that half hour. Over the long run, and this is going to correspond to a yearly interval, we've got the investment and retirement decisions. So firms are adjusting their sets of generators. We're getting a new portfolio of generators. Demand is going to respond to average wholesale prices. The distribution of realizations of inelastic demand is either shifting up or down, depending on the price. That's going to yield the expected profits for each of these firms in the year. So I'll go through each of these 2 components. So in terms of generator production, we're going to enter an interval, and a few things are going to be realized. We'll have a realization of demand. We'll have a realization of each of the generators' available capacity constraints. So this is going to capture whether it's a windy day, whether a coal plant has an outage. It's going to be captured there. And we have shocks to the generator's production costs. Then the big guys, the strategic firms, are going to play a core node game. They're going to choose for each of their generators how much they're going to produce, constrained by whatever that available capacity is. And then the competitive fringe is going to produce whatever the difference is between what the strategic firms are producing and what the realization of demand was. Okay, so the wholesale market price is going to be whatever is the price that causes the competitive fringe to produce that difference. If we don't have enough capacity, this is when a blackout is going to result. So that occurs in every single half hour. Over the year, we get this expected sum of wholesale profits. Okay, that's just going to be a function of the portfolio of generators. Okay, so then over the long run, we're adjusting this portfolio. Okay, we build new plants or we retire the existing ones. Now these generators are long-lived. They carry over from year to year. Firms are strategic. So what this means is this is going to be a dynamic game in generator portfolios. Now, I'm not going to spend too much time talking about this, but I want to just briefly note, generally speaking, dynamic games pose a few challenges. I list some of them there. I'm going to address these challenges with some timing assumptions. There's going to be a finite horizon. I'll be explicit about what that looks like in just a moment. And there are going to be sequential moves. Okay, happy to talk about kind of the implications of all of that later. What this is going to look like is going to be in each period, firms are going to enter with some set of generators from the previous period and a cost of building generators in this current year. Nature is going to choose a firm to adjust. It's going to make a costly adjustment. It's going to decide what plants it wants to retire, what generators it wants to build, and then everyone's going to compete in this series of wholesale markets. I said there's a finite horizon. So after some period T, firms are going to be locked in. Okay, they're going to be able to continue competing in wholesale markets for the rest of time, but they're stuck with whatever the portfolio of generators is that they had in that final year. Okay, so what does that investment decision look like? So let's consider a particular firm, and it is able to make an adjustment decision. So it's going to choose a new set of generators for itself to do the following. It's going to want to maximize its profits in this period. It's going to get this capacity payment. Remember, there's this subsidy to capacity that it's going to get. It's going to have to pay maintenance costs. So it's going to be costly to just have generators. Okay, this is what's going to induce exit of plants, because if you're not using that capacity, or you have to pay a fixed cost for having this capacity, so you're going to want to retire it if you're not using it. And you're going to have to pay whatever the investment cost is of building any new generators that you didn't have before. There's an idiosyncratic shock to that investment cost. And you're going to continue with those generators into the next period. So there's a continuation value. Okay, so that's what the investment decision looks like. Remember, there's lock-in. So after some period of time, set of generators is fixed. Everyone just has those for the rest of what this final equation say. Okay. So I will give the, say, 30-second version of model estimation. So I gave you two components to the model, right? There was the short run and there was the long run. Similarly, there are two stages to estimation. So in the first stage, we're going to estimate the distribution of wholesale market variables. Basic ideas using firms' first order conditions to back out production costs. Using that, we can simulate what the profits would be for any given portfolio of generators. We can use that in a second stage where we're going to estimate what I'll call the dynamic parameters, things like the sunk costs, maintenance costs, the idiosyncratic shock distribution, and we're going to do that using maximum likelihood. Okay, so we've got the model, we've got the parameter estimates. Now we get to the fun part. We get to ask what would happen under counterfactual policies. So going all the way back to the first slide, what's this paper about? This paper is about thinking about how should we design electricity markets so that they're clean and reliable. So got these three sets of counterfactuals. What I'll focus on today is the first set, where we're looking at environmental and reliability policies. And I'll look at separately a carbon tax and capacity payments, and then these two jointly. And then I'll summarize the results of those two other sets of counterfactuals. In each of these, we're going to start off in 2007. That was the first year in the sample. We're going to begin with the same state as we had in the data in 2007 and simulate what would happen in the market going forward under whatever the counterfactual policy is. And yeah. So there is call it a small demand side. Okay, so we've got some distribution of possible realizations of inelastic demand, right? And this results from the end consumers. You know, they pay some fixed rate that's based on some like long run average cost, right? But you know, in the counterfactuals, when we say add a carbon tax, that's going to influence the price, that's going to influence the average price. That's going to filter down to the consumers, and that's going to shift the distribution. Okay, so if the wholesale market price goes up on average, the distribution of demand is going to shift down. It's still inelastic in the short run. It doesn't respond to whatever the spot market, an individual spot market price is, but demand is shifting. Right. Yeah. So it's not, you know, we saw earlier Octopus Energy. Some people are on like real-time pricing. I'm saying, you know, I'm just taking in, you know, the vast majority of people do not pay real-time prices anywhere. That's certainly true in Western Australia. You know, everyone's on like a fixed contract. Yeah. Okay, so, and to evaluate these policies, you know, we want to, I'm going to use the following welfare function. So it's going to be standard producer, consumer surplus, government revenues. There's going to be a cost of emissions. It's going to depend on a social cost of carbon, which I'll be agnostic about. I'm going to show you for a range of different values of the social cost of carbon. There's going to be a cost of blackouts. So the level of blackouts times a value of lost load. Okay, and this is where, you know, kind of how much should we trade off reducing emissions versus reducing blackouts. That's going to come from those two numbers right there. But what I'll do today, I'm going to use the value of lost load that's used by the Western Australian grid operator. Okay, so first exercise, let's look at the impact of a carbon tax. So no capacity payments, just a carbon tax. So what I'm plotting here is the expected capacity over time for these three different energy sources for different levels of the carbon tax. So that each line corresponds to a carbon tax. The darker the line, the higher the tax. Okay, so what do we see here? Well, even without a carbon tax, coal is declining over time. It's costly to maintain coal capacity. This is going to result in coal exit. And even a small carbon tax is going to make coal decline more quickly, more closely to zero. Okay, gas is pretty constant. Wind, however, is really responsive. We see more and earlier investment in wind as we increase the tax. Probably none of this is super surprising. We can also look at expected production shares over time. So previous slide was capacity. This is actual production. Okay, so we can see really clearly here, substitution between coal and gas. Coal is about twice as emissions intensive as gases. Okay, so early on in the sample, firms haven't yet had much time to adjust their generator portfolios. When we add a carbon tax, they're going to want to use more of their gas plants, less of their coal plants. We see that in the production shares. Okay, so what would all of this mean for welfare? So here we've got in these three subplots, three components of welfare: product market welfare, emissions, blackouts, as a function of the size of the carbon. Okay, so carbon tax distorts the product market. So we see a decline in product market welfare, but it also results in less emissions. Now, what's maybe most surprising here is the impact it has on blackouts. So for small values of the carbon tax, which are those that, you know, the values that we've largely seen in practice, blackouts are increasing in the tax. We've got coal plants that are exiting the market. We don't yet have, we don't have that much new investment, and so that's going to result in more blackouts. But past a certain level, we're actually going to get blackouts declining in the carbon tax. This comes from this happens for two reasons. So coal has exited the market. Gas is pretty constant. We get more wind investment. So wind's not particularly reliable, but additional wind farms are helpful for avoiding blackouts if it happens to be that it's windy when demand is high. Moreover, because we do have the distribution of demand responding to the price, we had a carbon tax. That means higher average wholesale market prices. That lowers demand, which also reduces the probability of blackouts. So we can use that to think about what the optimal carbon tax would be as a function of the social cost of carbon. And so I think this graph is like pretty reassuring to me in that, if we think of, like Econ 101, we have some emissions, we want to slap on a tax. In the case of carbon emissions, what do we want to do? Well, we want to slap it on a tax that's equal to the social cost of carbon. But there's a bunch of other frictions here, right? We've got this reliability issue. We have firms that have market power. Does the optimal carbon tax diverge greatly from the social cost of carbon? Not really. Okay, so policy tool number 2 was capacity payments. So we're going to set carbon taxes equal to 0, just have capacity payments. This is basically going to correspond to the world as it existed for the most part in Western Australia. So we can see coal and gas capacity is really responsive to the capacity price. So the darker the line, the higher the price. We look at wind, we actually see the reverse pattern. So the higher the capacity price, the less investment in wind. And this speaks to a debate that exists in the energy policy world, which is what is the impact of capacity payments on renewables? I find that these payments have a negative impact on wind investment, although it's not a huge impact and it occurs mostly at the end of this sample period. Yeah, so basically for a unit of capacity, wind gets a smaller payment because it's not going to commit very much capacity. Most of the time it's not going to have all of its capacity. And when we invest, when we subsidize coal and gas capacity, it's going to result in more generators. It's going to lower the wholesale market price, so that's going to lower the returns to investing in wind. That's what's driving this result.
You pay this capacity, you pay the system subsidy, and it will somehow be included with use.
So okay, I think I understand your question. So does this result in lower production costs? Is that basically your question as we subsidize capacity?
No, the question is, does it lead to windfall profits and how much? If you gas capacity test is fixed capacity compensation, but it's fixed compensation from the market that is made marginal cost pricing. My question is then, is that your windfall extra profit, or would they reduce their price with the wholesale price to take more compensation for the price?
I see. So they're not going to, conditional on a set of generators that are in the market, they're not going to reduce their price. So you're absolutely right. That's not going to influence their production. Now, it is going to impact their investment or retirement decisions, right? So that's indirectly going to impact, wholesale market prices. So these do have an effect, but you're right that conditional on the set of generators, it doesn't influence their prices. Yeah. You asked for a quantification. I don't have that exact. Well, I guess it's 0. Okay. So got 1 minute left. Let me quickly wrap up. So what's the impact of these capacity payments? Well, they're really effective at reducing blackouts. In fact, based on these results, Western Australia has kind of varied in the size of their payments in this region right here. So this suggests they probably could have reduced their payments significantly and kept blackouts nearly at zero, but they're increasing emissions, right? We saw a bunch more investment in coal and gas. Okay, that means the optimal capacity payment would be declining in social cost of carbon. Now, what happens when we use both of these policies jointly? So I don't have a lot of time to spend here, so let me just kind of like summarize this for you. So the top row, we've got capacities for each of these three energy sources. Bottom row, we've got production shares. So red is just a capacity payment, blue is a carbon tax, purple, their intersection, are both of these together. And so the capacity responds significantly to the capacity payments, while the production shares respond significantly to the carbon tax. And so that's how we get the result that I previewed for you at the very beginning, that if we use both of these tools together, we can reduce emissions and also blackouts. Okay, and here's the exercise if you want to do what is the optimal policy as a function of the social cost of carbon. So in the 30 seconds I have remaining, let me just summarize the other counterfactuals. So renewable subsidies tend to fare worse than does a carbon tax, and in particular, investment subsidies, which target the wrong margin, target the investment margin rather than the production margin. And as we delay a carbon tax, that's gonna get us some cost savings. It lowers production costs, it lowers wholesale prices, but it increases emissions. I find that, you know, for almost any value of the social cost of carbon, optimal delay is simply 1 year. So I think I'm out of time, so I'll just leave the conclusion slide up here. It just summarizes what I said in this presentation. Thanks.
Okay, thanks a lot for the organizers and thanks for putting the paper on the program. This sits somewhat in between environment and development. And we're going to stick with electricity, but we're going to move from wholesale markets to pricing for industry and how it affects industry. So I'm going to motivate the paper from two angles, from the policy side and then from the economics of the problem. And so from the policy side, we know that industrial development requires a lot of capital intensive production, capital accumulation. And this capital is typically machines that also require electricity to be run, to produce. So the question here is, how much can lower electricity prices help in this process? At the same time, we know that there's going to be a huge amount of demand from manufacturing and developing countries coming in the future. And usually we think that energy efficiency in industry is one of the key solutions to achieve the climate goals for industrial sectors. And here we usually think that higher electricity prices help to incentivize more efficient use. So in the paper, I argue that in some contexts, there might not be this apparent trade-off between environmental and developmental goals. So in terms of the economics of the problem, the empirical setting of the paper is going to be India. It's going to be manufacturing industry. So forget about residential electricity users, forget about agricultural electricity users, this is about industry. And in the late 90s, you have a situation in India that electricity prices for industry are extremely high. We're talking 8 times the OECD average in terms of PPP. So very expensive to use. And then over the 2000s, you see the dashed line, these are real electricity prices. You have the secular decrease by about 50% in terms of electricity prices. And this is true whether you look at, this is for manufacturing plant level data, but this is also true when you look at manually collected utility tariffs. Now, the solid line plots electricity productivity in manufacturing. That's deflated output divided by kilowatt hours of electricity used. You can see that during the 2000s, at the same time when you have this electricity price decrease, you have about a 35% increase in electricity productivity. And this is true whether you look within sectors or within states. It's not a story of pure reallocation between these. And yes. Yes. So electricity consumed here includes electricity purchased from the grid as well as self-generated for firms that have generators. So these these patterns, we're going to get to the causal story later, but taking these two patterns at face value presents somewhat of a puzzle. Because we would think that with lower prices for electricity, lower prices for one input, you substitute towards that input, you become less efficient in that input, you become less electricity productive. Okay, and that intuition is true in a world where you don't have any technology choices. But the story of the paper is that once you're in a world where you have technology choices, that doesn't need to be true. And Steve earlier in his great presentation mentioned the importance of electricity prices for consumers for considering buying electric boilers, for example. Here, the technology choices are going to be more general. So it's going to be choices between traditional labor-intensive manufacturing and modern capital-intensive manufacturing, where this modern capital-intensive production technique also requires a complementary input, electricity, to run the machines. And so then you can get a second effect, an output effect from switching to this modern technology that can overcompensate the pure substitution effect. And as a result, lower electricity prices can improve electricity productivity. Not only that, this will also give a boost to labor productivity, so we'll have broader developmental implications as well.
Right. So is that real output on the left-hand side?
So this is all in real terms. So prices in real terms, output in real terms. Yes, it's all deflated. This graph, so the dashed line is plotting electricity prices for industry. And the solid line is plotting electricity productivity, which is a ratio, which is real output, deflated output divided by kilowatt hours used, which includes both purchased and generated electricity. Okay. So in the paper, I have three goals. The first goal is to estimate a causal effect of electricity prices on firm and environmental performance. The second is to look under the hood and think about what are the mechanisms here, testing some model predictions. And then finally, I want to know what is the impact not only on firms, but also on consumers. What are the welfare implications and the implications for emissions? And three key findings that come out of this analysis are first, I show that electricity prices can indeed increase both labor and electricity productivity. Context is important. I show that the likely mechanism is that because electricity is complementary to modern production, that this upgrading channel is key to the story here. And this has not only benefits for firms, indeed 2/3 of the welfare benefits accrue to consumers in form of lower output prices. And those efficiency improvements for electricity productivity that I estimate help to limit the increase in environmental costs from emissions from scale by a large margin. Skip this. For the rest of the talk, I'm quickly gonna show you some theory to build some intuition how this is even possible. Then I'm gonna talk about the institutional background to set the setting for the empirical analysis, talk through some results, and then talk about mechanisms where I'll be testing some of these model predictions I'll show you in the beginning. In the end, I'll talk about welfare and emissions. Okay. Now here's a super simple model. Firms maximize profit. Profit consists of sales minus what they spend on capital K, labor L, electricity E, and some fixed costs. Sales are generated with a nested production function. In upper nest, firms combine labor L and capital services X. And in the lower nest, capital services X are produced by combining electricity E and capital K. And the innovation of the model is that there are technology choices. So C is indexing technology, where C is either 1, which is the traditional technology, or it's C prime, which is greater than 1, which is the modern technology. And so it's designed to capture 3 features of modern production. First, the modern production technology is more capital intensive. Second, you have a higher complementarity between capital and electricity because these machines require electricity to run. And third, they are allowed to have higher fixed costs. Okay, to fix some ideas, here are 2 technologies that produce the same output in the textiles industry. So on the left-hand side, you have a pedal loom. It's sort of operated like a bicycle, more labor intensive. On the right-hand side, you have a power loom, which requires electricity, and it's more machine intensive. Okay, from the model, there are a bunch of predictions and propositions I can derive, which I'll show you graphically. But first I'll answer Mark's question.
No, I do think about the example.
Yeah.
When we start cycle, I think
Yeah, I think that's a yeah. Yeah, I think nowadays you have a kind of big discussion coming up, about like these exact things about electrification. Because this paper is mainly about industry, and when I think about heat pumps, I'm mainly thinking about the residential sector. I'm not so sure, but I completely agree that kind of you have this analogy that it's not purely relevant for industry. So yeah, thanks for that. Yeah.
Whether it's like a high fixed cost production technology, whether it's the industry. I'm just wondering if this is a generalized problem.
What solve? What lower electricity
If you have like high fixed cost, low marginal cost technologies, you can get stuff in that equilibrium. That maybe invest into them, the reduction in the cost of the input lets you shift into the grid.
Yeah.
I mean, it's like maybe it's a cost problem.
No, I think so. But let's see if this slide speaks to your question. So this is just showing you kind of the solved model with graphs. On the horizontal axis, just focus on the top left for now. Once you go to the right, electricity prices decrease, okay? And then this is plotting electricity productivity. And then here you can see kind of lemma 1 in action, that if you stay on one technology, these are two different technologies, with lower electricity prices, unambiguously, electricity productivity will always go down. But when you look at firm decisions in terms of maximizing profits, you can see that at the thick blue line tracks optimal choices. At one point, when electricity prices fall far enough, the modern technology becomes more profitable. So you have to switch. And what it does to electricity productivity, you get this jump in electricity productivity, basically. And this is just one firm. But in the aggregate, if you have heterogeneous firms, these thresholds will be at different points, and you can also have, of course, multiple technologies, so you can get a more smoothly upward trending relationship between electricity prices and electricity productivity. But this jump will also improve labor productivity. Here on the bottom left, I think that's super interesting. This is plotting capital to electricity ratios. And in any sort of standard class of production model, CS model, certainly, you will always get that if one input becomes cheaper, you become more intensive in that input. And the only way the story can work is if you also get this jump in capital to electricity prices. So from lower electricity prices, you're going to increase in the capital to electricity ratio. And so that's something I can also test in the data. Okay, Anna. Absolutely, yeah. Absolutely agree. Yeah, thanks. Yes, Frank. Also goes up. Electricity quantity goes up, but output goes up even more. Okay, so let me just tell you on one slide, there's much more detail in the paper in terms of the institutional background. So where does power come from? How do prices come about? So power is mainly purchased from the grid. Individual firms do have generators, but they are mainly used or almost exclusively used to smooth across outages, because even in the Indian context, it's more expensive to self-generate than to buy from the grid. Importantly, in this context, power shortages are not related to prices. In part, this is due to the institutional context that utilities are not allowed to adjust retail prices in response to power shortages. And I collect data on power shortages and show that they're not correlated to prices. But in robustness checks, I can also control for shortages and results will up. Generation of electricity mainly comes from coal. This is going to be important for one of the instruments. It's mainly vertically integrated. There's been some deregulation after a policy shock in 2003, which I'm going to exploit for a robustness check. I already told you about the high prices. So this is about high prices in industry, and for the residential and for the agricultural sectors, much different, as Anant and Robin, have worked on. Prices are much cheaper, and in fact, there's a lot of cross-subsidization where high industrial electricity prices cross-subsidize cheap electricity prices for residential consumers and agricultural consumers, in part due to political economy considerations, because they are important voting blocks. And then finally, prices can vary locally from manufacturing plant to manufacturing plant even, and are supposed to be set according to cost pressures. And the kind of large decline in electricity prices you saw over the decade is due to a combination of factors, including reduced cross-subsidization over time, more deregulation and entry, and also a reduction in generation cost. Okay, now the main data set comes from the ASI, which is an annual factory level panel data with, importantly, information at the plant level on average electricity prices and quantities. A bunch of other data I'm not gonna talk about, just to show you a little bit of what these plants look like. On average, these have 72 employees. The electricity share and total variable costs are 6%. The electricity share and fuel expenditure is 2/3. And importantly, on the right-hand side, you can see that there are different information on book value of capital. And I'm going to be using machinery capital, which is the relevant type of capital for the story. Okay, I just want to show you quickly in terms of how much variation is there in the cross-section. So this is just for 2003, 1 year, and you can see these 3 different variables plotted, and the dark shaded areas are data. And then the densities to the left of it are once you partial out state by industry fixed effects. And this is just showing you that even within industries, within states, you still have a lot of variation, both in terms of prices, but also in terms of productivities. So I'm going to be using both within, but also across plant within industry variation. And I'm going to show you next about the empirical strategy, how I exploit this. So to start with, the main regressions are of standard type. On the left-hand side, I have some outcome. Here it's going to be logged electricity productivity, counting for self-generated electricity. On the right-hand side, I have electricity prices and logs. And then alpha are 4-digit industry by region by year fixed effects. So these accounts for any sort of confounding trends in technology or demand that can be differentiated by industry or spatially. But even within those fixed effects, you still have a bunch of endogeneity concerns. In a paper, I talk about these in more detail. Just to structure the discussion, we can break up the error term into a true error component mu, and then there are these endogenous components at the plant level xi and at the industry level lambda. So what might these be? Xi would contain any sort of block tariff issue. So if you get a shock to output, you will require more electricity, you will be placed potentially on a different block tariff. So you have some mechanical endogeneity. There could be some sort of plant level negotiating power with the utility or corruption that's related to the economic position of firms. There can be geographic sorting, measurement error. And at the industry level, you could have some sort of industry bargaining. The plants within the same industry get together, bargain with the utility. You could have some industry by state endogenous factors not accounted for by the fixed effects. So the way I deal with this is with instruments. I have 2 main instruments. I'm going to call them IVA and IVB. So the idea for IVA is that any exogenous price signal should also affect other plants nearby. So I'm going to use the prices of other plants in the same state, but in a different 2-digit industry. Why different 2-digit industry? To allow for some sort of industry bargaining. And then I'm going to weight the prices of these other plants by the distance in the purchase ratio, basically placing higher weight on plants that purchase a similar quantity to smooth across block tariffs. The second instrument is based on the idea that any cost shifters upstream in generation would also affect downstream prices. So it's going to be a classic Bartik style shift share instrument. Just quickly show you some details where the shifters are national coal prices set by the Indian coal monopoly for power utilities. And the shares are going to be pre-sample state level shares of coal in generating capacity. And we know from recent advances that for these shift share techniques to work, we need either exogenous shifters or exogenous shares. And then for the shifters, you might be worried that coal prices for power utilities are correlated with coal prices that some plants might be using directly. In the Indian context, it turns out it's actually not so much the case because the coal monopoly has a very different pricing regime for power utilities than for the industrial sector. And in fact, you can see that sometimes one goes up while the other goes down. But in robustness check, I can also exclude all plants that use coal directly, and the results are very similar. So the coal prices are set nationally. Yeah, exactly. I would love to talk to you later because I'm a little bit aware of time. There's some stuff I'm also doing with distances in terms of, because you know you also have some shipping costs and so on. But I'm gonna hold off for offline. And then the shares are here shown on the right-hand side, and the paper I show that they're not correlated with several pre-sample variables that you might be worried about. Okay. So both of these have their disadvantages and advantages. So let me show you some results. The first column is OLS, and then you have IVA and IVB. So you can pick kind of which one you think you prefer. So first, when you run an OLS, you get a result that's very much in line with initial intuition that lower electricity prices would decrease electricity production. I'm gonna interpret everything in terms of falling electricity prices because that's what happened over the sample period. You have to take the negative of the coefficient in your head. But the heterogeneity bias is large. So for both IVs, you get an opposite sign, statistically significant. And I want to make 2 points here. First of all, these two IVs are statistically different from each other. In the paper, I have a section thinking about heterogeneous treatment effect, kind of following Angus and Immons and splitting those up. And indeed, I find some support for heterogeneous treatment effects. So these are kind of different complies that are shifted by the instrument here. If you take the average of those two IVs, you get remarkably close to the prediction of the first slide that I showed you in terms of the improvement in electricity productivity from the realized fall in electricity prices. You also get a boost to labor productivity. You can split up the ratio, right? Electricity productivity is the ratio. You can split it up into components. The only thing I want to say here is that it seems like the endogeneity bias mainly operates to the output side. Okay, then I have a bunch of robustness check in the paper. I just want to mention two. So if you haven't, if you didn't buy the instruments so far, I have two more instruments for you that are based on the timing of the policy that I mentioned. Okay, so first there was a big electricity act in 2003. And so I'm interacting that with the distance to coal fields. Why that? Because that will predict entry of private generators into the system, which will affect electricity prices. And you get an IV coefficient that's very similar to the two that I showed you. The second IV exploits the staggered electricity market unbundling following the Electricity Act. And again, you get a very similar IV coefficient. Okay, so let me briefly talk about mechanisms. On the left-hand side, we have again the model predictions. Remember, if you go to the right-hand side on the x-axis, lower electricity prices. On the right-hand side, you have a table of the empirical counterparts, again, OLS and the two IVs. Already showed you these. First of all, profits go up with lower electricity prices. Very boring, that's not surprising. A little bit more interesting is that with lower electricity prices, total variable costs go up, and that's because plants scale up. Now let's look at some input ratios. So first of all, with lower electricity prices, the machine to employment ratio increases, and that's driven by investment into machineries. I'm going to skip this part. and turn to the last prediction that I want to show you from the model, where you have this very non-standard prediction that the capital to electricity ratio will increase, even though electricity is actually the input that gets cheaper. And indeed, I also find support of that prediction in the empirical counterpart. Now, if machinery capital is that important of a story, and we can think a little bit more about it. So first, if plants that are initially less capitalized, defined by a low machinery to labor ratio at baseline, then we would think that those firms would profit particularly from lower electricity prices from this technology upgrading effect. And indeed, when you split up, again, this is with industries, median sample split, those firms that have a lower initial machinery penetration see more benefits from these lower electricity prices. You may say, okay, based on labor to machinery ratio that's endogenous. So here on the right-hand side, I'm using a FDI liberalization in 2006, which only targeted a subset of sectors. There's this recent Econometrica paper arguing that this is an exogenous shock. So I'm running a triple diff here, looking at whether electricity prices don't have such a negative effect on electricity productivity after the capital injection. And indeed, it is less negative. So it is those firms that are particularly low in machinery penetration that benefit more from this mechanism. So this is very much a story talking about industrial development. This is not a story, I think, about France, the US, and so on. Okay, I also find evidence of fuel substitution. So this is between electricity and other fuels like coal and gas. This is going to be important for the emissions. I find statistically significant but very tiny impacts on TFP. And then lastly, I find that from lower electricity prices, price to marginal cost markups go up. So this is a great segue to the last section. What are the effects on welfare and emissions? So here the question is, from this 48% price decline that I showed you, what is the effect on producer surplus, consumer surplus, and governments? For producers, it's fairly straightforward because I observe profits and I have these estimated effects on profits. For consumers, it's a little bit more involved. So here I'm using a model of a generalized oligopoly and using the incidence share in this model. The important assumption here is that average variable costs are equal to marginal cost. And since I estimate marginal cost and observe average variable cost, I can actually test this assumption. And then what's key here is that I have data both on output quantities and output prices of what the plant manufactures. So I can run a regression of prices on estimated marginal cost, and I use my instruments that I have for electricity prices, which should also shift marginal cost, to estimate pass-through. And that combined with a few other things will give you the incidence share for consumers, which is 64 billion. And then finally, for utilities, I need some measure of the cost of supply of electricity. So I collect some data on that and find that the revenue losses from cutting prices are around 3 billion. So when you add these up, you get a figure of 99 billion US dollars, which corresponds to around 0.5% of Indian GDP on an annualized basis. Okay, so the last thing I want to talk about, these welfare figures don't include any emission adjustments. So, yes. Yeah. 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 The reason that Indian utilities are in bad financial health is certainly not because of industry. The prices are definitely above cost of supply. The reason is because they have super cheap prices for agriculture and residential consumers. Yeah. Okay, so here the question is, how much are the emission costs from this increase in manufacturing? So I use data on the emission factors. Sorry, I use data on the consumption for plants for electricity, coal, gas, and oil, combine it with emission factors. And then I used the dirtiness of the Indian power grid to calculate the additional emissions from electricity consumption. And what you get is from this price decline of 50%, you get a $4 billion cost at a social cost of carbon of $100 a ton. Now, importantly, the last thing I want to say here for the emissions is that you can run a counterfactual where you switch off these improvements in electricity productivity and lower prices. So assume there is no effect on electricity productivity. The increase in emissions would have been more than double, and therefore also the cost more than double. So these efficiency improvements help to curb the environmental costs by a large margin. Now, lastly, if electricity is the special input into modern production, we can think about, hey, let's look at the effect of another energy input. Let's look at the effect of coal prices on coal productivity and other plant outcomes using similar instruments. And here I find that both in OLS and IV, lower coal prices actually decrease coal productivity, lending support to this argument that this is really something special about electricity and not energy in general, which also helps, to think about climate policy where, at least in terms of the direct impacts, taxing fossil fuels like coal, the dirtier fuel, has less detrimental impacts on the firms directly. So let me wrap up by saying that in the paper, I show that lower electricity prices can improve both labor and electricity productivity. Context is important. The likely mechanism is that it's a story about industrial development of upgrading technology to a modern production process. And this is relevant for environmental and industrial policies. You might say, hey, wait a second. So does this mean we shouldn't tax fossil fuels because electricity is mainly generated with coal? So it's going to make electricity more expensive for firms. That's bad. It's going to make them actually less energy efficient. But I think that conflates two externalities. First of all, the pure environmental externality, for which you should still tax fossil fuels. And then you have the industrial development externality, where you actually want to think about subsidizing industrial electricity prices, or at least reducing the severe cross subsidies. And this then not has only implications for firms, but also for consumers through pass-through. So I'll stop here, and thanks a lot for listening and your comments.